on this July 20th, 1969.
It's one small step for man, one giant leap for mankind. Oh, that looks beautiful.
Ladies and gentlemen, good afternoon, everyone, and welcome to this special science event. But before I continue introducing the event, let me give our warmest welcome to Professor Samuel Ting, who today will be one of the speakers of the first session, and for exceptional reasons, he will need to speak seated. So, this is a joint science festival of the UPAP, the Swiss Physical Society, the University of Geneva, and CERN, with the participation of ESA and the support of the Swiss National Fund. And is held in the context of the 39th International Cosmic Ray Conference, which has brought hundreds of researchers to Geneva to discuss the latest insights in the high-energy universe. Now, we are very pleased to welcome a very diverse public audience. Some of you are participants in the conference, but we are also delighted to welcome many curious minds, science enthusiasts, or curious visitors that may be encountering these topics for the first time. I am very honored to chair this opening session. We are privileged to hear from a truly exceptional scientist whose research has significantly contributed to transforming our understanding of the fundamental laws of nature, from the laws that govern its fundamental constituents and their interactions to the most energetic and mysterious phenomena. Now, the first speaker is here today to welcome us, not only as a scientist, but also as the host of this House of Science. As a spokesperson of the Atlas collaboration, she played a key role in the discovery of the Higgs boson in 2012, alongside the CMS experiment, a major breakthrough in particle physics that crowned decades of theoretical and experimental work. This discovery confirmed that the mechanism by which elementary particles acquire mass, and it's a cornerstone of our current understanding of the fundamental structure of matter. Over the past decade, as CERN's Director General, she has led the laboratory through a period rich in scientific achievements, major upgrades, including the high luminosity LHC project, but also strategic planning for future frontiers, such as the proposed Future Circular Collider. Please join me in welcoming CERN's Director General, Fabiola Gianotti.
Thank you, Luciano, and a warm welcome to CERN also from me. Welcome to this stellar event, a voyage across the universe. And actually, CERN contributes a lot to the exploration of the universe. This is because we are the most important, most powerful laboratory in the world for high-energy particle physics. Particle physics is the most elementary of all sciences because it studies the smallest constituents of matter, the matter we are all made of the universe, and the laws of nature at the most fundamental level. So here you can see an aerial view of the region. You see here in red the border between Switzerland on the bottom part of the screen and France on the top part. You see Lake Geneva here. And this white circle shows the location of the Large Hadron Collider, the LHC, the most powerful accelerator ever built by humanity. It's a 27-kilometer ring, 100-meter underground. And it's today CERN flagship project. So CERN mission actually is based on 4 pillars: research, technological developments, collaboration across border, and education and training. And I will go through them one by one. And I will start with research, and here I apologize with my colleagues, physicists and scientists in the audience. I will be very basic because there are, of course, people in the audience with little background in physics. So what are the elementary particles that we study at CERN? They are, of course, not atoms, because atoms are not elementary. They can be cut into smaller pieces, and atoms are made of a nucleus surrounded by electrons. Nuclei are not elementary. They are made of protons and neutrons, and protons and neutrons are also not elementary because they are made of smaller particles called the quarks. And as far as we know today, quarks and electrons are elementary particles. They cannot be cut into smaller pieces. They are point-like. They have no substructures. And they are, therefore, the fundamental constituents of everything in this room. All of us, even Professor Ting, is made of electrons and quarks. And the Nobel Laureates, you will see later on, everybody is made of electrons and quarks. The visible universe is made of electrons and quarks. The Large Hadron Colliders allow us to study matter at the level of the quarks. So on physical scales, smaller than billions of a meter, smaller than 10 to the minus 18 meters. So the Large Hadron Collider can be seen as a giant microscope. If you want to study human cells, a tabletop microscope in a lab, it's sufficient. But the smaller the structure you want to study, the higher the energy you have to inject into the system to resolve even the smaller structures that compose the object that you are studying. At the same time, the study of the very, very small allows us to study the very, very big, so the structure and evolution of the universe. We know today, from cosmology, but also based on experimental observation, that the universe had origin some 13.8 billion years ago, from an initial state, so very high density of energy and very high temperature. It's called the Big Bang, the big explosion, but it was not really an explosion. It was an initial state of high density of energy and temperature, which expanded very quickly and then expanded at a slower pace. At the beginning, the universe was very hot and very dense, and was a gas of 3 elementary particles. And with time, it expanded and cooled down, and these particles started to combine together to form a structure of increasing complexity. So essentially, starting from the elementary particle, the quarks and the electrons, then protons and neutrons were formed, then nuclei, then with electrons, atoms, and so on and so forth, up to the beautiful macrostructures we see today, stars, galaxies, planets, etc. And there are 2 complementary ways of studying the universe and its evolution. One is to use telescopes on Earth or in space. Telescopes look at big objects, and by studying the farthest object, they can go back in time. Another way that allows us to go back really to the first instance of the universe is to use accelerator like the Large Hadron Collider. And actually, with the Large Hadron Collider, we are able to reproduce here in the lab at any moment in time the conditions that characterize the universe at millions of a second after the Big Bang. What does it mean? It means that the energy that we produce in the collision of the beams of protons that we circulate in the Large Hadron Collider corresponds to the temperature that the universe had at that primordial stage. So we are able to produce the conditions of that early universe. So, of course, this requires a lot of technology because the goals are extremely ambitious, almost vertiginous. And so we need 3 main instruments, big and complex instruments. We need accelerator, we need particle accelerator, particle detectors, and large computing infrastructure. And we need to develop cutting-edge technologies in many fields, as we will see later on. So here again is the Large Hadron Collider. Now the circle is indicated in yellow. What we do is to accelerate 2 beams of protons in the 2 opposite directions of the ring up to the highest achievable energy, where the limit only comes from the available technology. And the technology is that of superconducting magnets, because what is difficult in a proton accelerator is not so much to accelerate the particles, but to keep them on the circular trajectory. So you need a very strong magnetic field that bend the particles and they keep them on the trajectory with a precision. We control the trajectory with a precision of a few micron. A micron is a millionth of a meter. So the superconducting magnet that we use at the LHC allowed us to make a big step in energy compared to the previous collider in the United States. And then we bring these two beams into collision at 4 points of the ring, where in 4 big experimental caverns we have installed 4 big instruments that we call particle detectors. When I say big, it's really big. Atlas is the biggest of the 4. It has the size of half the Notre Dame Cathedral in Paris, but underground. So these detectors, they surround the full solid angle around the collision point, and they detect, record, measure, identify the multitude, the thousands of particles that are produced in the collision. So you have this high energy collision between the proton beams, you produce myriad of particles, a multitude of particles, and these detectors reconstruct the full collision event. So if the accelerator can be seen as a giant microscope, the detectors can be seen as giant and very precise digital camera, which takes picture of the collision event. But to give you an idea of the challenges, the 2 beams of protons collide 40 million times a second. So this detector must take pictures 40 million times a second. So again, the technology is really, really challenging and demanding. So we started operation in 2010, and 2 years later, we discovered a new and very special particle, the Higgs boson. Why is it so special? The Higgs boson is related to the mechanism that allowed matter, the matter we are all made of, atoms, to form in the early universe. Without this mechanism, we would simply not be here. So it's a very important particle for our own life. And here, for the experts in the room following the Cosmic Ray conference, we can also collide ion in the LHC, so lead, xenon, oxygen, neon, and lead, ion, and proton-ion collision. And we can make a lot of measurements relevant to cosmic rays, both in the central region of the detectors, but also in particular in the forward regions with the 4 experiments, but in particular in the forward region with dedicated experiments. So this is a spectacular image of the underground tunnel, the 27-kilometer ring. Those blue tubes contain superconducting magnets, those famous magnets that allow us to bend the particle. They are magnets at the frontier of technology still today, and they were even more so when we built them at the end of last century, in the beginning of this century. The construction of the 1232 magnets for the LHC is a brilliant example of collaboration between CERN and industry. It's not just a relation between a client and a supplier, because the technology that CERN needs very often does not exist when we need it. So on one hand, we are a driver of innovation, we push the technology. On the other hand, we cannot just go to industry and buy. We need to develop prototypes in-house at CERN, and then collaborate with industry, the most promising industry in the field, and then once the technology is mature enough, it is transferred to industry for the mass production of many accelerator components. So a few more key figures to impress you beyond what I already said. So the protons in the ring travel very close to the speed of light, so they make 11,000 turns of the 27-kilometer ring per second. And there are 200,000 billion protons circulating in each beam. The superconducting magnets of the LHC work at low temperature, because superconductivity is something that is reached at low temperature. And so the LHC operates in a bath of superfluid helium at 1.9 Kelvin, minus 271 degrees, which makes it the largest cryogenic installation in the world. So CERN has a diverse scientific program, not just the Large Hadron Collider. We have a series of additional facilities. For instance, we have the only dedicated facility in the world for the study of antimatter, which is an interesting partner of matter. I don't have the time to elaborate, but it's something about which we know very little today. We also have a nuclear physics facility, which in particular produces radioisotope for medical application. And we have an experiment to study the impact of cosmic rays on the formation of clouds as input to the modeling of climate and weather and climate change. So what's the next step after the discovery of the Higgs boson? First of all, the Higgs boson remains a very special particle. For me, it's the simplest and the most exotic and the most puzzling object we have ever discovered in fundamental physics. It is also related to the initial, the primordial epoch of the universe, as I said before, maybe also related to its fate, to its future evolution, and clearly related to many open questions in fundamental physics today. So we need to study it in all details. And then to illustrate the next step also, I want to show this beautiful image taken by the James Webb Space Telescope. And when we see beautiful images of the skies like this one, we are of course all fascinated by the luminous object, star, galaxies, etc. But actually for us particle physicists, like for astronomers, cosmologists, the most intriguing part is the dark part. 95% of the universe today is dark. When you take all the stars, galaxies, planets you see in the universe and you add them up, you get only 5% of the matter energy content of the universe. All the rest is a question mark, made of forms of energy and matter that we do not know and we cannot detect directly with our instruments, and for these reasons we call them dark matter, dark energy. So this is one of the next frontier. But also, what is also fascinating is the vacuum. In physics, the vacuum is not empty. It's full of energy, and it's full of particles flashing in and out. This is a quantum mechanics effect. And so understanding the structure and the energy of the vacuum is very important. You will say, okay, who cares about the energy of the vacuum? You should, because actually we think today that the energy of the vacuum is responsible for the current expansion of the universe. The universe is still expanding at an accelerated pace, so every point is running away from the other one. And we think that this is due to the energy of the vacuum, of which we know very little. So you see there is a lot to learn. So what are the next steps at CERN? Of course, in order to answer this question, we need a lot of different approaches. And at CERN, what we do is big accelerators. So we try to shed lights into these mysteries using what we can do, accelerator. The next step is to upgrade the LHC to operate with more intense beam. This is called the high luminosity LHC, which will allow us to record 10 times more data by 2041 than what the LHC has produced so far. And then the next step is what we call the Future Circular Collider. This is not yet an approved project, unlike the high luminosity LHC. And we have just completed the feasibility study. You can see it here. So you see the LHC, it's the 27-kilometer ring, and the Future Circular Collider potentially is a 90-kilometer ring, which, if approved, will become the most extraordinary instrument ever built by humanity to study the laws of nature at the shorter distances, and we know that the shorter distances are related to physics on the cosmic scale. Technologically, it's very ambitious, so it will push the innovation in many, many fields with application to society. I will come back to this later on. And we are in sort of friendly competition, in quotes, with China, because China is planning to build a similar instrument, so there is a competition on this project. So this leads me to talk about the impact of CERN on society. The instruments we need require the development of cutting-edge technologies in many fields that go from superconducting materials to vacuum technologies, cryogenic, electronics, robotic, artificial intelligence, big data, quantum computing, etc. And these technologies find application in many sectors of society and then transfer to society at no cost, because CERN embraces and promotes open science. So everybody knows by now that the World Wide Web was developed here at CERN in 1989 and then made available for everyone to use and develop. Another example are the accelerator for treating cancer using light ions like carbon ions. This is a therapy complementary to the more standard X-ray therapy, and in some cases for some tumors more effective. CERN instrumentation is used in medical imaging. You can see here in relation to space is a CERN dosimeter, is an instrument to measure radiation on board of the International Space Station. Our AI technologies are used for autonomous car driving, and we have developed superconducting cables that allows to transfer huge currents with no losses, and we have a collaboration, for instance, with Airbus for clean air transportation. All this will not have been possible without the history of CERN. The lab was founded in 1954 with the goal of bringing back, reestablishing scientific excellence in Europe after the war and fostering peaceful collaboration after the war through science. 12 member states signed the founding convention. Today we have 25 member states, mainly from Europe, and 9 associate member states from all over the world, from Brazil to India. And we have a population of more than 17,500 people from all over the world. More than 110 nationalities are represented. And if you look at the age distribution, the peak is at 27. So most of our community is made of young people, young postdoc, etc. I'm also here in this peak, and I will not move from here. No, don't laugh, because not kind. Anyway, so only 30% typically of these people, young people, remain in research in particle physics. The majority of them go somewhere else, and actually about half of them go to industry, and the rest go to other public institutions. So CERN educates and trains many, many young people. At any given time, we are training 5,500 young people, technicians, physicists, engineers, on many different domains, and then provide society with a continuous flux of talented people in STEM. We are in the auditorium of the Science Gateway. Is our new flagship project for scientific communication and outreach. The goal, one of the main goals of the Science Gateway, is to communicate the beauty and utility of science with the general public. There is no way we can think of addressing today's global challenges without the help of science. And we have to increase the trust in science in today's society. And it's actually, the Science Gateway has been very successful. We opened it to the public on the 8th of October of 2023. And since then, we have hosted almost 700,000 visitors from 175 countries. So I'm coming to my conclusion. CERN today is many, many things. Is not only a center of scientific excellence in fundamental research, actually the world leader with our international partners in high-energy particle physics, is a driver of innovation with many important impact on society, is an excellent platform for training the young generations, is an example, a brilliant example of collaboration across border with this community from all over the world. And it's a promoter of open science, as open science means sharing knowledge, sharing hardware, sharing software, sharing education with everyone at no cost, as a means of A, boosting science itself, B, spreading its benefit, and C, reducing inequities across the world. So CERN is a value system and really a precious asset of humanity, and now we are working to make sure that this very unique institution has a brilliant future. Thank you very much.
Thank you very much, Fabiola, for this brief introduction, overview of CERN, and also for reminding us with this last slide how let's say, the scientific excellence is not the only foundation of the work that we do at CERN, but they are equally important, the technology innovation in general, as well as openness in science and international collaboration. So let's thank Fabiola Gianotti once again with a round of applause. So our next speaker is a physicist whose career has spanned some of the most significant scientific and technological frontiers over the past 5-6 decades, from collider experiments on Earth, as you will hear, to experiments orbiting in space. Professor Samuel Ting was awarded the Nobel Prize in Physics in 1976 for the discovery of the J-psi particle in November 1974, a breakthrough that confirmed the existence of the charm quark and provided a solid ground to the quark model of matter, and marked the beginning of what became known as the November Revolution in particle physics, which would have reshaped our understanding of the strong interaction, one of the fundamental forces in nature. Professor Ting has also made major contributions at CERN, leading the L3 experiment, one of the large detectors at the Large Electron-Positron Collider, which under his leadership produced important results in precision electroweak physics and also in the search for new phenomena. Today, he continues to push the boundaries of exploration as the founder and leader of the Alpha Magnetic Spectrometer, the AMS experiment aboard the International Space Station, where I would say beyond the state of the art. Detector continues to collect cosmic ray data, searching for traces of primordial antimatter, investigating possible signals of dark matter, and studying the composition and propagation of cosmic rays in the galaxy. So please join me in welcoming Professor Samuel Ting.
Mr. Chairman, Director General, Barish, and Dr. Kajita, and ladies and gentlemen. What I would like to do today is to share with you a certain type of experiment in space. An accelerator has been developed in the last 400 years. The oldest accelerator still exists today, very low energy, but perhaps has done the most important work in physics. As Director General just mentioned, she has a very good plan for RHC and other future colliders. So, for me, search for fundamental particles in the universe means you have atom, outside you have the electron, inside you have nucleus, then you have protons, neutrons, and their forces bind the quarks together called gluons. Intuitively, the first question you ask is how many types of electrons are there? What is the size of the electron? Can the electron be divided into smaller particles? How many types of quarks? What is the size of the quarks? If I ask my theoretical friends, they will think these are useless questions. But if you don't do experiment, you never know. In 1963, I started my career at CERN, proton synchrotron. First, doing proton-proton interactions with Giuseppe Cocconi's group. I learned enormous amount of things from Giuseppe Cocconi. He mentioned to me, be very careful about the instrumentation. But the second thing he mentioned to me, never make a mistake. But if you do, no matter how many experiments you have done, people will remember the one you made the mistake. And this too has been a very important lesson for me. Another is Giorgio Baratini, who I worked with for many years. In addition, I also worked with Klaus Winter and Marcel Vivajan. My first experiment at CERN is in the storage ring, and proton go to mu plus mu minus experiment at ISR. In there, you look for quark, anti-quark annihilation, produce a photon, produce mu plus mu minus. And indeed, we see the cross-section of it. It's independent of energy of the accelerator, but only depends on a parameter called tau. For 21 years, I worked on electron-positron physics at R3 experiment. The simplest way to view R3 experiment is all the lab experiment, just like the Director General has mentioned. You create a condition very close to the beginning of the Big Bang. So this is the first experiment involving, for me, involving 20 countries, including United States, Soviet Union, later on Russia, China, and Taiwan, India, and all European countries. So this is the R3 experiment. The magnet is outside, is six stories high, followed by magnetic coil, by muon chamber, by calorimeter, by BGU crystal, and vortex detector. So the magnet weighs 10,000 tons. The uranium calorimeter has 300 tons of uranium, 100,000 channel, come from Soviet Union. I was told this is one of the largest international collaboration during Soviet time. There were 300 papers published and 300 PhD degrees. But you can, at least for me, summarize in a few sentences. Namely, within the current energy range, there are only 3 types of electrons. Electron we use in wire, electron from space, electron in the nucleus. There are 6 types of quarks within the current energy range. Most curious to me is electrons and quarks have no size. Their radius is less than 10 to the minus 17 centimeter. 10 to the minus 17 is a very, very small number. The results are in excellent agreement with the current theory of elementary particles. This is good for the theorists, but not extremely good for experimentalists, because only when you have a result confront with the theory, you learn something new. I was deeply involved in support of the superconducting super collider SAC project in Texas, and there's the accelerator plant with the 87 kilometers. I think it's in 88 at White House, President Reagan announced the construction of SSC and invited Steve Weinberg, myself, Bertrand Richter, and Jim Cronin to be there. Just a minute. What happened? Go back.
Go back, the other one. Yes, this one. Back.
After the untimely shutdown of SSC by the United States Congress, I was wondering what I should do. I realized that I've spent much of my career in different accelerators. And maybe I should do something new, something I know nothing about, something most people consider impossible. And this is how I started the AMS experiment. I thought I really want to do something totally different. I should mention I'm grateful to Herwig Schaper, former Director General, for introducing me to Johann Tromper, the director of Max Planck Institute, and who shared his vast experience with me about doing space. This is a cartoon people sent to me when I proposed the experiment. So you have a large collaboration, but not a single person in your collaboration ever done experiment in space. You have totally not qualified. And I agree with them. So my current experiment is started from 1994 and go to 2030 and plus on the International Space Station. The International Space Station is 109 meter by 80 meter, weight 420 tons. The total construction cost of the space station is about $100 billion US. The physics on the space station is the physics of dark matter, antimatter, and the origin of cosmos, a new phenomena. Through precision, long-duration measurement of charged cosmic rays. Charged cosmic rays have mass, therefore they are absorbed by Earth's atmosphere. Earth's 100 kilometers of Earth's atmosphere is equal to 10 meters of water. So the properties such as the charge and momentum of charged particles cannot be studied on the ground. To measure cosmic ray charge and momentum require a magnetic spectrometer in space. And this turned out to be difficult because if you put a magnet in, one end will point to the north, another end point to the south, so you lose control. And finally we figure out a way a magnet does not rotate in space. AMS is a state-of-the-art CERN particle physics detector. It's scaled to fit in the space shuttle designed to survive launch loads and space environment. One of the LHC detectors is typically such as CMS, 100 meter underground, 14,000 tons. In space, it's 400 kilometers above ground, it weighs 7.5 tons. NASA decided maybe we shouldn't trust you at all. And so they said, you first build a prototype, and then we put you on the space shuttle and see whether you survive. So they approved our project in 1995 and assembled in 1997. We fly for 10 days in 1998. Turn out we see some new interesting things. This is an example of helium in low Earth orbit. In the energy range between 100 MeV and 4,000 MeV. Over a large region between 30 plus minus 35 degrees, only helium-3 exists. And the helium-4 is not in this region. Unexpected observation. After successful test of first MSO1, the first flight, we received strong support from NASA and from all collaborating institutes to proceed with the MS mission on the International Space Station. So the first flight was 4,200 kilograms. The final flight is 7,500 kilograms. It was constructed in Europe and Asia with strong CERN, NASA, MIT, and DOE support, involving Korea, China, Finland, Switzerland, Turkey, Italy, Netherlands, France, Portugal, Spain, Mexico, and United States. Major support from CERN first provide engineering and technical support for integration of the detector. And CERN built a specially designed control room, provide the infrastructure, logistics support, as well as computing support. So we received continuous support from CERN Director General. Luciano invited the President of China, Jiang Zemin, to visit CERN, and then Robert M. invited Senator Bill Nielsen for a while, the head of NASA, and then Ralph Hoyle went to Kennedy Space Center. This is under the rocket for the shuttle. And I had the good fortune to meet Christine Lagarde through you. And let me mention, the first sentence she mentioned to me is, "I don't like Nobel Prize winners." And I said, "I'm a physicist, not an economist." And that seemed to calm her down. So the MS space shuttle flight was canceled by the White House after the Columbia accident. This decision initiated widespread reaction from physics community and press. There's many articles, and this one's the long-awaited cosmic ray detector may be shelved. And there are many quotes, including Nobel Laureate Barish, who I think is the next speaker, which said, "It is a crime to make this kind of investment, then walk away with it." So finally, both House and Senate unanimously approved legislation, H.R. 6063, ordered NASA to provide an additional flight to deliver alpha magnetic spectrometer and other scientific equipment and payloads to the International Space Station. So this is the AMS. On top is a transition radiation detector, identify electron positrons. Then there are 9 layers of silicon tracker marked 1 to 9, measure charge and momentum. Ring image drone counter, measure charge and energy. Electromagnetic calorimeter, measure energy of electron positron. Then 2 banks of time of flight counter, measure charge and energy. A permanent magnet, and also a veto counter, reject particles from the background. I should mention we received strong support from NASA, from CERN, which has been essential to the success of AMS. We have Dr. Corrado Gagiulio, who really was chief engineer for the whole assembly system, and without him, we would not have made this possible. Also, Kim Borwick, manager of NASA project office, who keep us not going to things that's not allowed by NASA. The original construction was a superconducting magnet. It carries 2,500 liter of superfluid helium at 1.8 K. And we spent enormous amount of time with the support of Dr. Andrew Simcoe of CERN to build this magnet. And then we test the magnet in the CERN test beam, and then we assemble the magnet ready to ship to Kennedy Space Center. Just before when we left CERN, I received a phone call, said now all the space shuttle are canceled. That means after 2,500 liters of superfluid helium is used, your experiment is there, it's useless. And so I remember it was April 16th, 2010. I had to make a hard decision to abandon this magnet to use a permanent magnet. The magnet is still at CERN. So this is superconducting magnet at the European Space Agency thermal vacuum chamber, and this is expected lifetime tested to be 28 plus minus 6 months. And that means every 2 to 3 years you have to do a refill. Superconducting magnet attract attention of many people. Of all the visitors, I remember 2. One, Steve Hawking, who was there for quite some time to understand what we're doing, and not just Elon Musk, who was there for 4 to 5 hours to understand how to build a superconducting magnet in space. Transition radiation detector identifies electron positrons is made out of 5,000 proportional tubes, 2 meters in length. And from the gas diffusion rate, we know your gas will last to 2040. Silicon tracker provide a coordinate resolution 5 to 10 micron, measure momentum and nuclear charge. The electromagnetic calorimeter provide a precision 3-dimensional measurement of direction and energy of positrons and electrons. And so the electron positron go in to the lead, become shower, and shower collected by optical fibers, and then you repeat at 90-degree direction. Time-of-flight system provide 50 picosecond for Z larger than 4, which is extremely good time resolution. And it's the Bologna group under the then Nino Takaaki did the enormous amount of work for this detector. The electronics, we use certain standard electronics, but they are not space qualified. So we use the commercial component. We go do radiation tests to make sure they are radiation tolerant. The assembly is at CERN, and this is a successful changing of permanent magnet to replace the superconducting magnet. Before we left, we made a calibration, an extensive calibration, because we realized once you're in space, you cannot go there to touch it. So we test the particles at different energies. And there's a letter from Steve Meyer said there's a decision from the director level to give maximum possible amount of help to AMS. By then, given the difficulties we had, everybody wants this experiment to be successful. The experiment finally is too big for Boeing 747, which is what we originally planned. So we have to go to the Air Force to borrow a C-5. And so Air Force quickly agreed to that. So one of the C-5 came from the United States, landed in Geneva, and put AMS on board to go to Kennedy Space Center. So this is at Geneva Airport, August 26th to just before lift-off. So this is the lift-off on May 16th, and then after 2 days, they approached the space station, and this is the captain, Mark Kelly, now a senator from Arizona. So the data in space has 7 gigabit per second, go on board with 650 microprocessors, processing 220,000 channels, and become 10 megabit per second, and go to White Sands, and go to CERN. The 650 microprocessors each have 2-fold or 4-fold redundancy. So the operation is 24 hours a day, 7 days a week, 365 days a year. And one of the things, one of the mistakes I made is I forgot once you are in space, there's no such thing as stop, as shut down, as upgrade. You simply cannot go there. And you always have to suspect something may go wrong. And therefore you always have to check it. And Dr. Mike Capel here was mainly responsible to make sure this doesn't happen to us. As of today, we have 252 billion cosmic ray events, up to trillions of electron volts. So the detector, TRD, time of flight, tracker, rate, echo, give different signal for different particles. From this, you can identify elementary particles and all the elements on the periodic table. So we measure the momentum, measure charge, measure the rigidity. Rigidity is momentum per unit charge, and measure the flux, and measure the energy. So once in space, at least for me, you always worry something may go wrong, and you do not know. And so we have continuous checking. An example is the silicon tracker. From layer 2 to layer 8, we have 24 laser beams inside. And for layer 1 and layer 9, we use cosmic ray every 2 minutes. So the stability over 14 years is 2 microns. Results on cosmic ray elementary particles. So cosmic ray interact with the interstellar medium, can produce positons, antiprotons. But dark matter collision can also produce positons, antiprotons. A light ray interacts with the magnetic field of pulsars, can produce positons. So all of this will be collected by AMS. This is our latest data from 1 GeV to 1,000 GeV. The low energy part can fit with cosmic ray collision models. The question is, what is this? This is 4.5 million events. And this can only be the other two sources, pulsars or dark matter. The curious thing is this data goes up and then goes down. And the goes down probability is 5 sigma. I remember a conversation with you mentioning about discovery of Higgs. You said 5 sigma is the minimum. That was some time ago. And so we now have reached 5 sigma to see this goes down. We still do not know whether it's due to dark matter or pulsars. But we also measure antiprotons. And this is the spectrum of antiprotons and compare with positrons. Above 60 GeV, these two spectrums is exactly the same. So the identical behavior of positrons antiproton above 60 GeV exclude pulsar origin of positrons. Then we also study property of galactic cosmic rays. Primary cosmic ray, helium, carbon, oxygen, and silicon ion are produced in stars and accelerated by supernova. So they have nuclear fusion and then supernova produce helium, carbon, oxygen, and then these particles collide with interstellar media, produce lithium, beryllium, boron, and so forth. So measurement, precision measurement of cosmic nuclei provide you understanding how the cosmic ray come from. I should mention we have benefited enormously from Igor Mostelenko and Subir Sakar for this analysis. Cosmic ray was discovered in 1912. Cosmic ray experiment before AMS typically has an error of 50%. When you have an error of 50%, you agree with all theoretical models. AMS is to 1% accuracy. When you have 1% accuracy, the yellow point is the data, and the dotted point is the theory. So no theory can explain all measurement. You can adjust a parameter to agree with one measurement, but the same parameter cannot explain all the other measurements. So now we have 1% measurement of all the cosmic rays, and we are eager for someone to provide a consistent, accurate to 1% explanation. This is one of the peculiarities. The results on cosmic ray. So that's a primary cosmic ray, which has a rigidity dependence, helium, carbon, oxygen, which is different from secondary cosmic ray. You notice the normalization are different, but the functional behavior of functional rigidity is actually the same for primary and totally different from secondary. Nobody knows why it is so simple. You look more carefully, you see the primary cosmic ray has actually two parts, the low energy part and the high energy part. And the secondary cosmic ray also have two parts. So up to now, we have measured 250 billion cosmic rays, provide the precision spectroscopy of cosmic nuclei. The separation between hydrogen and helium is the order 1 in a billion. Separation between iron and cobalt is 1 in 100 because of the rate. So for the first time, you really have every element measured accurately. or even now, is to understand why they have such symmetric properties. So all the 21 of the 28 elements can be grouped into 4 classes. We begin to measure isotopes. Isotopes are particles with same charge, different mass. We have a ring image Cherenkov counter, and which has sodium fluoride and aerogel, and it provides velocity resolution at speed of light to 4 parts in 10,000 for z larger than 4. This is an extremely accurate measurement of velocity, and therefore you can determine the mass. But again, see unexpected things, like the origin of cosmic deuterons. Primary cosmic ray interact with interstellar medium, produce deuteron helium-3. So deuteron and helium-3 are to be secondary particles. But if you look at the flux ratio of helium-3 over proton, they increase to 4 GeV and then gradually decreases. So this is a secondary particle. But if deuteron is secondary particle, then the flux should also decrease. Yet the flux does not decrease and become a constant. That means deuteron must have primary part. Why it has a primary part? How it comes from? Nobody seems to know, because everybody before this think deuteron is secondary. We also measure lithium. The ratio lithium-7 to lithium-6 as function of energy shows this measurement yellow point, and again shows the data does not fit the standard model of cosmic ray, which assumes primary component of lithium-7. It does not agree with this model, which assumes secondary origin of lithium-6 and lithium-7. The data shows a flat behavior above 7 GeV. So above 7 GeV, the rigidity dependence are identical, and therefore it's totally unexpected why it's like this. Then we begin to measure beryllium. Beryllium has 3 isotopes, 7, 9, and 10. Stable beryllium-9 goes through the entire galactic halo. Beryllium-10 decays to boron-10 before reaching the boundary of the galaxy. And therefore, the ratio of beryllium-10 to beryllium-9 measure the galactic size. This is our latest result, measure beryllium-7, beryllium-9, beryllium-10, and this ratio beryllium-10 to beryllium-9 is on the right side, and it goes to very high energy compared with the early measurements. Then let me share with you my favorite topic, antimatter. The Big Bang origin of the universe requires matter and antimatter to be equally abundant at the very hot beginning. But cosmic antimatter, such as antihelium, anticarbon, has never been found. Matter is defined by its mass and charge. Antimatter has same mass but opposite charge. So if you have an antimatter star, you have antideutron, antihelium, anticarbon, antioxygen. You need a very precise magnetic spectrometer to find the sign of the charge. These are two cosmic anti-helium-4 candidates. The one on the left has a mass. I could not see the value. The mass, yes, I can see it from here. Yeah. The charge is 2.05, minus 2.05, mass is 3.81. The one on the right, the charge is minus 2.05, the mass is 3.15 plus minus 5.3, namely exactly of helium-4 except opposite charge. So far, we have 66 million electrons, billions of protons and nuclei for matter. For antimatter, 4.5 million positons and 1.3 million antiprotons. These most likely come from cosmic collision or pulsars or dark matter. We begin to see anti-helium. The question is, where's anti-carbon and anti-oxygen? This is why we're now enlarging the detector and try to accept these particles. Let me share with you long-term AMS interplanetary exploration. Lethal cosmic radiation is approximately 300 rem. To survive long-term mission to Moon and Mars required complete radiation knowledge being uniquely provided by MS. So lethal radiation is being measured for its rate, time dependence, energy dependence for all the elements in space. So we found radiation changes hourly, daily, and yearly. So there's a vast difference, for example, in September 8, 2017, whether it's, you do it at 0 hour or you do it 13 hours. This is not in any cosmic ray models. Also, we notice the cosmic ray varies with energy. With energy, so the energy dependence of time variation, daily electron flux over 22-year solar cycle. This shows the relationship between electron and proton in 2011, 2012, 2013, 2014, 2020, 21, 22, and so it's a hysteresis. But for proton and positron, it's linear. Nobody understands why it is like this. So we have measured the scan dose of different nuclei over 11-year solar cycle. You can see for different nuclei, from solar minimum to solar maximum is factor 2 to 3 different from each other. This means as solar cycle 24 in solar maximum, the radiation over 3-year period is 120 rem. When you go to solar minimum, it's 240 rem. 240 is very close to the lethal dose. Without knowing this, you better not leave the Earth because you may not be able to come back. So we will be on the space station for the lifetime, and now we're in the process of upgrade. So we have finished a new 4+4 tracker plans, and this will complete. this will be completed, assembled by Dr. Corrado and his collaborators, and then with SpaceX, we'll put on the space station, and then we require 2 astronauts to connect the installation. So everything is ready, but now we don't know what's going on with NASA. So I began my career at CERN in '63. Over the years, I indeed have learned a lot of physics, and particularly instrumentation with the CERN community. Let me comment. Space is the ultimate laboratory. Space provides particles with highest energies. Thank you.
Thank you, Professor Ting, for this inspiring talk and also for your lifelong pursuit of fundamental questions, and really good luck for the installation of the upgrade. And so let's thank Professor Ting once again with a round of applause. And it is now my great pleasure to introduce one of the most influential physicists of our times, Professor Barish, who was awarded the Nobel Prize in Physics in 2017 for his decisive contributions to one of the most extraordinary scientific achievements of the 21st century, the first direct detection of gravitational waves, confirming a prediction made by Albert Einstein over 100 years earlier, and especially opening a completely and entirely new way to study the universe and its evolution. Now let me say that I learned a bit about the difficulties of putting together this project, and beyond the Nobel and the headlines, what's remarkable is the scale and complexity of what he helped build. And as the leader who brought to life the LIGO project, he wasn't just the visionary scientist chasing ripples in space-time, but he also had to navigate the tides of bureaucracy, the gravitational pull of funding agencies, and also the occasional black hole of skepticism. Please join me in welcoming Professor Barish.
It's a bit intimidating to follow these 2 speakers, but I'll do my best. I'm going to talk today about kind of an intersection between what I have been doing the last decade and the kind of physics that you've been hearing about from the last 2 speakers. So let me see if I can make this go. I'm going to start by just showing one slide that's gravitational waves, the discovery that we made. The picture on the left is actually the slide picture that was made by the Nobel Committee. So I didn't make it, but it shows the idea of 2 black holes coming together and emitting gravitational radiation. And then we detected it in an instrument that I'm not going to describe today called an interferometer, which is down there. And figure 1 of our discovery article is shown on the right, which is the image of the detected first signal for gravitational waves, showing as they merge together a signal that gets larger and larger, but much smaller than almost anything that was talked about today. Actually, 10 to the minus 21 is the size of the signal on that. I'm going to talk today about what I think is the future. The reason I'm doing that isn't this audience and it isn't the 2 speakers before, but what I've been spending the last month or so on, and that is that, to my shock, we realized that it's 10 years since we made the discovery of gravitational waves, and so we're putting together an event, or events, to celebrate it in September. September will be the celebration of the 10th anniversary of gravitational waves. It's made us reflect kind of on where we are, what we've accomplished the last 10 years. I could have talked about that because it's pretty impressive, not just the detection, but how we've managed, it's such a new field, how we've managed to explore it so quickly. We now have more than 300 examples of gravitational waves, quite a few that don't fit the picture that people have of what's out in the universe. We have black holes that are bigger than astronomers believe could exist, not like the ones at the center of the galaxy, but the black holes that are free-floating, which are presumably made by a stellar collapse. But rather than me give that, we'll have to do that in September, I decided that I'd spend my time today reflecting a little bit on something else, which is maybe the long-range impact that we might have, and I don't know how to do it, with gravitational waves and where I think it goes and how it fits in to the rest of the big issues that we're trying to solve, some of which you heard about a little bit earlier. I'm going to talk about the Big Bang, and I'm going to talk about how gravitational waves fit into the Big Bang and how we're going to understand it. Everybody cares about the Big Bang, I think, because one of the most successful television series in America that lasted actually something like 12 years is called The Big Bang Theory. It was a comedy series, and it was much of it was shot on my campus, on the Caltech campus, and many of us consulted on various of the episodes that they had. But we saw a picture at the beginning of Fabiola's talk, which is our best understanding, I'm going to talk about it in a little more depth, our best understanding of how the Big Bang happened and how it progressed. And so this picture is a summary, which we're able to make actually, of almost all the major issues in cosmology and how the universe began. My focus is to try to say, how are we really going to understand how it all began? Presumably everybody cares, since there's been a successful program on television. But this picture here shows 13.7 billion years of history. We know very well that that's the age of the universe. We measure it in a way that I'll talk about. The geometry that's shown shows it starting to spread in width very quickly compared to in time. And that's something called inflation that happens at the very beginning. A very puzzling issue. It doesn't mean that somehow in the early universe things went faster than the speed of light, but it meant that space itself expanded at a very rapid rate. And then eventually it slowed down to almost what we have today and what we thought we have today. And we were able to see things which I'm going to describe about 375,000 years after the Big Bang. I'll tell you how we do that. And then it's progressed from particles to stars and planets to galaxies and so forth, which we see today. So modern astronomy is done on the right side of this picture. And lastly, there's another puzzle, which I'll come to, which is the line also starts diverging again as you get near the end, and that's something we call dark energy. So unraveling the mysteries of the early universe, there's some really big questions, like what was the Big Bang itself? In fact, we call it the hot Big Bang. It was mentioned earlier today. Most things that are big and explosive certainly don't start hot. So something we have to really understand, if we're ever going to understand it, is what do we mean by hot Big Bang? We call it hot because the particles that exist once the particles are there a second or so afterwards have a lot of energy. And so there's a lot of energy and mass being created very, very quickly, and including the inflation. A second question is the one I already mentioned, and that is the inflation. I'm not going to make a long, long list. Those are two big ones, but maybe a third one is a little more personal, and that's why we're here. And that's a puzzle, because everything we know from the rules and theories that we have in particle physics, from all the experiments done here at CERN and elsewhere, when we have a lot of energy and we make particles, we make an equal number of particles and antiparticles. Apparently, that wasn't true in the early universe, and we have speculation why and how, but it's one of the biggest questions we need to answer. Obviously, if there was an equal number of particles and antiparticles made at this very early stage of the universe, we wouldn't be here, because they all would annihilate and it would be back to energy. So there had to be a small difference, which we need to explain. So how do we do that? Let me just mention. First, we have to look at theory and various ideas, and we rely a lot on that. They may be right, they may not, but it gives us a testing ground to try to do experiment, which is the final judge of what's right and wrong. Secondly, we have to find ways to probe experimentally to very early times. That's where I'll talk about, not very much, but where gravitational waves are the ultimate way to do that. Third, we need to recreate and study the conditions of the early universe in our laboratories. I'll mention that at the end as a way to understand the early universe. And fourth, we should keep in mind when we go to a very different regime, like the early universe, that it's not guaranteed that the laws of physics that we have tested and use on the Earth here in all our laboratories apply everywhere. It's not automatic that it's universal. We think so, we assume so within our universe, but it's something we have to keep in mind. So, first piece of the puzzle, big piece of the puzzle was answered here recently, and that is in the Big Bang, when it happened at the very, very beginning, a lot of energy was released, and then it started to convert and make particles or quarks, and eventually massive particles, protons, and so forth. And that whole physics of how we go from energy to mass was, of course, first focused on by Albert Einstein when he wrote down E equals mc squared. He told us that you can take energy and make mass. Of course, it was done to make that process was not understood why it happened exactly, but the fact that it happened enabled people to understand something called fission and make an atomic bomb, and later more peaceful things. But basically, the conversion of energy to mass is a wonderful example. Of course, it's a very central problem of how we go from a basic idea or conjecture to actually proving and understanding something. We don't yet totally understand it, and Fabiola previewed that by saying one of the big issues in the future is to really understand what the Higgs is and how it works, not just the conjecture and simple ones that we already have. So this is one of the pieces of the puzzle, how we went from a very hot Big Bang itself to a few seconds later creating some sort of particles. This is just a picture of the discovery of the Higgs particle at CERN. And I just want to point out how, because it's not what Fabiola showed, how good we are at actually finding something new in the midst of a lot else that's happening. So the pictures on the right show this little bump when you see in it. And in order to see that that little bump is actually something new, requires understanding that whole shape, what makes it, and then having the bump have enough statistical significance and the characteristics that a Higgs particle would have. So there's a lot that goes into doing that. Back to the early universe. What we understood about the early universe a little more than 100 years ago came, again, from Albert Einstein. And he basically believed that we had what he called a static universe. A static universe is one that is just there, nothing changes. And basically, we're just part of the static universe. That was not true, it turns out. And it was discovered not too long after Albert Einstein talked about a static universe, that the universe isn't static at all. And that was done by somebody named Hubble. And what he did was actually realize that you measure that elements in the universe were moving on the average at 70 kilometers per second per megaparsec away from us. And that's just the graph from his discovery that the universe was expanding. So we learned about 100 years ago that the universe is expanding. And it also illustrates that even Einstein sometimes isn't right. And then I'll jump another 10 years roughly into the 1930s, where a physicist at my institution, Caltech, who was colorful enough that there were stories about him by the time I got there, Fritz Zwicky, who made a discovery. He actually looked in 1933 at the velocities of, I can't read it very well here, of various clusters and how much they're moving away by using what we call the virial theorem, which conserves energy and momentum. And he saw that basically they were moving away in some cases much, much more than you would think by just the virial theorem. And so he estimated that the clusters that were doing that were moving at about 80 kilometers a second. But he found instead that they should be, that in practice they were moving at more than 10 times that. That meant that what he was looking at when he was looking at these clusters was dominated by something he wasn't seeing. And so he made a statement, which I've written here. And he concluded in his article in 1933 that if this would be confirmed, we would get the surprising result that dark matter, he made the name up at that time, is present in much greater amount than luminous matter, which turns out to be an exactly true statement, but one that nobody paid any attention to. So from 1933, for another essentially 30 years, it just was something that scientists said, but nobody actually pursued it. Then Vera Rubin and collaborators came along in the 1960s and made more detailed measurements of the motion of these various stars. And I'll tell you how in a second. And of course, she recently has been honored by naming a new facility in South America after her. But at this point, she very carefully measured the velocity of stars in a spiral galaxy as a function of how far they are from the center of the spiral. And as you went out, you would expect that their stars are less dense near each other, so they would be going slower than the ones earlier in terms of the amount of gravity that was pulling on them. But that's not what she found. What she found is shown here. And that is, as you go away from the center of the spiral, you expect, after you get out of the bunch, then into the tails, that you'd expect this drop off and in the brightness. Instead, it stayed up, and that was what was observed. And this turned out to be the first real proof that there is dark matter. We still don't know what it is, but that was the proof that there was dark matter. Second feature, the one I alluded to in the beginning, that is new and actually only discovered a decade or so ago, was found by these three gentlemen, two different experiments, all Perlmutter from Berkeley, Brian Schmidt and Adam Rees, who were working at Harvard. And they independently, they were checking each other, did the same experiment. They were trying to measure more carefully the expansion of the stars that are far away to see if they could detect that the universe was starting to collapse on itself, which people believe was true, or maybe it just keeps going and it was straight. But instead, they found a surprise, and that is that the universe was actually expanding now, increasing its expansion rate now. And that is shown here, where you can see, again, the same kind of graph that I showed before, but rather than follow the line, the dots at the top drop off to the right. And that means that we're going, as we go further up, we're going further away from the observer to these guys, to stars that are far away. And those stars that are far away are moving away from us, but slower than the ones that are closer to us. And so if you go back in time then, since that time, the universe has accelerated. So basically, we are now in a period where it's accelerating. That's all summed up in a graph, in a picture that many have seen, and that is the message, most important message to take home, is very little part of what's in the universe is what we see and what we detect. We have never been able to understand what the dark matter is, but we can detect that it's there. The dark energy is a big mystery. We don't know what causes an acceleration now in the modern times. It's not like the early universe. So I want to go back to the early universe before I end and talk about how we learn more than we know now about the early universe. So what we've done is we look at the patterns of stars and galaxies and so forth and ask how they could have evolved, and that's one way to kind of phenomenologically go to earlier times. But the best way we've had to understand things at early times comes about from another accidental discovery. This discovery was made by realizing or finding that there was background radiation that we didn't know was there. It was just noise detected by called the cosmic microwave background by these gentlemen in the 1960s. We now measure that background very precisely because we realize it's a vestigial tale or a memory of what happened in the early universe. And looking at it carefully, we can go back to the point at which those microwaves were absorbed, and that's 400,000 years after the Big Bang. So we're able to go back to 400,000 years after the Big Bang and see basically a photograph of what the universe looked like at that time. That's 400,000 years compared to now, which is 13.7 or 13.8 billion years. Of course, we want to get closer, and I'll talk about that in a minute. This background radiation is very, very smooth. That was discovered in a satellite experiment in the 1990s. And therefore, if we look at kind of the microstructure in it, it tells us things. And so this is the kind of picture that we look at of the universe, looking at this cosmic microwave background, and the different colors represent slightly different amounts in the different places. Sorry. And so by looking at this, first we can project ourselves forward in time to later times and try to establish how this kind of structure gives us the kind of structures we have now, like galaxies and so forth. And also buried in this is some information beyond just what the universe looked like at 400,000 years, which happened earlier, maybe. And so one of the big objects of the research now is to see if we can tell anything about what happened earlier by the fact that there could be some interference effects between gravitational waves, which were there earlier, and this background radiation, which would show itself in a particular way in this kind of graph that I've shown you. We're not good enough to do it yet, but the next generation of these experiments, that's their big goal. So this is one way to try to understand things earlier than 400,000 years. Best way is to actually have probes that can go back there. So what I show in this is kind of just a cartoon where on the right is now, and I've kind of rounded the numbers, where it's 10 billion, it's 13 billion actually, but a factor of 100,000 years earlier is when we can study photons, which I just showed you. If we could do exactly the same thing, look at this background radiation that came from the early universe, but the background radiation that was neutrinos instead of gamma rays, we could go back to about a second after the early universe was started. And that's when particles were just being made. So this would be a phenomenal goal. It isn't obviously impossible because there's a lot of them, as I'll show, I think, on the slide after this. So if we could actually detect the cosmic microwave neutrinos, we'd go back to 1 second after the Big Bang, or roughly 1 second after the Big Bang. But I show this just to show that it's not obviously impossible. This is the neutrino flux versus the different mechanisms, and the tallest and the most prevalent is actually the cosmic neutrino background. There's many of those neutrinos going through my hand right now. They're very difficult to detect because they've thermalized since the Big Bang, and they're very, very low energy, which is why they're on the very left of this graph. But there are ways that you can imagine, there's so many of them, you don't have to be very efficient. There are ways you can imagine how to detect them, and there's actually serious R&D attempts to make a prototype detector that would work to be able to detect these. So they're not obviously impossible. We don't know how to do it yet, but I can imagine that we will in the coming years. Better yet would be to detect the gravitational waves from the early universe, because then we could go back to the very first instance that the universe began. And so what we get is really the story from the start of whatever was what we call the hot Big Bang till now. Neutrinos bring us back to when particles were made, but we want to understand before that, for example, inflation, which happened before. And so gravitational waves would be the ideal way. We're not good enough to do that yet. We're only 10 years old, but give us a chance and it may happen. I don't know how to do it. I show here LIGO, which is our experiment that has detected gravitational waves, versus frequency. It's a frequency plot. And we're at very high frequency, which means we can see very spectacular things like the collision of two black holes. That's what we discovered. We know that there's rich sources which aren't as spectacular in terms of an explosion that we can see at somewhat lower frequency, and that's what's called LISA here, and it's doing gravitational waves in space, and we'd like to kind of smoothly move down in frequency. Even at lower frequency, we now have a search for gravitational waves that maybe is showing gravitational waves. It's not quite statistically significant yet at even lower frequency by using the fact that pulsars, something that we have around us, are very good clocks. And if we have a set of very good clocks and we look at them at the same time, and a gravitational wave passes through at low frequency, it'll distort the clocks relative to each other. And an experiment that is presently trying to do that, and they actually have a 3 sigma effect. That's not enough for us to call a discovery. And their data, the best candidate, is actually not the early universe, but some big black holes. But it's moving us in the direction of going back. And as I say, the field's only 10 years old. So that's where we are. This is their data. Instead of the correlation being no correlation between the different pulsar, each one of those error bars are a pulsar measurement of a different pulsar. And it has a shape which is a predicted shape, so that you know that if we have a source that that has gravitational waves that distorts things, you get a shape like this. This effect is presently not established. It's what we call 3 sigma, but it looks like the right kind of thing. And it isn't going to show the early universe yet. We're not there. But it's certainly showing our ability to move in steps to lower and lower frequency, which is what we have to do if we want to understand the early universe. So this is kind of a busy plot of how we get there. On the very left is where we want to go. That's when we can do, I show a picture on the bottom left of the kind of pattern that we look for in the cosmic microwave background that might have some memory of gravitational waves from the earlier universe that we might see within the next decade. Off to the left further, we require how to detect gravitational waves all the way back. I've shown you we're at least showing progress since the first detection. And so maybe we can do that eventually, I hope so. And then here is just a summary of some of the science that we're doing with the present LIGO and with the mission that'll go in space in the 2030s, and the pulsar timing that I showed you. And I think with that, I want to end with one other subject, which I'll show only on one slide. Everything I've shown you so far is how to study directly about the early universe by going to seeing effects that we can measure in the early universe, or that we can't measure yet, but want to be able to measure in the early universe. The other way we study as physicists is try to actually simulate in our labs, or in our labs create the same conditions that existed in the early universe. And that's basically happening. So what I show here is that if you take the region of space, if you want, where I'm plotting temperature versus density, where the science at the Large Hadron Collider falls, it's obviously not very dense, but it's high energy, and so it's off on the very left. I show then where you would be in another working facility at Brookhaven, a heavy ion collider, which is not as high in temperature, but very dense, and they see something that hints at early universe effects called the quark-gluon plasma. I show what we can learn with gravitational waves by the merger of neutron stars, which I didn't talk about it, but we've already detected since the first detection. And that just shows the illustration, if you want, of us being able to create enough information, not by measuring the effect directly, but enough information that we can determine something or test our belief of what the early universe might be like. And with that, I thank you.
Thank you very much, Barry, for this compelling and also accessible talk. I was also very pleased to see the last slide, which is about a program that is very dear to my heart. So let's thank Professor Barish once again. So our final speaker is a physicist whose work fundamentally changed the way we understand the building blocks of the universe. Professor Takaaki Kajita was awarded the Nobel Prize in Physics in 2015 for the discovery of the neutrino oscillations, a phenomenon that revealed the neutrinos, once thought to be massless, actually have a mass. And this groundbreaking discovery not only solved a long-standing open question puzzle in particle physics, but also forced to revise the standard model, which is our best framework to describe and explain matter and forces. So Professor Kajita's research was carried out at the Super Kamiokande detector in Japan, deep underground, where he and his team detected this subtle elusive transformation of neutrinos arriving from cosmic sources. Please join me in welcoming Professor Takaaki Kajita.
Okay, good afternoon. Well, I find it's very difficult to speak after such a great 3 talks. Anyway, I have to speak, so let's try. Okay, I see. Well, okay. This is the outline of this talk. First, I want to have a brief introduction on neutrinos and cosmic rays. Then, I want to discuss neutrino problems, discovery of neutrino oscillations, discovery of solar neutrino oscillations, and I want to talk about the neutrinos and the universe. And before finishing, I want to talk about neutrinos and cosmic rays. Well, of course, we are here for the International Cosmic Ray Conference, and I want to summarize this talk. Okay. Well, let me start about the birth of neutrino. Well, the story is more than 100 years ago. In the early 20th century, physicists were puzzled with beta decays, namely the measured energy spectrum of beta rays, or electrons, were continuous rather than a unique value expected for two-body decays. Well, if the true nature is a nucleon emitting an electron and converted to nucleus emitting an electron and converted to another nucleus, then we can calculate the energy of the emitted electron, which is a unique value. However, well, observed spectrum was continuous. What happened? Well, people didn't understand, but then in 1930, Pauli had an idea, and indeed, he wrote a letter to dear radioactive ladies and gentlemen. Well, in fact, nowadays, if one has a great idea, you have to write a paper. But he wrote a letter, and in fact, he was invited to a conference, but he had to go to another place, therefore he wrote a letter. Anyway, his idea was, when a nucleus emits an electron, at the same time, a neutral particle is emitted, then it is very natural that the electron energy spectrum is continuous. So this was the birth of neutrinos. Well, okay. after that, physicists studied neutrinos. And today, well, I don't have much time, and therefore, let me summarize what are neutrinos. Well, neutrinos are fundamental particles like electrons and quarks. And neutrinos are something like electrons without electric charge. And neutrinos can easily pass through even the Earth or even the Sun. So, well, certainly, neutrinos are elusive. But this feature is very important. Neutrinos can bring information of the fundamental processes occurring in the universe, say, at the center of the Sun. And we know that neutrinos have three types: electron neutrinos, muon neutrinos, and tau neutrinos. And finally, I want to say that neutrinos have been assumed to have no mass. Okay, well, this is a very brief summary on neutrinos. Then, you may ask, how can we study neutrinos? Well, of course, we cannot see neutrinos themselves. But, as I already said, neutrinos very rarely interact with matter. For example, a neutrino may interact with a nucleus. Then, typically in this case, a charged particle is emitted. And if a charged particle is emitted, we have various ways to observe this particle. For example, the nucleus there is a, say, water nucleus, oxygen. Then this particle propagates in the water. Then in this case, a light is emitted. Of course, we have various ways to observe light. We have a camera. Well, in fact, we have an experimental devices to observe photons. So we can observe this light or photons, and this way we know that a neutrino interact at that time. So this way we study neutrinos. Now, before moving on, I want to briefly talk about the discovery of cosmic rays, which was made in 1912. In fact, Victor Hess measured the intensity of radiation at the balloon altitude. Well, before this measurement, people knew there are radiation at the surface, and people thought maybe this radiation came from the ground. And if this idea is correct, if you go away from the surface, the radiation level will decrease. However, he found that at the balloon altitude, there is a higher radiation. So this was the discovery of the cosmic ray or cosmic radiation. And in fact, Victor Hess received Nobel Prize in Physics in 1936. And anyway, this discovery told us that there are phenomena in the universe that cannot be measured with optical telescopes. Therefore, since that discovery, we have been studying cosmic rays extensively. In particular, we'd like to understand where and how these cosmic rays are generated. Okay, now I want to move on to neutrino problems. Okay. Well, 2 pages ago, I briefly discussed cosmic rays. And in fact, these cosmic rays come into the atmosphere of the Earth, and these cosmic ray particles interact with the air nucleus, typically producing pions. Well, pions are small particles, but they are unstable. Therefore, pions decay to other particles, and during this decay, neutrinos are produced. And we call these neutrinos as atmospheric neutrinos. Now, I want to talk about the studies of these atmospheric neutrinos in 1980s and 90s. Well, in early 1980s, several proton decay experiments began. Well, in these experiments, people wanted to observe proton decays, which were predicted by grand unified theories at that time. We thought the discovery of proton decay should be extremely important. Unfortunately, no experiment observed proton decays. However, these experiments observed many neutrinos, atmospheric neutrinos. And because atmospheric neutrinos are the most serious background to the search for proton decays, these experiments had to study atmospheric neutrinos to understand the background to the proton decay searches. And during these studies, people realized that the observed muon neutrino events in their detectors are less than expected. In fact, missing atmospheric neutrinos were observed in the Kamiokande and IMB experiments. Both are large water detectors, and they observed many atmospheric neutrinos, and they observed much less muon neutrino events compared with expectations. Now, I want to switch to other problem. Well, we know that the sun generates energy by nuclear fusion processes, and neutrinos are created by these processes. Therefore, the observation of solar neutrinos is very important to understand the energy generation mechanism in the sun. In fact, already in the late 1960s, Ray Davis and his collaborators successfully observed solar neutrinos. And indeed, he received Nobel Prize in Physics for the observation of solar neutrinos. However, in detail, there was some problem. The observed event rate was about 30% of the expectation. People had no idea what happened. Anyway, this was a serious problem, and people called this problem as missing solar neutrino problem. Well, in the 90s, in the late 80s and 90s, several solar neutrino experiments indeed observed solar neutrinos. And these solar neutrino experiments confirmed the missing solar neutrinos. However, during the 20th century, it was not possible to understand the reason for the missing neutrinos. Anyway, in the 90s, these experiments, Homestake, Kamiokande, Sage, Galax, and GNO observed solar neutrinos. Okay. Then, well, in fact, people did not know what was the cause of these missing neutrinos. However, there were theoretical predictions that were made more than half a century ago. Well, at the bottom of this slide, I show two photos. One is Maki Nakagawa Sakata, another is Pontecorvo. And according to these people, if neutrinos have mass, neutrinos change their type from one type to the other while propagating. For example, in this slide, a muon neutrino is created at the left corner and begin to propagate to the right. Then at some point, muon neutrino type changes to tau neutrino. If this neutrino continues to propagate, then the neutrino type come back to muon neutrinos, then tau neutrinos, and so on. So this is neutrino oscillations. And well, certainly, if this is happening, we can explain the missing neutrino data. However, of course, this was just one of the possibilities to explain the missing neutrinos. Therefore, we needed much stronger data to tell if the missing neutrinos are due to neutrino oscillations. Okay, then I want to move on to the discovery of neutrino oscillations. Well, so the experiment that contributed significantly to the discovery of neutrino oscillation was the Super Kamiokande experiment. It is a very large detector. It is about 40 meters diameter and 40 meters high, and it contains 50,000 tons of very clean water. And in the right, I show a photo of the Super Kamiokande detector. And well, at the surface, there are 3 people on a plastic boat. So you find this detector is big. Oh, by the way, this is an international collaboration. We have many collaborators from various countries. Anyway, when Super Kamiokande started experiment, we knew the missing neutrino problems. Therefore, from the start of the experiment, we studied atmospheric neutrinos and solar neutrinos. And now I want to talk about the atmospheric neutrino studies. As I said, these neutrinos are created at the atmosphere of the Earth. And some of these neutrinos are created above the detector. And some of the neutrinos are created at the other side of the Earth and come to the Super Kamiokande detector after traveling a large distance. Anyway, here I want to show the Super Kamiokande result in 1988. Here I show 2 graphs. The top one is a neutrino arrival direction for electron neutrinos, and the bottom one is for muon neutrinos. And well, the horizontal axis is the neutrino arrival direction, and cosine theta 1 means downgoing neutrinos, and -1 means upward-going neutrinos. Then you can find for downgoing neutrinos, oh, sorry, I'm talking about the muon neutrino events, bottom one. So for downgoing neutrinos, the data and the expectation agreed well. However, for upward-going neutrinos, data show a significant, the number of muon neutrino events was significantly smaller compared with the expectation. And in fact, this can be very well explained if we simply assume neutrino oscillations, namely muon neutrinos created in the other side of the Earth propagate inside the Earth. But while propagating inside the Earth, the muon neutrino change to tau neutrino, muon neutrino, tau neutrino, and so on. And therefore, when they arrived at the super Kamiokande detector, the probability that the muon neutrino remain as muon neutrino is essentially 50%. So this way, Super Kamiokande was able to convince the neutrino community that neutrinos oscillate. Well, I was thinking to skip this slide, but I decided not to. Well, President Clinton gave a talk at MIT's 1998 commencement. And well, in the middle of his talk, he commented or mentioned about the discovery of neutrino oscillations. Well, he said, just yesterday in Japan, physicists announced this discovery that tiny neutrinos have mass. Now, that may not mean much to most Americans, but it may change our most fundamental theories from the nature of the smallest particles to to how the universe itself works, and indeed how it expands. Well, of course, as the US president, he mentioned that in Super Kamiokande, there are US collaborators working. Then he came back and continued. The larger issue is that these kinds of findings have implications that are not limited to the laboratory. They affect the whole of society, not only economy, but our very view of life, our understanding of our relations with others, and our place in time. I think the Super Kamiokande collaboration was honored to hear this kind of statement from the US president on the next day of the discovery announcement. Well, of course, the discovery was made in 1998. Well, but even if the discovery were made now, I wish that the US president would say the same thing. Now, I want to move on to the discovery of solar neutrino oscillations. Well, the experiment that contributed most significantly to the discovery of solar neutrino oscillation was the SNO experiment. It is again a large underground detector, and in fact, it contains a kind of water, heavy water, 1,000 tons of heavy water. Well, it is easy to say 1,000 tons of heavy water, but it is extremely expensive water. And well, they were fortunate. Canada government had this amount of heavy water. So this experiment was made possible. Anyway, there is a reason to use heavy water. Well, if they use heavy water, it is possible to observe the total solar neutrino flux, independent of the neutrino type. In addition, it is possible to observe how many electron neutrinos come from the sun. And here I show the result. If they observe the total neutrino flux, the observed event rate was just expected from the standard solar model. However, if they observe the electron neutrino flux, the observed event rate was only 30% of the expectation. And since the sun generates only electron neutrinos, the data clearly told us that 2/3 or 70% of the neutrinos are not electron neutrinos, which means neutrinos change their type. So this was the discovery of solar neutrino oscillations. Okay, well, these discoveries were almost 25 years ago. Since then, in fact, neutrino physicists were excited, and there have been many neutrino experiments that studied neutrino oscillations. Here, I show the list of these experiments. Maybe I think I still need to show some other experiments. So this could be the partial list. But anyway, I want to tell neutrino physicists were excited with the discovery of neutrino oscillations that shows neutrinos have small mass. Okay, now I want to move on to the neutrinos and the universe. Well, in the previous page, I showed neutrino physicists were excited with the small neutrino mass. But you may wonder, why? Electron has mass. Quarks have mass. Then, in a sense, it's natural that neutrinos have mass. Why neutrino physicists were so excited? Well, okay, let me tell. Here, I show the mass of elementary particles, quarks, and charged leptons, including electrons. Horizontal axis is the mass. Now, after 25 years of extensive studies of neutrino mass, we have now a rather good idea on some of the neutrino mass. Therefore, I would like to plot the neutrino mass here. And they are around here. So first, you notice that these gray dots were plotted in a different place. And please be careful about the horizontal axis. So 1 unit is 100. So from this plot, you can easily find that neutrino mass is approximately, or maybe more than, 10 billion times smaller than the corresponding mass of quarks and charged leptons. 10 billion times, or maybe more smaller. Very small. And we believe, indeed, this is the key to better understand elementary particles and the universe. Indeed, of course, if we understand why neutrino mass are so small. What is the mechanism to generate such small mass? We certainly understand elementary particles better, but we think the neutrino mass could be related to the understanding of the universe itself. Why? Well, of course, you saw several of these kind of pictures already. Well, we know that these galaxies and stars are all made of matter. There's no antimatter, no antimatter star, no antimatter galaxy. However, as already discussed in the previous speakers, we know that the universe began with Big Bang, hot Big Bang. And in the hot Big Bang universe, always matter and antimatter particles are created simultaneously. Therefore, in the Big Bang universe, we expect that the universe was filled with equal number of matter and antimatter particles. Then, as the universe cooled down, particles and antiparticles meet and annihilate, disappear. So, if our view is correct, at present, there should be no matter, no antimatter in the universe. But of course, we know that we exist. We are made of matter. In fact, we do not understand this question, why the present universe is dominated by matter particles. Well, we do not know, but there is a theoretical idea that neutrinos with very small mass might be the key to understand the matter in the universe. Okay, well, this is a great idea, interesting idea, but this is still a theoretical idea. Maybe right, maybe not right. Therefore, we have to confirm or exclude this idea by experiment. Well, unfortunately today, I do not have time to discuss the next generation of experiment, but anyway, we think this is a very important idea. Therefore, we'd like to attack this problem with the next generation very large neutrino experiments. Okay, then before finishing, I want to talk about neutrinos and cosmic rays. Well, at the beginning, I said we have been extensively studying neutrinos for essentially 100 years, but we still want to understand where and how these cosmic ray particles are generated. Well, say, there is a cosmic ray accelerator, and this, the particle is emitted from there, but there is a magnetic field in the universe. Therefore, the generated cosmic ray have a very complicated trajectory. Therefore, even if you measure the cosmic ray arrival direction very precisely, you get no information on the source. On the other hand, well, at the same time of the cosmic ray generation, neutrinos should be generated, and these neutrinos have, of course, no electric charge. Therefore, they go straight. Therefore, if we observe these neutrinos, we could know the source of the cosmic rays. Okay, well, idea is simple. Well, however, there is a background. Well, earlier, I discussed atmospheric neutrinos. And atmospheric neutrinos are very important for the discovery of neutrino oscillations. But these neutrinos are background to these studies. So, in order to avoid the atmospheric neutrino background, in order to find the cosmic high-energy neutrinos, well, so I already said high energy, sorry. One must study very high-energy neutrinos. Unfortunately, the expected number of neutrinos is not much. Therefore, we need very large neutrino detectors. And, well, I want to show some examples. At the South Pole, there's ice cube, and in the Mediterranean Sea, there is KM3 net. And in Baikal, Russia, there is Baikal GVD. So, well, actually, these are just examples. There could be some other possibilities. But anyway, I want to say that all these detectors are very large, typically 1 kilometer by 1 kilometer by 1 kilometer. So huge detectors. Well, in fact, people are thinking even larger detector in the future. Anyway, some of these detectors are already operational. And now coming back to cosmic rays physicists have been thinking that cosmic rays, which are not extremely high energies, are originated in our galaxy. Therefore, we think we should observe neutrinos from the galactic plane. And here, I show the result. Well, the top panel is the galactic plane observed optically. The middle one is the galactic plane observed by gamma rays. Then the bottom one is the galactic plane observed by neutrinos. So indeed, now we have evidence that neutrinos come from the galactic plane. In addition, well, today I don't have time, but extragalactic neutrinos have been observed. So I think we are now entering a very interesting era. Okay, let me summarize. Well, as the title said, neutrinos are elusive particles, but neutrinos have been playing very important roles in understanding the laws of nature, and neutrinos are likely to continue playing very important roles in understanding the smallest particles and the largest universe. And finally, I hope you agree with me that neutrinos are worth pursuing. Okay, that's all. Thank you very much.
Thank you very much, Takaaki, for really illuminating the hidden world of neutrinos and with your discovery opening new doors beyond the standard model. It was really fascinating to see all the new ideas on how to experimentally address some of the big open questions. So let's thank Takaaki Kajita once again. So unfortunately, we are significantly behind schedule, so we will not be able to take questions. So this brings us to the end of this session. It has been truly a privilege to hear from such outstanding scientists. And so we thank Professors Ting, Barish, Kajita, and Gianotti for their inspiring contributions. We thank you all, also in the audience, for your presence, for your attention. And now, since the next session, which is titled Exploration from the Invisible Universe to Exoplanets, starting at 1850, we had to delay it a bit. Nevertheless, we kindly ask you to exit the auditorium promptly, such that we do not accumulate further delays. We hope you enjoy the rest of the stellar event, and we look very much to welcoming you again at the CERN Science Gateway in the near future. Thank you very much.
Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running. We have a liftoff. Liftoff on Apollo 11.
On this July 20th, 1969.
It's one small step for man, one giant leap for mankind. Oh, that looks beautiful.
Good evening, ladies and gentlemen, and welcome to the second session of our stellar event, an event organized with the International Conference on Cosmic Rays that is taking place right now in Geneva. This is a world conference for mega experts in cosmic radiation. So far, we've heard from distinguished scientists, 3 Nobel laureates, and our Director General, Fabiola Gianotti, have brought us very close to the mysteries of the universe. They made a very, very nice and detailed account of the many things we don't know from the universe, and of how close the infinitely small of particle physics is to the infinitely large of our universe. The panel today is the first of our second session. The session is called Galactic Exploration, from the invisible universe to exoplanets. And I know that this word exoplanets, many of you are expecting somebody very famous here in Geneva. I won't say his name. This will be the session just after this one. We are starting with a panel of lady scientists who are all building, operating, imagining, and analyzing data from extremely complex and futuristic instruments to hunt this invisible universe that is all around us, and the universe that holds a lot of mysteries yet, in spite of all the progress done so far. So I'm very glad to call on stage to join me here Dr. Patrizia Caraveo, astrophysicist from Pavia University and the International Union of Astronomy, the president of the International Union of Astronomy in Italy. Welcome, Patrizia. You can sit close to me. Then we have Professor Teresa Montarulli from the University of Geneva, also an astroparticle physicist. I will tell you what she does later on when we talk to her. And Dr. Clara Nellis, somebody very close to me. She's a colleague of mine here at CERN, particle physicist from the Atlas experiment, also very famous for her science communication work as astroparticles. Go on Instagram, check for her. You will learn a lot, and you will have fun at the same time. And I'm also very honored and pleased to welcome here on stage another scientist who is maybe more famous for being an astronaut rather than a scientist, but she's both. Megan Christian, Dr. Megan Christian, European Space Agency Reserve Astronaut, Head of Commercialization and Exploration at the UK Space Agency. We can take a seat, everybody. So I need actually the clicker. I don't see the clicker here on stage. Can somebody bring me the clicker for going through the slides? I'm going to go through the slides for you. Thank you very much. Okay, so we are talking about these sophisticated instruments that these ladies are imagining, designing, operating, building, and analyzing data from. And I would like to start with Patrizia. So I was saying Patrizia is an astrophysicist. She teaches at Pavia University. She's also the president of the Italian Union of Astronomers or Astrophysicists. Is that astronomers, right?
Astronomers.
Right. And Patrizia is at the forefront of many instruments that most of them are in space. So she gave a major contribution to space missions that are very famous, like the Integral, Fermi, and Agile. She's an expert in neutron stars, in particular pulsars, and she had many many honors. One of them I'm really glad to mention because it's typically given to men. It's the Légion d'honneur. You are a Chevalier de la Légion d'honneur. Who gave it to you? Monsieur Macron?
I am commander.
Commander. Was
Yes.
it Macron or another French president?
No,
who gave it?
and I have the Italian degree, commendatore.
Okay, yeah, okay, so Patrizia, with you, I want to go through so these are the slides I should have shown while talking. So we see here some new ground telescopes. I just wanted you to go through them. It's an array of impressive, mostly ground-based astronomical telescopes. Can you just describe them for us?
I just pick few because the time is limited. I wanted to give credit to the Vera Rubin telescope. This telescope just had this important moment which is called first light. So the telescope released the first images, has been named to honor a lady scientist who was mentioned by Professor Barish in the previous talk, because she is the mother of the dark matter. And this telescope is particular since it's a big telescope, 8 meters in diameter, but it has an enormous field of view. So it will survey all the southern sky every 3 days. So we will have always a picture of the sky up to date. While
sorry, just interrupted. This is in Atacama, right?
Yes.
I recognize the geology of the place.
In Chile. Chile is the heaven of astronomy, and always in Chile, in a slightly different place, the European extremely large telescope, which is being built. This is a monster telescope, 39 meters in diameter. And it's a promise to be a real revolution. Is as big as the Colosseum, but it should move with millimeter precision. So these are the one is a telescope now being open, and the other one is being built. We European astronomers are very proud of it, but there are other instruments we are proud of. And you see here the Cherenkov telescope array and observatory. It's an observatory which is made by a number of telescopes. It's the telescope looks more or less optical telescope, but they are optimized to see the light emitted by particles crossing the atmosphere. So it's a high energy instrument and will be built in 2 sides since the sky should be explored in its totality. The northern sky will be studied from the Canary Island, the southern side from Chile, next to the extremely large telescope. We shall build our instrument in the ESO ground. And the idea to build an array of instruments it's the ultimate solution to get something very sensitive, so to allow scientists to study faint objects, keeping the price reasonable, since all those telescopes are being built to know how to work together. And so they will behave like one. And it's a technique which was started in radio astronomy. And this technique is now brought to its maximum capability with this other project, the Square Kilometer Array Observatory, always. And you see here, it's made by two different types of telescopes. Usual, let's say, radio telescope, which shall be built by dozens, literally, in South Africa, while the other one, looking like a Christmas tree, it's a different type of radio antenna, and they will be built in Australia, in the Australian desert. So, two arrays of telescopes under European leadership. So it's very important. And let me say that both were born thanks to the vision of a great scientist who also happened to be my husband, Giovanni Bignami. I mean, he is not with us anymore, but he was the first one to really believe in these two instruments, and as president of the Italian National Institute for Astrophysics, he gave the first really important push.
And it's very nice that you are getting his legacy alive again.
Yes. So the next generation space telescope, since astronomy is also done from space, it's just following two different paths. You can try to build a very big telescope. So we are talking about the Habitable World Observatory, the Flute, which is an instrument with a liquid mirror 50 meters in diameter, so something absolutely fantastic, but they are still on paper, they are still futuristic. And, but there is also another road, very small object, but a constellation of small objects, and they must be built to work together in order to be able to see, for instance, very bright transient supernovas, gamma ray burst, something very bright, then does not need an enormous collecting area, but it needs an eye in the sky, and this can be done. Of course, there is also the option to go to the moon. And
everybody wants to go to the moon. I think somebody there is.
I'd quite like to go to the moon. And there are plans to build a telescope on the moon, and using a crater on the moon and using a robot to just build an antenna on the moon. Once again, it's a project for the future, but it's been studied intensively since we want to go back to the moon, and the moon, it's a pristine environment, especially for radio astronomers, since with no atmosphere, in this case, they want to go on the other side of the moon, so in a completely silent environment. And we really hope to be able to do something on this respect.
We first have to go there again.
Yes.
Thank you for mentioning this specific telescope, future telescope, because one of the reasons why we are here tonight is that in a few hours will be 20th of July, which is the 56th anniversary of the first human moon landing. And so this is one of the reasons also why we involved astronauts in these events, because the moon is the next step, right? Is the right, Megan? That's right. I think our microphone is not working, so can somebody do something about that? So I also wanted to tell everyone that we are taking a few questions. So there is going to be a QR code displayed on the screens on the sides. There it is. So if you want to send your questions in, you just scan that QR code and I will receive some questions. We don't have time for many, but we will try. So our next speaker is Particle Clara on the far right here. So Clara is a particle physicist, so a girl from the house here, working at the Atlas experiment, which is just behind us, no, that direction. Yeah. And it's actually at the moment collecting something like 40 billion collisions per second, 100 meters below our feet, because it's part of the Large Hadron Collider, obviously. But Clara, with you, I just wanted to go back to the origins of particle physicists before accelerators. What were particle physicists doing?
Yeah,
how did they start this discipline?
So yeah, you can hear me, brilliant. Yeah, so originally, when we wanted to understand the smallest building blocks of our universe, we were reliant on the natural phenomena around us. So we were able to look at radioactive decay, so things like alpha emission and things like that, to be able to understand what the universe is built from on the smallest scales. And one thing that was observed is there was this radiation all around us, and the assumption at the time, about 100 years ago, was that if we left the Earth, then in a hot air balloon, not in a rocket, this radiation would reduce as we got further from the Earth. And the studies actually showed from Victor Hess, his sort of landmark flight, that the radiation increased as we went further from the land. And this is what we now know as cosmic rays, that there are particles coming from outer space all around us, showering down on us. And this is a very useful way to study our universe. So we can build cloud chambers, which are early sort of particle detectors, and study particles that are naturally around us. So we were able to, for example, discover antimatter
by observing cosmic rays.
By observing cosmic rays and also the natural radiation around us, so natural radioactive decay. And so this is the very first picture of antimatter ever taken. It's one of my favorite pictures. It looks very simple, but it was such a huge sort of scientific achievement able to measure this. So what we're seeing is a light particle that's passing through a cloud chamber, and there's a block of lead in the middle and a magnetic field. So charged particles, when they pass through a magnetic field, their path gets bent. And this looks exactly like an electron, but its electric charge is the wrong way round.
Because it goes in the opposite direction as an electron.
Exactly. And so this was the first discovery of a positron, what we now call a positron, which is a positive electron. So we were doing really advanced particle physics studies with the natural phenomena that was around us. But then we sort of hit a limit where if we wanted to study our universe further, we needed to be able to artificially accelerate particles and then to be able to look at the structure, the internal structure of the atom, and then even further inside the particles.
So this machine that is now under our feet, 27 kilometers around, through France and Switzerland, may I call it like a cosmic shaker?
A little bit, yeah. So it's well, shaking the particles in one direction very quickly.
And in the other.
And in the other direction, of course. And then we collide them. So this is, as you know, but we have the 27-kilometer long particle accelerator, the Large Hadron Collider, and it accelerates protons in opposite directions around the ring. We have 100 billion protons in each bunch, and then between 2,000 and 3,000 bunches in each train of the particle beams, and they collide at very close to the speed of light in the center of our detectors. And then we're using Einstein's equation, E equals mc squared, and this allows us to convert the matter of the protons, or sometimes other particles. We just recently collided oxygen and also neon, which was a really interesting study. And we can then convert this matter into energy and back into new matter, which is new types of particles.
And because you're a member of the ATLAS experiment, of course, we have to mention the discovery that you, with 4,000 other physicists from your experiment,
yep,
and 4,000 from CMS,
yeah,
did together in 2012.
Yeah, so we had the discovery of the Higgs boson, which was a huge achievement for the Large Hadron Collider. And the Higgs boson is associated with the Higgs field, which gives mass to many particles in our universe. We're not sure if it gives mass to neutrinos, so that's still a big question. We think not, but it's something to study. And so discovering this new particle was such a huge achievement. We had a huge seminar here at CERN to celebrate the discovery, but it's the first step. It's not the end of the research. It's you discover a particle, and now we want to know everything about it.
So what's next after the LHC?
So after the LHC, right now we're in a really exciting time because we are discussing in the community what particle accelerator we would like to go to next. These accelerators take decades to design and construct in order to be able to do this research. So we're going through something called the European Strategy for Particle Physics right now, which is a huge process where particle physicists from Europe and all over the world are discussing what collider we want next. And one of the big options that we're talking about is we have the 27-kilometer long Large Hadron Collider, and we're talking about going to 90 kilometers. So 3 times the size, called the FCC, the Future Circular Collider. But in this case, we would change the type of particles that we are accelerating and go to electrons and positrons, those positrons I talked about earlier, in order to specifically do precision studies of the particles we've already discovered, like the Higgs boson, to be able to untangle other information about how our universe works.
But in the meantime, we keep colliding.
In the meantime,
more
we keep
and more
colliding.
Particles.
And also, a very important point is that the Large Hadron Collider is going to get an upgrade. So next year, we're going to start upgrading it to the high luminosity LHC. So this is almost like getting a new collider in itself. We've collected about 10% of the data with the Large Hadron Collider so far, and we're going to get 90% more with this upgrade. And data is really what particle physicists love, because that's how we can look for really rare events and understand the particles that we've discovered. And maybe search for things like dark matter if it's a particle that could be created in our detectors.
So regarding the objectives of these machines, there is a lot of complementarity between what we do underground with some artificial stars that are exactly the same as the cosmic that we get from the cosmos, and the big picture of the cosmos.
Yeah, so it's, our research is really complementary to the astrophysics research and cosmology research, because we send telescopes out into space or build them in, around the world to look at our universe, and the further out into our universe we look, the further back in time we are observing our universe. But there is a limit to how far back in time of the universe's lifetime that we can look with telescopes. And so to be able to understand the very early universe, fractions of a second after the Big Bang, we want to momentarily recreate those conditions, which we do with heavy ions like lead when we collide them in the center of the LHC. And we can, recreate the conditions of the early universe and understand how the particles interacted with each other, how they evolved, and it tells us more about our universe.
And it tells you gives a lot of precision to the models as well for what's next. Thank you, Clara. We'll get back to you as well as to Patrizia in a second round of questions. I would like now to talk a little bit with Teresa Montarulli, who is an astroparticle physicist from the University of Geneva. She's a leading expert in the cosmic neutrinos we heard about before from Professor Kajita, and also gamma rays. These are very high energy sources of particles that arrive on the planet. You took part in a lot of big experiments from, let's mention quite a few, Macro, Antares, IceCube. We are going to talk to IceCube very soon. And that's your specialty, trying to understand the origin of these particles. So here is an image, still with the LHC, and an image from the cosmos. Would you like to start commenting this?
Yes. So this is sort of an analogy between the two things, because these accelerators that are in the universe are similar in concept to the LHC. There are intense magnetic fields, and these magnetic fields accelerate the charged particles that then we see colliding in the detectors in LHC. But in the case of these big monsters that we have in the universe, these particles can reach us and bring information.
So the cosmos is a big accelerator too.
Exactly. So they basically concentrate the magnetic fields that we would never be able to achieve on ground. And so that's why they can produce the particles that have the most extreme energies that we know. But not only, they are really laboratories in the universe, because, for instance, the black hole that is in the core of the galaxy that you see is actually an object in a state of extreme gravity. So one has also the opportunity to know better not only particles, but also the forces that are governing our universe.
Yeah,
like
we mentioned
gravitation.
before the discovery of cosmic rays. I will pass on that, but this is a very important concept. We
Yes.
spoke about complementarity. We're also today talking in your field about multi-messenger astronomy.
Indeed. So multi-messenger astronomy is, let's say, a way to open a new astronomy, including not only radiation, so photons in many energy bands, but also neutrinos and cosmic rays, so the protons, who actually are the parents of the neutrinos and the gamma rays, and also gravitational waves, as you heard before from Professor Barish.
And where do all these objects come from?
Well, the big accelerators, well, we know very well a small accelerator, which is our sun. Sometimes when you observe the sun with a filter, you see this immense coronal mass ejecta that can reach very high energy, 10 times the mass of the protons. And what happens instead in the galaxy is that we have objects like collapsed stars that produce a pulsar that is rotating still along the axis on which the star was rotating. And also we see, for instance, in different bands like X-rays or gamma rays or in infrared, particles accelerated. You see in the X-rays 2 jets emerging and going along the axis of rotation. These are really winds of particles. Then you see in the optical, for instance, the filaments that you see in this Crab nebula. It is called the supernova remnant. You see these filaments are electrons accelerated in the enormous magnetic field in this collapsed star, where after the collapse a shock formed. In the infrared, actually, is the red. You see the gas that is absorbing and re-emitting all this immense energy. And then we have the radio. So it was a bit mixed up, but the radio, which is also showing, in a way, accelerated particles. And for instance, the radio is the domain of SKO that we discussed before.
Among the many instruments that you have contributed building, I think that there is one in particular I want to mention is the IceCube Neutrino Observatory in Antarctica. We are going very soon to talk to our friends who are down under, not down under in Australia, but on the South Pole, on geographic South Pole. So this is an incredible laboratory in order to hunt for these particles.
Yes.
Physicists and astroparticle physicists are building crazy instruments. We saw a few before, but this is really amazing, built in the ice of the South Pole, and it's an ice cube because it's a cubic kilometer, right?
It's a cubic kilometer of instrumented ice at the South Pole between 1.5 and 2.5 kilometers. So it's 1 kilometer long, 1 kilometer large. And here we have computers, little computers that are built along these strings that bring the data to us and let us explore what happens in this dark environment, because we are down the ice, so it is dark, but it is extremely transparent. And you can see that the particles that travel, so also the neutrinos that travel across the strings, at some point may interact with the atoms of water and produce an immense cascade of other particles, or they can produce a muon that travels along the full detector.
Let's take a closer look of what is it made of, these ice cube detectors.
Yes, you see here, we are at the South Pole. We were installing a digital optical module, it is called. So you can see there is a photosensor that looks downward, and it is also shown in the scheme on the left. And then there is, let's say, the electronics that you saw on top of the photomultiplier, which is actually digitizing, so it is providing all the information of each of the photons of the light produced by the particles that are generated by the neutrinos in the ice. We have exactly the time at which each of the photons arrives, so it's a quantum sensor in a way.
And how many of these objects have you installed?
These are about 6,000.
6,000 of these.
Yeah.
How long did it take to build this thing in the ice?
So I arrived in Wisconsin in 2005. We installed in the season 2005-2006 the first string, and then after 5 years there was completion of the 86
You mentioned Wisconsin, but you installed in Antarctica, right?
No, because I traveled to Wisconsin to work closer to this detector, and then I traveled also to Antares.
To Antarctica.
South Pole.
This shows how you detect the passage of neutrinos.
Neutrinos are very penetrating. You already heard a lot about this, and I don't need to repeat. So once in a while, one neutrino will interact in the ice close to the instruments, or even in the rock below. And this interaction produces a charged particle. We cannot detect directly neutral particles because they don't produce any current, so we cannot really transmit any signal from them. But if they crash and they produce a charged particle like a muon, then they can also, traveling at a speed which is higher than the speed of light in the ice, they produce a cone of light. This is exactly the phenomenon that you see in the sonic boom of a plane. So when the plane surpasses the speed of sound, you see this cone that opens up if there is some powder close by. And this is the same thing when the particle travels at a speed that is larger than the speed of light in ice.
Can we mention some of the big results that you already obtained with the ice cube?
So one of the results that really was a game changer was the discovery for the first time of the astrophysical neutrinos, because we have a lot of neutrinos generated in the atmosphere, and so we saw a lot of them, but still we didn't see these big monsters, which actually we called after the Muppets, and we published the paper of their discovery in 2013. So what you see is a neutrino interaction in the core of the strings. Each of the digital optical modules is represented by a circle, and this circle has a color. So the red color to the rainbow colors of blue represents the timing at which the photons reach the detector.
I think we have an animation, right?
And also, you see, this is a muon instead, because it's a single particle that is producing showers along its track. But you can see that it is basically traveling across 1 kilometer of ice, and it is entering from the left, slightly upgoing up to the green part. The dimension of these optical modules that we represent are representing also the energy of these particles.
Yeah. Shall we go through very quickly through a few more discoveries.
Yes, this is actually one of the highest energy neutrinos we ever detected. It is not the highest energy, but one of the highest energy, and it is, again, a muon neutrino. But what is interesting is that we started a system of alerting other observatories. So we told to the other observatories in the world, we saw a huge monster of neutrino from this direction. What do you see in that direction? And some gamma-ray experiments responded, and they actually saw a big black hole embedded in a galaxy flaring towards us.
So we were talking about multi-messenger astronomy. This is multi-messenger astrophysics.
Yes,
and it's also very good. I think I would like now, I'm sure our friends from Antarctica are there listening to us, but before going to them, I just wanted to have a quick chat with Megan. Is your microphone working?
Let's see, is this working? Yes,
yeah?
There we go.
Okay, that's great. So, as I was introducing you before, you are better known as an ESA astronaut just selected from the latest astronaut selection, waiting to go to space, but in the meantime you're training, but you're also an industrial chemist, material engineer, and you're also head of commercialization of exploration at the UK Space Agency, so you do many things. My question to you is rather, now you're training for space. We're talking about Antarctica extreme conditions. You also spent 1 full year in Antarctica, not at the South Pole, but in Concordia. I've been to Concordia myself for 1 week. It was minus 55. Megan has been there, and it was a summer. You've been there for a whole year.
I was there
including
for a whole
winter.
Year. Yes, including winter. 2 summers and a winter, and then I went back again, actually, for another summer season. To get to Concordia, you basically go from the South Pole, head towards Australia, and go a bit uphill, and about halfway towards the Antarctic coast, you'll hit Concordia Station. It's at an altitude of about 3,200 meters. And the reason that they chose that location for Concordia is for a project called EPICA, European Project for Ice Coring in Antarctica. And this was an ice core that was 3,300 meters long approximately. And they took slices of this, correlated it with the depth, analyzed the gas bubbles inside each of those slices, and gave us the really famous graphic of the amount of carbon dioxide and methane that has been in the atmosphere for the past 800,000 years, and how much that has increased in the past 150.
So this is the proof of global warming.
Exactly. And
of human origin,
and this,
right?
Exactly, and this is the kind of the birth of Concordia Station.
Right.
But they also realized that there's a whole lot more interesting science that you can do in such a location. Astronomy is one of them because of the really low humidity in the atmosphere. So it's a
and
really
6 continuous months of darkness.
Yes.
Right?
Yeah, well, at Concordia, since we're not exactly at the South Pole, we get 100 days of darkness, and then there's a kind of crossover season.
So this is you at Concordia, I can see. I never dared taking the glasses off because I was afraid that my eyelid would stick to the crystallino of the eye. But you dare doing that.
Yeah, I mean, not very often. I think I usually tend to be completely covered.
So how was this, sort of long permanence in these extreme conditions in the south, in Antarctica? Was it preparation for space or?
Yeah, I mean, like I say, there's a lot of science that you do there, and that we kept adding on different types of science. The kind of thing I was doing there was atmospheric physics and meteorology. But then the European Space Agency thought, you know what, there are people down there already. This place is kind of like White Mars. So Concordia got the nickname White Mars because it's the closest thing we have on Earth to what it would be like to do a mission to Mars, in terms of the isolation, the extreme conditions, and the confinement as well. And also that fact of being at altitude, so you have low oxygen levels. So all these things mean that it's a really good, actually, an analog for space, but it's not an analog astronaut mission because we're actually there doing our work. It's just a kind of added bonus. And I mean, it's a really difficult environment to be in. Yeah, we got down to minus 104 degrees Celsius wind chill, and I was working outside every day, so I actually got to experience that. There are the 100 days of darkness, and these things tend to make you more irritable. They make you feel your emotions even more strongly, and so it's really important to get along with the other people in your team. And so there are various kinds of studies on us, on those of us who spend the time there, on our bodies, how our bodies react to those conditions, also psychologically, how we react to those conditions. We did a lot of questionnaires. They gave us strange things to eat and see how that affected us. They did tests on our cognition. One in particular actually was a really interesting one. They had us learn how to dock the Soyuz onto the International Space Station using a simulator that they actually brought down there to Concordia. And they taught us how to do it, gave us increasingly difficult exams during the summer season, and then they divided us into groups of either 1 month or 3 months, and they would have us do more and more difficult exams after 1 or 3 months. And this was to see like how our cognition changed over that amount of time. Because if you think about it, if you're going on a mission to Mars, you're going to learn how to land on Mars when you're back here on Earth. And what do you lose under those extreme conditions?
You become space dumb.
What's the kind of the training that you need to do while you're in space to keep that up?
Now we're going to travel straight to the geographic South Pole, the place that was discovered in 1911 by Roald Amundsen, the hero. The other hero in the middle is Teresa. That's the mark of the South Pole, right? And I think we are ready to talk to Ilya Bodo and Joe Baines-Holm of the Ice Cube Neutrino Observatory down in Antarctica on the geographic South Pole. Welcome to CERN, Ilya and Joe Baines. How are you?
We're very good, thank you. Thank you for having us.
Okay, it's great that we hear you loud and clear. So we were talking, Megan was talking about the extreme conditions at Concordia. Is it worse there at the geographic South Pole? You're around 1,000 miles further down from compared to Concordia, right?
Yeah, so generally speaking, I'm not sure exactly what the weather's like in Concordia, but it's a bit less windy here than it is at some of the other bases.
It's slightly warmer here. Concordia regularly sees a little bit lower temperatures than what we see, but it's overall pretty similar.
Yeah, so...
What is it like right now? What is it like right now? What are you experiencing?
So we've just had the wind die down. It was about 45 kilometers an hour yesterday, and that's actually meant the weather's been a little bit warmer, so more like minus 55 Celsius ambient.
Mm-hmm.
Minus 55.
Yeah.
So yeah, it's pretty warm for winter because it's winter. With summertime here, but it's winter your side. And what time is it for you? Because all the time zones of the planet end up there, so you can choose the time you're operating at, right?
Yeah. So we use New Zealand time here. So at the moment, it's about 25 minutes to 6 in the morning.
Oh, sorry for waking you up so early. Thank you for staying up for us. Thank you very much. Can you tell us more about this extreme environment there? What else is different compared to another place, any other place on the planet? We have a clip that shows how you experience the sun around Antarctica. So that's a time lapse of the sun.
Yeah.
Actually, courtesy of Marc Jacquard of the Ice Cube Neutrino Observatory, National Science Foundation. We see the sun that is basically going around. It's the Earth that moves, obviously, but...
Yeah, that's it.
So how do you experience that thing?
Yeah, so it's very different, obviously. So, you know, it takes a lot of getting used to being somewhere where there is 24 hours of sunlight. And then once the sun goes below the horizon and it starts approaching darkness, you then have to get used to 24 hours of darkness as well. Each has its own unique individual challenges. Other things that are very difficult here is the altitude. So the pressure altitude fluctuates quite a lot, but it's often around 3,300 meters. So it's quite low pressure. And it's also similar to Concordia, you know, we're on an ice desert essentially, so it's incredibly dry, as well as being very cold. So the sun went down about 4 months ago for us now, and we've got about 2 months before it pops up at the horizon.
And what do you do there? What is your typical day like?
So we're actually very fortunate that IceCube is built in such a way that it's actually quite stable and generally requires not much intervention on our part. But generally what we do here is we run like special operations. So that would be testing new versions of the software. Like we're about to do our 2025 run start. So we just did a calibration about a month ago to calibrate all the DOMs in the ice. So we'll be implementing that calibration pretty soon. Some of the other stuff we do is we're basically on call 24/7 for any detector problems because we're the only two people on station who know how to operate the detector and know anything about it. So that could be if the run crashes because of DOMs that had like a little problem that just need to be restarted, or it could be hardware problems because we have pretty much like the largest data center in Antarctica, I believe. So we might have problems with the servers, we might have problems with the custom IceCube hardware, and we're on call to go fix or replace any parts of that that might break during the winter.
How is
yeah, so where we are now.
How is the detector behaving right now?
Oh, it's
really
been
good.
It's been good. We haven't we had like one drop DOM out of 5,000 in the past few days, and that's about it. So
yeah,
it generally requires just very little intervention, and it generally works very, very well. I believe the original design was for about a 1% failure rate of the in-ice DOMs per year, and we've seen about 2% failure rate or 1% failure rate over the past 15 years. So that's just really a testament to how well the detector was designed and manufactured.
Do you ever have to go outside
and,
for work? We have some
yeah,
images.
We do. So
can we see the next images? I'm asking. Yeah, right. So this is a night. We are seeing how it looks like a night there. Do you ever have to go to work outside?
Yeah, definitely. So as I mentioned, if there's any problems with like the server hardware or the data center hardware, we have to go out to the ICL or IceCube lab, which is about 1 kilometer away from the station. So that would be outside. And we also kind of have to like maintain the building a little bit. So as you see in the video, we have to do like shoveling just to keep the snow off. You know, the snow is generally pretty good there, but after it being really windy, so probably in a few days it'll be like covered in snow and we'll have to go shovel out the stairs and stuff like that.
Yeah, and we do have a few parts of the detector that are on the surface as well. So occasionally, especially over summer, we'll have to go and do some maintenance on those. We have some Air Cherenkov telescopes that they use for vetoing or like classifying certain events in the detector as being related to cosmic ray showers hitting the atmosphere. So yeah, there's a lot of different parts that we're responsible for. And yeah, it's certainly an interesting job.
It's an interesting job, yes, it's pretty tough. Thank you very much to Ilya, Bodo, and Joe Bainsholm of the IceCube Neutrino Observatory in Antarctica. I let you go back to sleep. I guess it's 6 in the morning. Thanks a lot for talking to us.
Thank you so
and
much.
good luck with the rest of your stay and the rest of the winter.
Yep.
So we're a little bit behind schedule.
Thank you so much for having us.
Yeah.
Thank you. So the last round of questions, before we get a couple of questions from the audience, was about, so we've seen how many efforts you're putting into building and operating these objects, not to speak about how difficult it is to extract the data and interpret and analyze, and you develop incredible new software, machine learning models, a lot of stuff you put into the interpretation of the data. But this is to satisfy human curiosity, solving scientific mysteries, but this also brings about a lot of new technologies and new applications. So to each of you, one comment on what these developments bring to humankind. We have to go back. This is right? So Patrizia.
Okay, fine. New technology due to the development of space economy. The heart of the matter is to lower the price of launching 1 kilogram, let's say, in orbit. The classical price was about $30,000 per kilos. And now the new generation of commercial launcher brought it down by a factor more or less of 10. We are around 3,000 per kilos, $3,000 per kilos, which is already a good achievement, but more should come thanks to the new generation of launcher. Especially the one astronomers are looking at is Starship, since it does have a very big space, 9-meter diameter, so it can bring up an unbelievable number of tons in orbit. So in principle, it would be easy to send big instruments in orbit. However, all good things come with drawbacks. And the growth of space economy is also producing very undesirable effects on the quality of our sky. Since we put in orbit, the commercial operators put in orbit thousands of satellites per year, and those satellites, once they are in orbit, they are stupid enough to reflect the light of our sun. When here it's already dark after the sun went down, in orbit, the satellites are still hit by the sunlight and they reflect. And here you see what's happened. This is a time lapse of 1 hour in Montana.
It doesn't start as a time lapse.
And it means you can search for a bit of sky which was not crossed by a satellite during 1 hour.
You really have to look for one. Okay, so this is the drawback of the
drawback
of the development of space economy.
Indeed, and astronomers are fighting it. Requesting satellites not to be so reflective, etc. But when you look deep into the problem, you discover that satellites have an ecological impact.
Yeah, I know that you are an advocate of give us back the starry night.
Yes.
And you do a personal fight against this light pollution. So thank you for mentioning that. Going back to the technological developments regarding the particle physics, many people know the World Wide Web was born here. Your favorite, Clara, which ones are? Very,
so we
very
can
quickly.
we can jump to the next picture. So
okay.
As you said before, I mean, many of us do this because we want to further human knowledge and we want to find out what our universe is made of. But one of my favorite things about particle physics is that there's a lot of spin-off technology that comes from our research, because we're really pushing the boundaries of technology that is possible to achieve. So we have to design better magnets and other technology, better accelerators, of course. And so, for example, whilst investigating potential future colliders to be built at CERN, then medical technology, better medical treatment comes out of this. So this is a picture of some development for a linear collider, and from this you can do something called flash therapy. And flash therapy, so it's still on the previous picture.
Oh, sorry.
It's okay. But flash therapy is, it's not a new concept in medical science, but it's newly reinvestigated, that if you irradiate a tumor with a lot of radiation, and specifically using electrons, then it used to be thought that the healthy tissue would also be damaged, but the understanding in medical research is that the cancerous tumors will be significantly damaged by this really high radiation dose, and actually the healthy tissue can recover a lot more quickly than was expected.
If it's done fast.
If it's done very fast, so a lot of electrons very fast, targeted on, for example, a cancerous tumor, and this comes from accelerator technology. And then there's also proton therapy that requires a very specific energy of protons using accelerators to deposit energy into a cancerous tumor.
That was for therapy.
Yeah.
This is for diagnostics.
And then this is for diagnostics. So using detector technology from CERN, you can do color X-rays. So X-rays are a form of light, so you can have different wavelengths of X-rays. And by having very sophisticated detectors, which is what we are known for, not only at CERN, but in particle physics around the world, you can then detect these different wavelengths of the X-rays and associate them with different colors, and the different tissues or bone of the body, in this case it's a wrist, interact with those different wavelengths.
And this is already happening, actually.
And this is already happening, so you can get color X-rays.
Thank you, Clara. Last but not least, Teresa, your favorite. Maybe this is one of the most recent spin-offs from astrophysics detector development.
This is a recent project that, so we in my group, we work a lot on building cameras with new silicon photosensors for telescopes, both in space and on ground. And we also associate to these photosensors that are sensitive to single photons, electronics. And this is a new ASIC, so an integrated piece of electronics, very, very small, that can process the data of these photosensors. And in the next future, we want to understand how these sensors can work in association with a further processor that is actually based on neuromorphic technology. So the neuromorphic technology is basically imitating what our brain does. Our brain works with spikes of current, and it is actually the processor that spends less energy, and it is the fastest also all over the world, compared even to quantum and the most modern silicon computers. So we will try to match the standard electronics, let's say, in silicon with these new processors.
And these are just a few examples of the continuous innovation that comes from the developments in all these beautiful disciplines, particle physics and particle physics. So I think I'm afraid there is no time for questions right now. We have to go along with the program, but we will answer the many questions received online. We will answer online. I just would like to end this session with one quote that was chosen by Teresa. So the real voyage of discovery is not looking for new landscapes, but having new eyes. And I think apart from all the technological spin-offs, which obviously come when you are developing new things that would not be developed otherwise, the real advancement here is looking at the world with new eyes. And with this message, I would like to thank Megan Christian, Patrizia Caraveo, Teresa Montarulli, and Clara Nellis. And I give the floor very gladly to Chloé Carrière, aka Galactic Chloé. Thank you very much.
Thank you.
Thank you. Good luck with your...
Merci. Donc je vais passer maintenant en français. Notre session va regarder aussi vers le ciel. On va aller regarder aux origines de l'univers, la physique des particules, l'astrophysique, même la cosmologie. Et maintenant, si on regardait aussi vers d'autres mondes. Cette session nous invite à regarder des planètes autour d'autres étoiles, ce qu'on appelle les exoplanètes. Donc mon nom est Galactique Chloé, je suis ingénieure aérospatiale de formation et vulgarisatrice scientifique. Et j'ai le privilège d'avoir sur scène une petite, même je dirais une grande célébrité locale quand on parle d'exoplanètes. Cet homme a découvert en 1995, avec son collègue Didier Queloz, la première exoplanète autour d'une étoile similaire à notre Soleil. Ça lui a valu le prix Nobel de physique en 2019 et ça a ouvert tout un champ de recherche que l'on va explorer ensemble sur les 30 prochaines minutes. Mesdames et messieurs, s'il vous plaît, accueillez sur scène Michel Mayor. Bienvenue Michel, bienvenue. Est-ce qu'on pourrait... Ah, c'est toi qui as le clicker, magnifique.
Voilà.
Parfait. Merci d'être avec nous. Donc on va venir tout d'abord parler de cette découverte qui t'a valu le prix Nobel de physique en 2019. La découverte de cette exoplanète. Est-ce que tu peux déjà nous expliquer comment vous l'avez vu par la découverte?
Oui, peut-être d'abord, peut-être on peut dire c'est l'année de l'anniversaire, puisque toute cette histoire a été effectuée il y a 30 ans. Donc c'est le 30e anniversaire du démarrage de ce chapitre nouveau de l'astrophysique, qui est cet énorme domaine qui est la recherche des exoplanètes. Alors ça commence avec la construction d'un instrument et une idée qui était déjà dans l'air, c'est que s'il y a une étoile ici, la planète tourne autour, mais le rapport de luminosité est tellement énorme qu'on ne peut pas observer la planète facilement. Par contre, si on mesure la vitesse de l'étoile, eh bien quand la planète tourne, l'étoile tourne aussi autour du centre de gravité. Et donc, l'idée, c'est de construire un instrument qui permet de mesurer les petites variations de vitesse de l'étoile. Évidemment, comme l'étoile est beaucoup plus massive que la planète, eh bien, ces changements de vitesse de l'étoile sont très, très faibles. Juste donner un ordre de grandeur. Jupiter fait changer la vitesse du Soleil environ à 10 mètres par seconde pendant 14 ans, sur 14 dizaines d'années. Par contre, la Terre ne fait bouger le Soleil que à 10 cm par seconde. Imaginez, si vous voulez vous intéresser à détecter des terres, vous devez mesurer des changements de vitesse d'une étoile au niveau de 10 cm par seconde sur une année. Voilà, ça c'est la difficulté technique. Et alors peut-être ici, juste comment est-ce qu'on fait? Eh bien, on utilise l'effet Doppler. Comment dire, on construit un instrument qui sépare les longueurs d'onde, et puis l'effet Doppler va faire que quand l'étoile s'approche de vous ou s'éloigne, il y a un changement des couleurs émises par l'étoile, et puis ceci est aidé par le fait que, je vais te demander le pointeur, ceci est aidé par le fait que, j'arrive pas à le... Bon, il n'est pas là, peu importe. Comment dire, on voit que le spectre de l'étoile est saturé de transitions atomiques, des milliers de transitions, ces rayons noirs. Ce n'est pas un arc-en-ciel continu, mais il y a toutes ces transitions. Et donc l'idée est de construire un instrument qui permet de mesurer ces oscillations, ces changements. Et on a construit un instrument avec nos collègues français, voici plus de 30 ans, et puis on l'a mis en service. On avait un échantillon, on n'avait aucun a priori. On avait 142 étoiles comme le Soleil, simples, on les avait choisies qu'elles ne soient pas doubles, et puis on a commencé à mesurer, une nuit, une autre nuit, etc. Et après un certain temps, on a vu que la plupart des étoiles avaient une vitesse constante, et puis il y en avait tout d'un coup quelques-unes qui avaient des variations de vitesse. Et là, voilà. Et tout d'un coup, la surprise, certaines ont des variations qui ne sont pas périodiques. Bon, c'est dû au champ magnétique de l'étoile. Et puis tout d'un coup, il y en a une qui a une variation périodique. On est content, mais il y a un problème énorme. La théorie nous disait que pour former une planète comme Jupiter, il fallait agglomérer des grains de glace à une grande distance de l'étoile. Et donc, il fallait que la période orbitale soit plus grande qu'environ 10 ans. Et l'objet qu'on trouve ici a une période orbitale de seulement 4,2 jours. Donc, ce Jupiter qu'on découvre, la masse était à peu près celle de Jupiter, eh bien, tournait autour de l'étoile en seulement 4 jours. Complètement. Un désaccord avec la théorie d'un facteur 1000. Et quand vous avez un désaccord d'un facteur 1000, eh bien, le minimum, c'est de se poser des questions, à savoir, est-ce que vraiment on a une planète? Et donc, c'est la raison pourquoi on a décidé de ne pas en parler pendant une année, de répéter les mesures une année après, pour éliminer des théories potentielles, d'autres hypothèses qui pouvaient expliquer ce phénomène. Et c'est seulement l'année d'après qu'on a été convaincu que c'était réellement une planète. Et très vite, l'expérience, on a compris quel était le phénomène qui se cachait là derrière, à savoir l'agglomération des glaces forme réellement la planète très loin, mais après l'interaction avec le disque de gaz et de particules va faire que l'orbite va se rapprocher de l'étoile. Et actuellement, c'est un phénomène complètement intégré dans toutes les recherches et la théorie de la formation des systèmes planétaires.
Mais si on parlait justement un peu plus de cette exoplanète, donc vous l'avez appelée 51 Pégasi B, donc j'imagine que ça vous l'avez choisi par rapport au système où elle était, sa position, etc.
Oui, on avait totalement la liberté de lui donner le nom qu'on voulait. Simplement, il existe des catalogues, des listes d'étoiles et tout, et c'était une manière de faire, c'était de se rattacher à ces catalogues. Alors nous, dans nos mesures, on utilisait un grand numéro, c'est pas très sympathique à utiliser en parlant, et on a trouvé au dernier moment, juste avant de publier les résultats, qu'il y avait un vieil atlas de 2-3 siècles qui mentionnait cette étoile, et elle s'appelait 51 Pégase. Et donc, c'était assez sympathique de reprendre cette vieille nomenclature, et puis on mettait un petit B à côté pour dire que ce n'est pas l'étoile, mais c'est le compagnon. Et d'où le fait 51 Pégasi B, c'était simplement issu de l'histoire de la nomenclature. Et ici, vous avez des comparaisons de différentes tailles. Alors bon, c'est peut-être pas très important, mais disons, on voit que la planète 51 Pégase B, elle a à peu près la moitié de la masse de Jupiter, mais elle est en fait un peu plus grande. Elle est un peu plus, sa dimension est un peu plus grande que celle de notre Jupiter, et l'étoile elle-même aussi est un petit peu plus grande que le Soleil, mais avec une masse extrêmement similaire à celle de notre Soleil. Depuis lors, on avait beaucoup d'études sur ces étoiles, sur ces planètes. Peut-être l'image suivante, pour moi, est beaucoup plus parlante de ce qui s'est passé au cours des 30 dernières années. En fait, bon, on a découvert 51 Pégase, mais après, on a continué, évidemment. On en a découvert d'autres avec la technique des vitesses radiales, donc cette technique où on mesure les changements de vitesse des étoiles. Et ça, dans ce diagramme, c'est les points rouges ici. Ce diagramme, on voit, c'est la masse des planètes qui ont été découvertes en fonction de leur distance à l'étoile. Alors, 1, c'est la distance Terre-Soleil, donc comme unité, et c'est une échelle logarithmique, donc il y a 10 fois plus petit, donc ce serait 1 mois à peu près, ou 100 fois plus petit, c'est quelques jours. C'est 3 jours, 3 jours et demi. Et regardez le nombre de planètes qu'on trouve ici qui ont des orbites seulement de quelques heures. Ça, c'était complètement inattendu, voici 30 ans, qu'il y ait une telle diversité. Alors, on voit d'une part qu'il y a des planètes qui ont été détectées qui sont plus petites que la masse de la Terre, mais on en voit qui sont 10 fois, 100 fois, voire 1000 fois la masse de la Terre. Donc, on voit ça peuple complètement l'espace des masses séparation. Et ça, c'était complètement inattendu que la diversité de ce qu'on trouve dans l'univers soit aussi riche que ceci. Alors évidemment, les conséquences sont énormes, puisque vous avez, par exemple, imaginez que vous ayez Neptune ou Uranus, des planètes qui sont de glace. Imaginez qu'elles subissent le même phénomène de migration orbitale comme ça. Eh bien, quand elles se rapprochent de l'étoile, cette énorme boule de glace va se mettre à fondre, et puis vous aurez une planète dite océan. Donc on doit anticiper qu'il y a des planètes qui sont des très grosses boules d'eau, comme ça. Imaginez qu'une planète rocheuse se rapproche trop près, et ça on le sait, de certaines étoiles chaudes, la température à la surface est telle que les silicates, les roches, vont fondre. Donc on a aussi la formation de planètes qui sont des boules de lave. Voilà. Et il y a une diversité aussi bien des orbites que des compositions que l'on voit ici. Puis après, il y a eu des techniques qui sont venues, d'autres techniques. Alors vous avez celle qui est verte, vert-bleu. Vous voyez, il y a énormément d'objets à courte période qui ont été découverts, en particulier par les satellites, les mesures spatiales. Et l'idée est d'une simplicité incroyable. On y reviendra parce que c'est une technique fabuleuse pour le futur. Eh bien, quand on a ces planètes qui sont très, très proches les unes de l'étoile elle-même, eh bien, il arrive que la planète va passer devant l'étoile. Donc, on pourrait dire d'une manière abusive un peu une éclipse. On utilise dans le cas particulier plutôt le terme de transit planétaire. Donc, imaginez que vous avez un instrument, vous mesurez l'éclat d'une étoile, vous ne voyez pas la planète. mais de temps en temps, la luminosité de l'étoile va diminuer périodiquement, comme ça. Et cette technique a été utilisée par différents instruments satellites, par exemple Corot, un petit satellite, mais surtout par le satellite Kepler.
Dont on parle justement juste après,
on y reviendra après, voilà. Oui. Qui, comment dire, un satellite de l'ordre du mètre. Alors l'idée est là de nouveau d'une simplicité énorme. Tu me donnerais peut-être juste le micro, oui. Alors, ici il y a la Terre, le satellite est là. Vous choisissez un coin du ciel où il y a 100 000 étoiles, voire plus que 100 000 étoiles, et vous faites une photo. Mais après, vous faites tout le temps des photos, des photos, des photos. Toutes les demi-heures, vous faites une photo du ciel comme ça, et vous, sans changer de direction, vous accumulez des photos. Et des photos, comment dire, après quelques années, qu'est-ce que vous allez avoir? Vous aurez la luminosité de 100 000 étoiles en fonction du temps. Vous analysez ça dans l'ordinateur et vous voyez qu'il y en a des milliers qui présentent des transits planétaires. En fait, ça nous montre que c'est un phénomène extraordinairement général dans l'univers. Il y a des systèmes multiplanétaires. Pourquoi? Parce que si vous regardez ce diagramme, vous avez par exemple, prenons les points rouges qu'il y a dans ce diagramme, eh bien, c'est des systèmes qui n'ont pas un transit, mais vous avez 6 différentes planètes qui passent devant en même temps. Ça nous dit quoi? Que le plan orbital est comme dans le système solaire, il est extrêmement mince, et donc il y a 6 planètes qui passent entre votre œil et l'étoile. Et donc, on voit que les systèmes comme le système solaire sont incroyablement fréquents. Par contre, on a vu le diagramme précédent, eh bien, leur géométrie est extraordinairement différente d'une autre. Mais ça montre que des planètes, il y en a partout. Si on fait un peu de statistiques et tout, aussi bien à partir des données de vitesse radiale que des transits, on arrive, en gros, la conclusion essentielle, en gros, toutes les étoiles ont des systèmes planétaires. Les systèmes planétaires sont des sous-produits obligatoires de la formation des étoiles elles-mêmes. Quand vous avez un nuage de gaz énorme, la nébuleuse d'Orion par exemple, qui s'effondre sous le poids de la gravité, eh bien vous formez des milliers d'étoiles. Mais il y a de la turbulence dans ce gaz. Eh bien, vous aurez toujours un problème d'excès de moment angulaire, de rotation, comme ça, qui va faire que toute la matière ne va pas pouvoir se rassembler pour former une nouvelle planète, une nouvelle étoile. Il restera toujours un disque de gaz et de poussière qui tourne beaucoup trop vite autour, et c'est le disque qui va permettre la formation des systèmes planétaires. Juste une petite remarque numérique, le 99% du moment angulaire du système solaire, c'est les planètes. Elles sont tout petites, mais l'essentiel du moment angulaire est dans les systèmes planétaires et non pas dans la rotation du Soleil, qui est pourtant beaucoup plus massif, mais évidemment, il est rassemblé. Voilà. Donc ça, c'est une image historique qui montre l'énorme richesse du ciel en système planétaire.
Parce qu'il y a 30 ans, vous découvriez la première exoplanète autour d'une étoile comme le Soleil, et maintenant, on en a découvert combien?
Alors actuellement, oui, c'est une histoire, une richesse incroyable, puisqu'actuellement, on a de l'ordre de 6000 planètes qui ont été découvertes. Donc on peut se dire aussi, quelle est la raison de continuer à les chercher? Mais parce qu'il y a toujours des choses à apprendre, des nouvelles, des objets incroyables, on a toujours des surprises phénoménales, et surtout, la quête, c'est de remplir ce diagramme, la partie où il y a peu de planètes de ce côté-là, disons vers 300 jours, et puis une fois la masse du Soleil, de la Terre. Pourquoi? Parce que c'est le domaine des planètes potentiellement habitables.
Et en parlant de ça, donc, tu le disais, vous aviez utilisé la vitesse radiale pour découvrir l'exoplanète. Maintenant, tu nous as bien expliqué la méthode de transit, on a le diagramme qui apparaît. Pourquoi est-ce que vous n'avez pas pu utiliser la méthode de transit de base? Alors, on a essayé tout de suite. À chaque fois qu'on trouvait des planètes, on essayait, mais il faut évidemment que le plan orbital soit favorable pour que ça se passe. Et c'est en fait seulement 4 ans après la découverte de la première planète, eh bien, on en avait découvert une nouvelle qui avait une période de 3,5 jours. Et puis là, de nouveau, on a essayé.
Et avec un petit télescope, parce que c'est une étoile brillante, eh bien, on a découvert le premier transit en 1999. Et cette découverte, elle est riche de potentiel pour le futur qui est exceptionnel. Alors, s'il y a un petit diagramme ici, vous avez d'une part le disque noir, c'est la planète qui passe devant l'étoile, qui est en jaune. Et puis, quand on fait, évidemment, plus la planète est grosse, plus la baisse de luminosité sera significative. Donc, c'est une manière de mesurer la dimension de la planète. OK, pas mal, on ne la voit pas, mais on peut mesurer sa taille. Et puis, quand elle passe derrière, vous voyez, on voit elle est rouge, elle est en train de se cacher, la lumière infrarouge baisse. Et ça, c'est directement une mesure de la température de la planète. Voilà, par exemple. Mais ce qui est le plus fabuleux, c'est le petit anneau bleu que l'on voit ici, qui est le domaine qui va faire parler la presse au cours des prochaines années. C'est un domaine prioritaire de la recherche actuellement. Pourquoi? Parce que ce disque bleu que l'on voit ici, ça symbolise l'atmosphère de la planète. L'atmosphère de la planète va filtrer un petit peu de la lumière de l'étoile. Et puis, quand elle est derrière, ben évidemment, elle ne filtre rien. Donc, si on compare le spectre de l'étoile derrière ou devant, il y a une toute petite différence. Mais quand je dis tout petite, l'atmosphère d'une planète, c'est vraiment extrêmement peu. Comme ça. Et donc, le problème, simplement, le filtre va nous dire quelque chose sur la composition chimique de la planète. Pas de l'étoile, de la planète. Et ça, vous pouvez le comprendre très bien, parce que prenez par exemple la Terre. Disons, elle a 12 000 km de diamètre, OK, dans le visible, c'est la dimension de la roche. Mais imaginez que vous fassiez la même mesure dans le domaine de l'ozone. Vous avez, l'ozone est bloqué à 40 km plus haut. Donc, vu dans le domaine de l'ozone, la Terre semble 40 km plus grande de chaque côté, 80 des deux côtés. Donc, pour reprendre, elle aurait 12 080 km. Et donc, simplement en mesurant la profondeur de l'éclipse du transit, eh bien, vous avez de l'information sur l'opacité en fonction de la longueur d'onde. Eh bien, ça vous permet de faire l'analyse chimique des atmosphères planétaires. Et pourquoi c'est extraordinairement riche de promesses pour le futur? Parce que vous allez peut-être rêver de détecter ce qu'on appelle des biomarqueurs. Des biomarqueurs, c'est des indicateurs chimiques que la vie est en train d'agir dans cette planète. Alors, l'exemple le plus frappant qu'on mentionne toujours, c'est l'énorme quantité d'oxygène qui existe dans l'atmosphère de la Terre, 20% d'oxygène dans l'atmosphère, alors que l'oxygène est un corps qui n'a qu'une envie, c'est se lier avec les roches et disparaître. Donc les 20% d'oxygène sont attribués essentiellement à la formation due à des phénomènes liés à la vie. Donc ça a été proposé il y a 40 ans, je crois par Carl Sagan. Mais on peut rêver de détecter d'autres transitions atomiques qui vont nous créer une situation où on se dit tout ça nous parle en faveur que la vie s'est développée sur cet objet-là. Alors ça, pour ça, évidemment, plus l'atmosphère est petite, et une planète comme la Terre, son atmosphère, si vous avez vu des photos faites par des satellites, c'est une petite bande bleue à la surface de la Terre, c'est un tout petit filtre qui va se faire. Donc, pour pouvoir arriver à faire ça, eh bien, il faudra pouvoir, avoir beaucoup de photons, donc un grand télescope. Mais peut-être juste avant, vous avez ici, sur ce diagramme, ce que j'ai expliqué avant, à savoir quand vous changez de couleur, la profondeur de l'éclipse du transit, eh bien, change d'après le type de l'opacité dans lequel vous allez observer. Et donc, ceci, ce n'est pas la seule justification, évidemment, mais l'image suivante, eh bien, ça justifie en particulier l'énorme espoir qu'on a en utilisant le 39 mètres, le télescope, les ELT, qui se construit actuellement au Chili, un télescope qui est plus grand que cette salle. Imaginez, le miroir principal est plus grand que cette salle, et puis il va être mis en service d'ici 3-4 ans. Eh bien, cet instrument-là va être un collecteur de photons absolument gigantesque, et éventuellement permettra de voir cette toute petite différence quand vous soustrayez, je dirais, 1 milliard moins 999 millions, etc. C'est une toute petite différence qui vous dit la quantité qui est bloquée dans un certain élément chimique. Donc, évidemment, cet instrument, il ne va pas faire que les planètes, il va faire beaucoup d'autres choses, mais en particulier, il va contribuer à cette question qui est quand même assez sympathique, qui est est-ce qu'il existe la vie ailleurs dans l'univers? Et qu'on va dire, une manière de répondre, c'est l'analyse chimique des atmosphères planétaires, puisque il faut quand même le rappeler, hein, même si on découvre de la vie dans une atmosphère d'une planète très proche de chez nous, une voisine, il n'est pas question d'y aller, les distances sont beaucoup trop considérables. Donc il n'est pas question, même que vous avez beaucoup de films ou de science-fiction qui parlent de voyages interplanétaires, il n'est pas question d'aller sur une exoplanète, même si elle est parfaitement habitable.
Donc là, on regarde une image de l'Extremely Large Telescope qui se trouve au Chili, à l'ESO. D'ailleurs, je crois que tu l'as vu en construction,
oui.
Il me semble. Et d'ailleurs, je crois que juste après, on a peut-être une vidéo, justement, faite directement là-bas par l'équipe, par Paola, qui allait sur place pour la construction. 39 mètres de diamètre, le miroir.
C'est absolument. Juste pour situer, le télescope mythique de ma jeunesse, c'était le Palomar, qui avait un miroir de 5 mètres. Et à l'époque, on disait qu'on ne pourrait pas en faire des plus grands. Et maintenant, il y a le Keck ou autre, c'est 10 mètres de diamètre. Et là, maintenant, on parle de 39 mètres. C'est un saut absolument fantastique qui est réalisé actuellement. Alors ça, ici, on a par anal, les télescopes, 4 télescopes de 8 mètres. Et peut-être qu'on peut le dire, actuellement, on les utilise pour chercher les planètes. Et on a un instrument qui permet de connecter ces 4 télescopes à un seul spectrographe, déjà pour avoir suffisamment de photons.
Comparable au Colisée, on entendait même dans la table ronde avant, la taille de l'Extremely Large Telescope.
Il est comparable.
Au Colisée.
Oui, je n'aurais pas eu l'idée de faire cette comparaison, mais c'est peut-être quelqu'un qui est italien.
Pour dire à quel point c'est grand.
Oui, c'est absolument fabuleux. Alors, on est d'accord, hein, ce n'est pas un monobloc. C'est des centaines d'hexagones qui sont mis d'une manière astucieuse. Alors, quand même, pour apprécier cette qualité incroyable de ce qui se cache là derrière, vous devez réaliser une surface qui est partout proche d'une surface théorique à moins d'une fraction, disons, 20e de micron. Donc 20 millièmes de fois plus petit qu'un millimètre sur cette surface de 39 mètres. Voilà, ça c'est remarquable. Et puis quand même, n'oublions pas un petit télescope dans l'espace de 6,50 mètres. Évidemment, il a l'avantage d'être au-dessus de l'atmosphère terrestre, le James Webb Telescope, qui est en train de révéler des choses absolument fabuleuses dans le domaine des exoplanètes, justement.
Et justement, on parle d'observation terrestre avec le LT, et puis là, donc, spatial avec le James Webb. Est-ce qu'on peut s'attendre à des meilleurs résultats pour le LT de par son diamètre par rapport au James Webb, ou c'est pas comparable?
Je crois que c'est complémentaire. Je crois en fait, on croit mettre des fois en compétition le spatial au sol. Bon, le sol, on peut mettre des très gros télescopes, on peut changer les instruments facilement, plus facilement que dans l'espace. Par ailleurs, les domaines de recherche sont complémentaires. Prenez le James Webb, lui, il travaille dans l'infrarouge, qu'on ne peut pas mesurer depuis le sol. Déjà, rien que pour ça, il a accès à un domaine qu'on ne peut pas faire depuis le sol.
J'en profite aussi pour dire que si vous voulez aussi poser vos questions, il y a un QR code qui va apparaître sur le côté. Vous pouvez déjà dire, on aura quelques minutes à la fin de cette discussion pour répondre à vos questions. Donc, quand on regarde le James Webb, le LT, il y a aussi d'autres missions qui sont en préparation pour découvrir les exoplanètes. On a aussi Khéops, qui est un télescope qui est quand même assez récent, qui vient de par chez nous.
Oui, pour regarder par exemple ce diagramme qu'on a vu avant, donc la masse des planètes versus leur distance. Alors on voit cette région où on voit Neptune, Uranus, la Terre. On voit actuellement c'est des domaines qui sont difficiles d'accès avec les instruments qu'on a. Mais regardez les missions. Alors d'une part, attendez, l'année prochaine, Gaïa, c'est un satellite européen qui détecte les mouvements des planètes sur le plan du ciel, et on peut s'attendre à ce qu'il y ait peut-être plusieurs milliers de planètes qui pourront être détectées, mais c'est plutôt des planètes massives qui seront là-bas. Et puis, il y a toutes ces planètes détectées par le satellite Roman qui sont potentiellement détectées des tout petites planètes dans cette zone-là, mais par une technique qui ne va pas permettre de les répéter, ces mesures. C'est des transits, pas des transits, des méthodes liées aux lentilles gravitationnelles qui vont faire qu'on fait une mesure et malheureusement on la détecte. Pour les mesures statistiques, c'est extrêmement important. Mais évidemment, il ne faut pas croire qu'on va avoir des mesures très précises de toutes ces planètes qui vont être détectées. Et vous voyez ici ces 4 images où on a 4 différents satellites qui sont... Gaïa va donner les résultats, ils voient déjà, mais les autres satellites sont toutes des projections pour le futur. Plateau va pouvoir faire des recherches de transit dans les étoiles brillantes, et même avec une précision extrême, et même mesurer les vibrations de l'atmosphère, etc. Donc, beaucoup, la spectroscopie Ariel, donc on ne manque pas de missions, et on peut rêver encore. Avant, on a entendu des missions incroyables qui sont comme ça. On aimerait, par exemple, mesurer, détecter des planètes, comme la Terre, dans la zone habitable. C'est-à-dire, qu'est-ce que ça veut dire? Des planètes qui sont ni trop proches, trop chaudes, ni trop loin, trop froides, dans cette zone où la chimie de la vie pourrait être active. Apparemment, ça paraît impossible. Et pourtant, vous avez par exemple John Matter, qui est prix Nobel de cosmologie il y a 20 ans à peu près, a proposé un concept où vous construisez un écran de l'ordre de 100 mètres de diamètre, avec quelques propriétés particulières de forme, et puis un satellite qui se met à 170 km. Et puis, alors admettons, ça c'est la planète. Alors, on regarde comme ça, eh bien, vous cachez l'étoile avec cet écran, et vous avez juste la possibilité de voir les planètes autour. Les calculs ont été faits, c'est tout à fait réaliste. On peut même faire l'analyse de la composition chimique de la planète. Alors voilà, c'est compliqué, c'est difficile, mais c'est tout à fait possible de faire l'image d'une planète dans la zone habitable d'une étoile comme le Soleil, et qui plus est encore analyser leur composition chimique, et ce sera une combinaison entre ce type de satellite et l'ELT en 39 mètres pour encore combiner les données des deux instruments. Donc voilà, le futur, en fait, on n'est qu'au début de cette histoire.
Est-ce qu'il y a une mission en particulier ou un télescope que tu attends avec impatience?
Bon, je crois que les LT, c'est tellement incroyable, un télescope de 39 mètres. Mais quand même, juste pour donner une idée, le James Webb Telescope, c'est un télescope qui peut faire tout en astronomie. Il n'est pas dédié à un domaine particulier. Mais déjà actuellement, le tiers du temps est donné aux planètes extrasolaires. Donc ça reste un chapitre absolument incroyable qui a émergé il y a 30 ans en astrophysique. Il y a tellement à découvrir, c'est tellement nouveau. Voilà, puis potentiellement, il y a ce rêve, est-ce qu'il existe d'autres mondes dans l'univers?
La fameuse question. Pour le moment, on n'a pas la réponse, ça reste encore de l'ordre de l'opinion de tout à chacun.
Et les opinions a priori du genre, oui, il y a beaucoup d'étoiles, donc il n'y a aucune raison qu'il n'y ait pas aussi une planète qui soit là, ce n'est pas une preuve, il faut faire de la science, il faut faire des mesures, comme ça. Et vous avez des arguments, la chimie de la vie est suffisamment compliquée, etc. Non, il faut faire des mesures, voilà.
Ça, c'est bien le processus scientifique. Il faut faire les mesures, du moins physique expérimentale.
Voilà.
Il nous reste 10 minutes, donc on va ouvrir les questions du public directement. Donc on a déjà plusieurs questions qui sont arrivées. On a parlé beaucoup d'exoplanètes. On nous demande aussi où en est-on des exolunes ou exomoons. Est-ce que c'est des choses qu'on arrive à détecter?
Alors, oui, c'est possible, mais à ma connaissance, il y a une annonce très, très discutable d'une telle détection. Je ne crois pas que c'est très solide. Par contre, le principe, oui. Imaginez que vous avez la Terre, enfin une étoile plutôt, et il y a une planète qui passe ici, et elle est toute seule. Donc, ça fait des transits périodiques. Maintenant, si elle est perturbée par une Lune, eh bien, de temps en temps, l'étoile sera un petit peu en avant ou un petit peu en retard parce qu'elle tourne autour du centre de gravité Terre-Lune. Donc, vous aurez des anomalies de l'horloge. Au lieu qu'elle soit bien périodique, il y aura de temps en temps en avant, en retard. donc on peut détecter par ces avancées circales s'il y a une planète, une lune autour. L'autre solution, c'est d'analyser en détail le transit. La forme, si vous avez une planète qui passe devant l'étoile, vous avez une courbe comme ça. Imaginez que vous ayez une grosse lune à côté, vous aurez peut-être une courbe un peu plus compliquée. C'est déjà utilisé quand il y a plusieurs planètes. Mais on pourrait théoriquement aussi détecter les lunes par le même phénomène. À ma connaissance, ça n'a pas encore été fait d'une manière convaincante, disons. Mais c'est possible. Cela dit, pour moi, je ne trouve pas ça, comment dire, d'une importance si importante que ça. Quand vous agglomérez la matière pour former une planète, on a vu dans le système solaire, Jupiter a des tas de lunes, Saturne a des lunes, etc. Donc finalement, oui, ce serait bien de le voir, mais je dirais que ça ne va pas nous dire quelque chose de révolutionnaire à ce moment-là. Par contre, c'est clair que c'est sympathique de le vérifier.
On a une autre question concernant notamment la méthode de transit où tu nous as expliqué comment on pouvait déterminer la taille et la température. Comment est-ce qu'on arrive à déterminer la masse d'une exoplanète?
La masse d'une exoplanète, ça c'est l'effet Doppler. Ça c'est l'effet Doppler qui simplement va faire bouger les rayons atomiques d'une quantité qui dépend de la perturbation de la masse de l'objet qui perturbe. Donc c'est une belle composition. L'effet Doppler, la spectroscopie nous donne la masse, les transits nous donnent la dimension, et comme vous vous rappelez vos souvenirs scolaires, comment dire, si vous avez une sphère dont vous connaissez la masse et la dimension, vous savez à calculer la densité moyenne. Et ça, c'est la première chose qu'on a fait en 99 quand on a eu le premier transit. On a calculé la densité, et la densité était de 0,3 grammes par centimètre cube. La Terre, c'est 1. Donc la densité moyenne de cette première planète qui transitait est 3 fois plus diluée que l'eau. Et si vous comparez à la densité moyenne de Saturne, Saturne, c'est environ 0,7. Donc la première planète qu'on avait découverte par transit, eh bien, elle est en gros 2 fois plus diluée que Saturne. Alors on est bien d'accord, c'est la densité moyenne. Au centre, la densité est gigantesque. Mais c'était quand même la preuve directe, observationnelle, eh bien, que c'était une planète géante gazeuse. Il y avait des gens qui n'y croyaient encore pas. Hein. Bon, on peut toujours imaginer que c'était un objet d'une autre nature, un objet exotique qui aurait été découvert. Donc ça, c'était la preuve vraiment que c'était une planète géante gazeuse.
Parce que justement, tu disais que quand vous aviez eu ces résultats, avant de publier, vous avez attendu 1 an pour vérifier que ça ne pouvait pas être autre chose. Et une des questions, c'est qu'est-ce que ça aurait pu être? Qu'est-ce qui pourrait provoquer le changement de mouvement d'une étoile si ce n'est pas une exoplanète?
Oui, disons, au moment où on avait, fin de l'année 94, début 95, on avait 12 mesures qui semblaient périodiques. Je trouve que ça aurait été complètement irresponsable de dire que c'était une détection de planète. Parce que, pourquoi? Parce que si vous avez une étoile qui a des taches qui tournent, eh bien, vous avez la possibilité d'avoir des variations, par exemple, déjà de vitesse, parce que vous cachez une partie de l'étoile qui vient vers vous, qui part. Donc, vous avez des variations de la vitesse liées à la présence de taches. Alors, il fallait d'abord surtout éliminer des phénomènes liés au champ magnétique des étoiles qui perturbent les vitesses. Et donc, si on remesurait une année après, les taches ne durent pas aussi longtemps ou migrent vers l'équateur, etc. On pouvait construire, disons, un certain nombre de mesures complémentaires qui permettaient d'éliminer. C'était le risque principal, c'était les effets magnétiques dans l'atmosphère. Bon, il y aurait eu théoriquement la pulsation, parce qu'il y a des étoiles qui pulsent. Donc, on aurait pu imaginer la vitesse radiale aussi, hein, l'atmosphère vient vers vous, part, etc. Mais en fait, des pulsations à 4 jours de période, ce qu'on s'appelle des modes de gravité des étoiles comme le Soleil, ce n'est pas possible. Alors voilà, bon, après ça devient un peu plus technique.
Magnifique. On passe du coup à la dernière question qui est un peu plus lié finalement à la raison d'être de la recherche. Donc c'est vrai qu'on demande souvent à quoi ça sert finalement d'aller explorer l'univers. Et une des questions, c'est est-ce que l'astronomie et les sciences spatiales peuvent-elles offrir des solutions ou une perspective globale qui nous aiderait à surmonter par exemple la crise climatique que l'humanité semble incapable de résoudre?
J'aime bien cette question. Alors, d'abord, je vais répondre un peu de manière plus générale. Il y a plus de 2000 ans qu'il y a des gens, des philosophes, des théologiens, des scientifiques qui se préoccupent de cette question. Est-ce qu'il existe d'autres mondes ailleurs dans l'univers? Ce n'est pas des exoplanètes, c'est une vision plus générale d'autres mondes dans l'univers. Donc c'est une question fondamentale que l'humanité traîne avec elle depuis 2500 ans. Donc je dirais que c'est comme un privilège extraordinaire de peut-être pouvoir répondre à cette question. Du reste, Albertus Magnus, un très grand philosophe du XIIIe siècle, disait « Qu'est-ce qu'il y a de plus intéressant que se poser cette question sur l'existence d'autres mondes ?» Bon, ce n'est pas la première partie. Alors maintenant, est-ce que ça peut être lié à la crise climatique? Alors d'une manière indirecte, je dirais. D'abord, on réalise qu'en tant qu'humain, on est lié à cette planète. Donc tous les rêves qui peuvent être proposés par certains d'aller ailleurs sur une autre planète habitable, c'est simplement non, ce n'est pas vrai. Comment dire? Alors je ne parle pas du système solaire, mais d'une exoplanète parfaite. Imaginez que dans nos recherches, on en trouve une qui soit de bonne température, de bonne masse. On peut prouver qu'il y a l'atmosphère est là et tout ce que vous voulez. Vous ne pouvez pas y aller. Vous pouvez faire un calcul très simple. L'homme est allé sur la Lune en 3 jours avec Apollo 11. La lumière met 1 seconde environ pour y aller. Voilà. Maintenant, imaginez qu'on trouve cette planète de rêve qui se trouve à 30 années-lumière. 30 années-lumière, c'est une voisine. La galaxie, c'est 100 000 années-lumière. Alors donc, vous voyez cette petite bulle-là, 30 années, imaginez que vous en trouvez. Eh bien, 30 ans, c'est déjà 1 milliard de secondes. Donc, aller sur cette hypothétique analogue de la Terre, c'est 1 milliard de fois plus loin que la Lune. 1000 millions de fois. Alors, le problème, si vous y allez à la vitesse de l'Apollo 11, le voyage dure longtemps. Hein. Mais si vous accélérez, vous prenez où l'énergie pour accélérer et en plus ralentir, parce que ça ne sert à rien d'arriver à la vitesse de la lumière. Donc simplement, voilà, des raisons de physique comme ça ne peut pas. Et puis même si vous l'accélériez et la ralentissiez, simplement, ça prendrait encore, parce que vous ne pouvez pas le faire à la vitesse de la lumière, ça prendrait des temps incroyables. Donc non, on n'ira pas. Alors il y a des concepts dans le système solaire où pour aller faire les missions, ça c'est tout à fait une toute autre question, mais pour les exoplanètes, non. On est des humains, puis on y reste, et puis on soigne notre environnement.
Eh bien, c'est une magnifique manière de clôturer cette discussion. Interstellar restera de la science-fiction. Merci Michel.
Allez, merci.
Merci Michel. Donc on te retrouvera dans une vingtaine de minutes pour une autre discussion avec Megan Christian qui nous reviendra sur scène. Donc on va prendre une pause de 20 minutes et on vous retrouvera pour la 3e session de l'événement Stellar. Merci beaucoup.
Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running. We have a liftoff. Liftoff on Apollo 11.
On this July 20th, 1969.
It's one small step for man, one giant leap for mankind. Oh, that looks beautiful.
And good evening once more, everyone, for the final session of our stellar event, which promises to be probably the most exciting one. You can guess that from the title, Stellar Dream, Seizing the Opportunities of Space Exploration. But we are starting with a big surprise, something which was not announced on the program, and something that will be particularly liked by some Polish people in the audience. There he is. We are talking to Sławosz Uznański-Wiśniewski, who is just back from space. He's actually in quarantine at the European Astronaut Center in Cologne. And in spite of the real signs of fatigue, but big happiness, he has accepted to talk to us. Welcome back on Earth, Sławosz. Can you put the sound, guys, from the Zoom? Sławosz, let's try again.
Hello, yes.
Yes, we can hear you, we can hear you. So this session is entitled Interstellar Dream, and you are the perfect example of somebody who 2 years ago didn't even know where you would be today, right?
That is true. 2 years ago, I was actually at CERN, like all of you now here, and it's a big pleasure for me to be here with you guys.
So when were you back from space? Exactly.
When?
When did you come back? For our audience.
This is quite interesting. What we say, today is R+4. So it means return plus 4 days.
Return plus 4 days.
Yes, we undocked from the International Space Station just on Tuesday. We splashed down on Wednesday. And from the coast of California, I flew to Houston, then through Washington to Cologne, where now I go through the reconditioning in the clinic of the European Space Agency.
So we are seeing some images of your mission, which lasted a couple of weeks on the space station. You flew with a Crew Dragon vessel. And tell us, what are the highlights of your mission?
Oh, there were so many of them. It's very difficult for me to pick just a couple of them. Obviously, each astronaut is looking forward towards the launch. And for me, the launch was a big moment. That was the first time I could experience, like building up these Gs and like after just a couple of minutes being injected into orbit and feeling the weightlessness, the microgravity. And for the first time, it was for longer than just 20 seconds or so. Like I could, experience the microgravity in parabolic flights before during my training, but at that moment it did not stop for 20 days. So that was a great moment. But I think one of the highlights was really going through the International Space Station, and for the first time to Cupola, to our window back on Earth, the window back on home, and. The crew that was on the International Space Station, they put us with a head down in Cupola because the window looks down on Earth with closed eyes. And they told us then to open the eyes when we were really close to the window. And for the first time, I saw Earth really, 360 degrees panoramic view with, this big, bright blue planet below our heads. For me, it was a very emotional moment.
During this mission, you did many experiments. One of them was from CERN. Can you briefly tell us about that?
Oh, yeah. There were a lot of scientific highlights for me as well. And yes, we took one of the CERN experiments to the International Space Station during the Polish mission. The mission is called IGNIS, and one of the Polish company commercializes through the CERN's knowledge transfer the CERN radiation dosimeters. So the dosimeters that we built at CERN, we install in our tunnels just to know the evolution of radiation, how we lose particles at CERN, and how our radiation evolves just, for operational reasons. CERN had this dosimeter sent on a Celesta satellite a couple of years before in collaboration with the University of Montpellier. And this time, with a Polish company, we brought the CERN dosimeter to the International Space Station that I had the big pleasure to install it in Columbus laboratory, so our European laboratory on the ISS. And this is the first dosimeter from CERN installed there in Columbus, and I hope the second one will be coming to be installed in an external platform to measure radiation directly of outer space.
And talking about CERN, before your selection, you were working here first as an engineer in charge on the LHC controls, and then as member of the systems team behind the Large Hadron Collider. Was this experience of 12 years at CERN useful as a training for what you're doing right now?
Oh, Paula, thank you for the question. And this is, for me, CERN is a tremendous experience that I got. I really grew up professionally at CERN. I would say that there are two main aspects. One aspect, as an engineer, as a systems engineer, I built with my team in technology department, then systems department, EPC group, the powering system and powering controls for the LHC. So that's, you know, building and working in the lab, debugging systems and being surrounded by electronics that we build at CERN, systems, commissioning, putting this in operations and then operating the systems is exactly how the work, how I worked on the ISS. So I think it sets me very well on good track for the mission. And I would say the second aspect is, as you said, operational one. You know, working in the CERN control center for long hours, shifts, weekends, sometimes it's really hard. But on the other hand, being in a control room, all of us, we have this feeling that you're surrounded in, like, this is why we exist as the organization. We deliver particle collisions to thousands of scientists. And this is where you really control the infrastructure to make that happen. And the ISS and space mission is quite similar. You have, you know, thousands of people on the ground that communicate with PIs, the principal investigators and scientists. And then you have astronauts, operators of science on orbit that actually execute this science on behalf of hundreds and thousands of people on Earth. And I find this really magical and the beautiful, you know, let's say, thanks to these collaborations, like big science collaborations, we manage to do such beautiful experiments and science and push the boundaries of our knowledge.
Thank you very much, Sławosz, for taking the time to talk to us during your quarantine. I also have a countdown, and some of your colleagues, more senior colleagues and less senior colleagues, are coming on this stage for this last session of our stellar event. But I'm really looking forward to seeing you back home, home being CERN.
Oh, Paula, I can't wait. And I wish you a beautiful session with my colleagues and other panelists.
You can watch us live on YouTube.
Yes, I will. Thank you so much for the invitation.
Thank you, and you enjoy your return +4.
Thank you.
Thank you. This was not foreseen, but I think it was worth it. Let's now switch to French. Those who want to follow in English can take their earphones. And I'm giving back the floor to Galactic Chloé. Chloé, the floor is yours.
Merci Paola, merci. Bonsoir à toutes et tous et bienvenue pour cette dernière session qui va nous faire rêver parce qu'on va réaccueillir certaines des personnalités qu'on a eues dans d'autres sessions, mais cette fois pour parler de leur parcours. Parce qu'il y a des prix, il y a des positions qui nous font rêver, mais il y a aussi des personnes qui sont derrière ces titres. Et donc, je suis ravie de raccueillir sur scène Mégane Christian et Michel Mayor. Prenez place. Donc, nous sommes là pour parler de vos parcours. Notre session s'appelle d'ailleurs « Décrochons la Lune, décrochons le Nobel mode d'emploi ». Donc, on verra au bout de 30 minutes si on a véritablement un mode d'emploi pour avoir ces deux titres. Peut-être pour rappeler, pour ceux qui n'étaient pas là aujourd'hui, qui viennent de nous rejoindre un petit peu ce que vous faites. Michel, prix Nobel de physique en 2019 pour la découverte de la première exoplanète qui orbite une étoile similaire au Soleil. Et Mégane, vous êtes astronaute de réserve sélectionnée par l'Agence spatiale européenne en 2022, mais aussi scientifique avec notamment une mission en Antarctique. Merci beaucoup à vous deux d'être parmi nous.
Merci.
Donc vous avez tous les deux, comme on l'a dit, des parcours d'exception. Et la première question que j'ai envie de vous demander, c'est si on remontait dans le temps, est-ce que c'est quelque chose que vous rêviez enfant? Est-ce que vous disiez, moi, je veux être astrophysicien ou je veux être astronaute?
D'abord, je m'excuse parce que je réponds en anglais. Il y a 15 ans, je parlais assez bien français, mais puis je me suis déménagée en Italie et l'italien a chassé le français de ma tête. Donc, je réponds en anglais.
Votre français semble impeccable pour le moment.
So I continue in English. I was born in the UK, but I grew up in Australia.
And there was no space agency in Australia at the time. There is now. But I started learning about the stars and planets and black holes. I was particularly fascinated by black holes. And I thought that was fascinating. But I actually didn't think of it as a career for me. I did think of science, though, because I loved problem solving and maths as well. So I ended up doing a Bachelor of Engineering, followed a scientific career, and it wasn't until I went and spent a year in Antarctica under that amazing polar night that I decided that I wanted to apply to become an astronaut.
Donc, vous êtes né en Australie et
Non, je suis née en Angleterre.
En Angleterre.
Ouais.
Ben, j'ai trouvé que vous aviez aussi la citoyenneté donc anglaise,
Oui.
italienne,
Néo-zélandaise.
australienne et néo-zélandaise. Comment
Oui.
est-ce qu'on a toutes ces citoyennetés en même temps?
My parents are New Zealanders. I was born in the UK. I grew up in Australia, and I spent 9 years in Italy.
Wow. Wow. Et pour vous, Michel, est-ce que c'était un rêve d'enfant d'étudier l'univers, les étoiles?
Non, pas du tout. Comment dire, comme enfant, la seule chose dont je peux bien me rappeler, c'est que j'étais vraiment fasciné par la science. Alors quand je dis la science, ce n'est pas l'astronomie, hein. C'était n'importe quel domaine de la science, c'était mon domaine favori. Comment dire. Et puis après, bon, j'ai fait des études comme ça. Puis en étant adolescent, j'ai été plutôt fasciné par le côté, très abstrait. Et donc j'ai travaillé plutôt en physique théorique d'abord, des problèmes d'interaction de particules, des choses comme ça. Et puis c'est un peu graduellement que j'ai commencé une thèse en astrophysique, et là, après, je vais d'abord revenir un tout petit peu, pourquoi enfant, typiquement, quels étaient les domaines qui me stimulaient particulièrement. Ma chambre donnait sur une montagne où on voyait ce qu'on appelle un pli retourné. C'est-à-dire que vous avez une bande de roches qui est ici, facilement visible, qui fait un Z comme ça. Et les adultes vous disent, c'est quand la plaque africaine a percuté la plaque européenne, Eurasie, que les montagnes, les couches se sont pliées, et comme ça. Et comme enfant, tiens, on peut plier une montagne, comme ça. Voilà, donc ça, c'était le genre de réflexion qui me perturbait comme enfant. Alors après, j'ai pas fait, comme je vous ai dit, j'ai fait plutôt de la physique théorique, comme ça. Et puis, quand j'ai commencé en astronomie, c'était les années 60, on pouvait facilement commencer dans différents domaines. Et là, il y avait une place qui s'ouvrait à l'Observatoire de Genève. Et là, j'ai commencé à travailler sur un problème complètement théorique qui était des problèmes liés à ces formes des galaxies, à des galaxies spirales. Mais c'était purement, il n'y avait pas de télescope, hein, c'était une feuille de papier et un crayon, hein, comme ça. Et comme j'ai eu énormément de plaisir à travailler dans ce domaine-là. Et puis à la fin de ce travail, de ma thèse, eh bien, je me suis dit, est-ce qu'on pourrait mesurer la vitesse des étoiles pour voir les modifications du flux des étoiles quand elles passent à travers le bras spiral. Et donc, il fallait des milliers de mesures de vitesse radiale d'étoiles. Et à l'époque, ça ne se trouvait pas dans les livres, il fallait le faire soi-même. C'était horriblement ennuyeux à faire, très inefficace, très peu précis. Et là, c'est ça, c'est hasard de l'existence. Tout d'un coup, je vais à Cambridge pour toute autre raison. Et là, je vois un astronome anglais, Roger Griffin, qui bidouillait, il développait un nouveau type de mesure qui était ce qu'on appelle la corrélation croisée. C'est une technique, enfin, on utilise toutes les raies spectrales pour mesurer une seule chose, la vitesse de l'étoile. Et il le faisait avec des moyens très simples. Et là, j'ai eu, le coup de foudre. Je me suis dit, c'est ce qu'il faut faire. Et puis, je suis rentré à l'Observatoire à Genève. J'ai demandé l'autorisation de le développer. Les gens ont beaucoup ri parce qu'un théoricien qui fait un instrument, ça c'est inhabituel. Et puis, et en fait, avec des moyens meilleurs que mon collègue anglais, eh bien, tout d'un coup, c'était le début de cette aventure qui m'a mené, 20 ans après, à m'intéresser aux planètes.
Merci. Est-ce qu'on m'entend? Oui, parfait, merci. Donc finalement, un parcours académique en physique théorique, pour le commun des mortels, on peut dire que c'est assez dur de faire ça. Est-ce que parfois vous avez failli abandonner? Est-ce que vous avez douté de votre capacité?
Non, je crois que... Comment dire? Bon, quand j'ai terminé mon travail de diplôme en physique théorique, il y avait des annonces de travail, d'offres de poste. Et puis on était deux sur le même genre de sujet. Il y avait un poste qui s'ouvrait à l'école polytechnique en mécanique statistique. Et puis il est allé voir si ça l'intéressait. Et il est devenu professeur de mécanique statistique. Et puis moi, j'ai été voir à l'observatoire. Et puis j'ai trouvé que ce problème était intéressant. Et c'est comme ça que j'ai débuté. Mais ce n'est pas du tout... Au contraire, je restais fasciné par la physique théorique. La preuve, c'est que ma thèse est dans le domaine, en termes techniques, des ondes de densité dans les galaxies. Voilà. Et alors après, c'est quand j'ai voulu m'intéresser à mesurer des vitesses que là, j'ai fait ce changement, tout d'un coup, de m'intéresser à l'instrumentation. Et alors que quand on est, disons, à 20 ans, on a une certaine fascination par l'élégance de la théorie. Et puis, comment dire, on considère l'instrumentation comme étant un peu secondaire. Et là, ce n'est pas vrai. Moi, j'ai eu un plaisir énorme à développer, comment dire, ces instruments. Dire, de temps en temps, il arrive, des journalistes m'ont posé la question, quel est le moment le plus exaltant que j'ai vécu? Et tout le monde s'attend évidemment à dire, c'est quand on a découvert la première planète. Eh bien non, ce n'est pas vrai. Pour moi, comment dire, quand vous avez travaillé à 10 personnes pour développer un nouvel instrument et que vous êtes dans la coupole au Chili, et comment dire, que tout le monde est dans la coupole, vous mesurez la vitesse d'une étoile, vous arrivez à 17 km,434, et puis vous répétez la mesure, et vous avez 17 km,434. Comment dire, et tout d'un coup, un instrument où vous avez travaillé à 10 personnes pendant 5 ans ou 4 ans, eh bien, tout d'un coup, de voir que vous avez la capacité de mesurer les vitesses d'étoiles avec cette précision-là, c'est là le moment le plus fascinant. Je trouve absolument fascinant le fait que tout d'un coup, vous voyez, ça marche.
Donc finalement, la curiosité scientifique, un moteur qui ne s'arrête pas, même encore aujourd'hui.
Et puis le fait d'être une équipe, tout d'un coup, vous avez dans la coupole des opticiens qui ont travaillé, vous avez des gens qui ont réglé les problèmes du froid, etc. Tout, il y a tellement de compétences qui sont mélangées pour arriver à ce faire. Et comment dire, il y a un sentiment global que l'on retrouve très fréquemment dans les images quand tout d'un coup il y a une mission spatiale et puis qui arrive au résultat et vous voyez l'explosion dans la salle de contrôle, une explosion globale de joie, comme ça. Et c'est un peu le même phénomène que l'on a. Pourquoi je dis que ce n'est pas le moment de la découverte de l'exoplanète? Parce qu'il n'y a pas un moment. Comment dire, on fait des mesures, on répète des mesures, etc. Et puis après un certain nombre, vous avez une série de mesures et vous voyez se dessiner, quand vous les repliez, une mesure périodique, etc. Mais ce n'est pas un moment donné, comme ça. Et puis ces mesures-là, vous avez quelques mesures, beaucoup de paramètres libres, un peu de bruit. Comment dire, et puis alors surtout, l'inquiétude, est-ce qu'on parle d'une planète ou est-ce qu'on parle d'un autre phénomène? Et comment dire, quand en janvier 95, tout d'un coup on a vu ce signal périodique, ça aurait été, je trouve, complètement non scientifique de parler de planète à ce moment-là. Il y a tellement d'autres phénomènes physiques qui auraient pu expliquer ce phénomène-là, donc ça justifiait d'attendre plusieurs mois, vérifier la stabilité du signal, etc., avant de parler de planète. Donc voilà, ça c'était... Donc il n'y a pas un moment... Oui, c'est vrai, quand on a vérifié au mois de juillet 95 que le phénomène était toujours là, bon, voilà, on a festoyé.
Vous étiez content quand même.
On a quand même festoyé avec tarte aux framboises, clairette de Die.
Le combo gagnant. Megan, vous avez une trajectoire non linéaire, si je peux dire, puisque vous avez fait de la recherche, vous êtes allé à Concordia, maintenant vous êtes en train de vous entraîner pour potentiellement devenir astronaute. Est-ce qu'il y a un moment qui est plus formateur pour vous, ou est-ce que c'est la diversité finalement?
Many, many moments. I think it has been my response to doubts that I've had that have shaped me in a way. I remember even in high school, I didn't think I was a particularly good student. I mean, I knew I got pretty good grades, but then a teacher said to me, "You don't know how close you came to being top of the year." And so that made me think, oh, okay, shall we do this? And so I did, and I pushed harder, and then the next moment was probably during my PhD. In my first year, I was making nanomaterials for hydrogen storage. Goal was to release hydrogen at a fairly low temperature. And I was kind of banging my head against the wall, trying to make all these different materials. Temperature was always 300 degrees. See this graph, it's another 300 degrees. But then one material I made, suddenly there was this hydrogen coming out at 50 degrees. And my supervisor said, "You've got your PhD." Of course, there was a lot more to do after that, but that was a special moment for me as well. And then, fast forward many years, I did a postdoc in Bologna at the National Research Council. I was working on a material called graphene, doing a lot more of bashing my head against a wall, but also having a bit of fun with it. But then I got this email from the National Research Council asking who would like to go and spend a year in Antarctica. And I thought back to when I was 12 years old, and I had been to the International Antarctic Centre in Christchurch in New Zealand, and I thought about how fascinated I was by that, and I thought, oh, I would love to do that. But you know what? I ignored it, because I thought there's no way they would accept someone like me. My work is in material science. They need somebody to do atmospheric physics and meteorology. I don't even really know what atmospheric physics is. But then, a year later, I got the email again, and I thought, you know what? I'm just going to send them an email and ask if they'll accept an application from someone like me. And they said, yeah, come and have a chat. Turned out that chat was an interview. And then I found my way to Antarctica. I was on a plane to Antarctica for what was a life-changing experience. And there were doubts even then, because, you know, it wasn't the type of work I had done before. I hadn't done a lot of programming or electronics in the past, and that's the main part of what I would have to do there. So I got there, and I had this first 2 weeks of handover with the previous winter over crew. I loved it. I loved that steep learning curve. And I loved being the custodian of other people's experiments. People had put their life's work into designing these experiments to go to Antarctica, but couldn't be there themselves to be the hands. So this was the first little connection with what astronauts do on the International Space Station. They're also the custodian of other people's experiments, just like Sławosz was saying before. And then the real moment was when I had this particular task to do, which was clean all the instruments on the American Tower, which was 1 kilometer away from the base, 45 meters high. We're at high altitude, so low oxygen levels, hard work. But my colleague and I would always use that as an opportunity to let our eyes adjust to the darkness. So we would take our headlamps off and just look up at the stars. And they were so bright. You felt like you were blanketed in those stars. And if it was a moonless day in these 100 days of darkness, you could look down and see your shadow in the light of the Milky Way. That's how bright those stars were. And so this combination of this very practical experience of what I wanted to do, what I enjoyed doing, and also this inspirational environment, that's what convinced me that I wanted to apply to become an astronaut. And it was good timing, because for the first time in 13 years, just a couple of years later, the European Space Agency opened up applications.
Donc finalement, c'est un rêve ou un objectif qui s'est construit petit à petit. est-ce que, à votre avis, c'est légitime d'avoir ça comme objectif de vie?
Is it legitimate? I mean, yes, but I wouldn't have it as your only goal. Because now there are so few opportunities to become an astronaut. Those opportunities will increase in the future, but you have to already be doing something that you love. And so that, in that case, becoming an astronaut, it's easier because you're already doing something that you love and that you're good at. And hey, if you don't get it, then you're still okay. You're still enjoying life. Whereas if you have it as your sole goal, it makes things much more challenging.
La cerise sur le gâteau.
Oui.
Cherry on the cake in English.
Exactement.
Et pour vous, Michel, est-ce que vous pensez que ça doit être un objectif d'avoir un prix Nobel en tant que scientifique?
Je dirais surtout pas. Parce que, comment dire, je ne sais pas combien, mais alors, disons qu'il y a 100 000 physiciens qui travaillent dans le monde. Il y en a des quantités qui font des travaux exceptionnels. Il y en a 300 à peu près qui sont nominés chaque année pour le prix Nobel. Et il y en a un qui l'obtient. Ou 3, je ne sais pas. Comme ça. Mais comment dire, et les autres, ils n'ont pas fait du moins bon travail. Comment dire, ça veut dire que vouloir ça, faire ce pari d'avoir un prix Nobel est un pari complètement inapproprié. Comment dire, le problème, c'est est-ce qu'on a du plaisir à faire de la recherche? Et puis, comment dire, il se peut que la recherche que vous faites, comment dire, va déboucher sur quelque chose qui a un impact global sur la physique, mais ça, vous ne pouvez pas le planifier à l'avance. Donc non, je pense que celui qui voudrait faire ça, c'est un mauvais pari. Comment dire, je dirais, les scientifiques ont un privilège gigantesque, déjà par leur métier, cette curiosité. On vous paye pour chercher des choses nouvelles dans la nature et le fonctionnement. Comment dire, c'est ça la joie de faire de la recherche. C'est pas de miser. Évidemment, on est content si par hasard ça marche, mais il faut voir que la probabilité est telle que ça n'a aucun sens de viser. Et j'ai jamais pensé du tout. Oui, à partir du moment où elle était découverte, oui, petite anecdote. Le médecin de mon épouse, quand je le rencontre dans les jours après l'annonce, il me dit « ça, c'est le prix Nobel ». Je n'ai jamais pensé à ça. Puis bon, on a rigolé un moment. Et puis quand on est rentré, j'étais en Espagne quand il y a eu l'annonce. Quand je suis rentré à minuit chez moi, il y avait un sac plastique pendu à la porte de ma maison avec une bouteille de champagne dedans et une carte de visite de ce médecin qui me disait « voyez, j'ai le bras long ». Comme ça, voilà. Donc, mais on ne planifie pas ça à l'avance. Non, ça n'a aucun sens.
On devrait renommer alors le titre de cette session. Il n'y a pas vraiment de mode d'emploi pour être astronaute au prix Nobel. Ça arrive à la dernière question. Après, on aimerait ouvrir les questions pour le public. Donc, si jamais vous voulez en poser, il y a un QR code qui va apparaître sur cet écran. Donc, n'hésitez pas à le scanner et puis à poser vos questions. La dernière question que j'aimerais vous poser, basée sur ce que vous venez de nous partager, quelle est pour vous la définition du succès?
For me, it's enjoying what you are doing and contributing as best as you can to the world in whatever way is right for you.
Pour moi, il me semble, c'est qu'on va dire arriver à un résultat dans ce qui vous passionne, simplement. C'est ça le succès.
Donc finalement, ce n'est pas les prix ou les titres, c'est vraiment plutôt une forme d'épanouissement.
Oui.
Avec un impact sur le monde. En tout cas, c'est ce que je retiendrai de vos réponses. Merci beaucoup. On peut déjà les applaudir le temps qu'on collecte encore des questions. Alors, on a une première question qui peut-être je vais poser à Megan en premier, donc en anglais. As someone that changed trajectories, did you experience any second thoughts in changing, and how did you handle it?
Yeah, I've changed trajectories more than once, I guess. I think the bigger problem was not changing sooner. Because I was ready probably sooner than I actually changed trajectories to take the new challenge. So that's probably a little regret that I've had, although to be honest, looking back, I don't really have any proper regrets because I'm very happy to be here. but it's also difficult. I'm a member of the reserve, so I'm not employed by the European Space Agency. There are no guarantees of a flight for me, so I'm in a bit of a strange position. But you just saw Sławosz. He's my colleague from the Astronaut Reserve, so you never know what's going to happen. But there's a lot of uncertainty, and you just have to go with it.
Une prochaine question plutôt pour Michel concernant la vie sur l'exoplanète. Que signifierait pour vous de trouver un autre type de vie intelligente sur une exoplanète?
Question impossible à répondre. Dire, déjà, c'est même pas la vie intelligente. La vie intelligente, ça, j'ai vraiment aucune idée. Mais même simplement de la vie. Quand on parle de détecter de la vie, il faut voir que pendant la plus grande partie de la vie sur Terre, c'était des unicellulaires. Et donc, des unicellulaires sont déjà de la vie. Et c'est déjà d'une complexité gigantesque. Et comment dire, actuellement, il y a des gens qui travaillent dans le laboratoire de voir des réseaux de réactions chimiques qui pourraient conduire à des choses comme ça. Mais on en est très loin de comprendre éventuellement ce qui se passe. Au niveau observationnel, ce n'est pas pour demain qu'on va découvrir ces méthodes d'analyse chimique des atmosphères planétaires. Comment dire, c'est une des grandes et belles questions pour le futur. Et je dirais, dans la thématique de, comment dire, c'est fascinant qu'il reste des questions gigantesques pour les plus jeunes chercheurs qui sont là. Comment dire, actuellement en astrophysique, vous avez la recherche de la vie, on en parle, mais il y a d'autres questions. La masse cachée dans l'univers, l'énergie noire, le fait que dans les galaxies extraordinairement lointaines, les plus anciennes, on découvre déjà des trous noirs massifs, comment est-ce qu'ils se forment, etc. Et ça, c'est dans un tout petit domaine de l'astrophysique. Comme ça, c'est ça qui est absolument fascinant pour le futur. Maintenant, pour la vie, comment dire, je ne sais pas. Comment dire. Et puis, est-ce que c'est des formes de vie similaires aux nôtres? On ne sait pas. Bon, moi, je suis lié aux exoplanètes pour des raisons évidentes, mais il y a une chose qui me passionne encore plus dans ce domaine-là. Alors, vous savez, il y a Europa, un des satellites de Jupiter, qui a une couverture de glace, une banquise, c'est-à-dire ce n'est pas des glaciers, c'est une couche de glace sur un océan. Et c'est fascinant d'imaginer qu'il y a de l'eau liquide dessous, comme ça, et cet océan est cassé à certains endroits, l'eau monte dans la fissure et forme un bourrelet. Et des mesures absolument des photos fascinantes de voyageurs à ce sujet-là. Imaginez, et c'est de la science-fiction, mais qui va se faire. Comment dire, qu'une sonde va sur cette satellite, prenne, je dirais, 1 mètre cube de glace, fonde ce mètre cube de glace, filtre et découvre qu'il y a des formes de vie là-dedans. C'est impossible de forer, c'est beaucoup trop épais, là, comme ça, mais l'eau, elle monte dans la fissure, elle sort comme ça. Donc, le bourrelet qui se trouve à la surface, c'est de l'eau qui vient de dessous. Imaginez que l'on trouve des formes élémentaires de vie, des unicellulaires. C'est d'une richesse incroyablement meilleure que ce qu'on voit quand on détecte sur une exoplanète. Pourquoi? Parce que vous auriez par exemple la possibilité de voir si l'ADN est le même que celui qui est l'essentiel de la vie sur Terre. Est-ce que la vie n'a qu'une seule recette ou est-ce qu'il y en a d'autres? Voilà. Donc ce domaine-là, je suis sûr qu'il est avec nous au sens général de l'humanité pour des dizaines d'années, des centaines d'années. C'est tellement riche de problèmes d'une grande complexité, mais à la clé, on n'est pas sûr, on n'en sait rien s'il y a d'autres formules qui permettent de créer quelque chose qui ressemble aussi au vivant. C'est beau d'avoir des belles questions. Il n'y a rien de plus triste qu'imaginerait si on avait tout compris.
En tout cas, ce qui est sûr, c'est qu'il y a de la place pour une prochaine génération de scientifiques et d'explorateurs. Merci beaucoup à vous deux. On arrive déjà à la fin de notre session. On a tout de même une dernière question, mais justement, je pense que ce sera pour notre prochain speaker. Is it hard to be an astronaut? Je pense qu'on laissera Paolo Nespoli nous répondre. Merci beaucoup à tous et toutes.
Merci Chloé, merci Michel, merci Megan. So you spoiled a bit my surprise, but I just wanted to say we keep dreaming with our next speaker, because this is somebody who fulfilled many of the impossible dreams I think a lot of us, 99% of us in this audience, have had. He started his career as a professional parachutist. Then he joined the peacekeeping forces in Lebanon. Then he became an astronaut, and he rode 2 types of rockets. First the space shuttle, then twice on the Soyuz, for a total of 313 days on the International Space Station, thriving, working hard, and having fun. So I have the very big pleasure of introducing here on this stage Paolo Nespoli.
Thank you, Paola. Thank you. All right, so thank you for inviting me here tonight. And yeah, the title that was given to me was Survive and Thrive in Space, a Beginner's Guide, which threw me off a little bit because I was trying to figure out what am I supposed to say here. So I came up with something which is kind of funky, said in English, because we are in an historical moment, in my opinion, very interesting, especially for space, because we are switching from astronauts that are belonging to space agencies to other type of astronaut. Some may say tourists, some may say space participants. So it's kind of complicated situation. But the good news is that this will allow us, all of us, to go to space without going through the griming selection or impossible selection and things like this. But then, if we talk about, you know, astronauts in general, I do have difficulties in defining the word astronaut. And by the way, I would like to make a disclaimer. Whatever I say tonight is my opinion. It's nothing to do with the European Space Agency, NASA, whatever. It's my personal opinion. And so, in my opinion, if we look at an aircraft like this today, it's clear that there are people that work to make the spacecraft go, which is the pilots, the steward, they are working to make sure that the other guys, which are the passengers, which means us, can sit in the back and maybe read a book, drink a glass of water, because they don't give you more than a glass of water, and maybe go to the toilet, one toilet for 200 people, but okay. So, but you are enjoying, you're sitting there, driving, flying the spacecraft, flying the aircraft is not your task. Somebody else has been trained, has qualified, has gone through all sorts of qualifications. So you know, if a guy like this shows up with 4 lines, it means he's you know, an ATP, a pilot that is allowed to drive, to fly a plane, is qualified. So the problem is that if you go to space, it's not, well, it's not that flying is simple. It's relatively complicated, but still, I think we master it now. But if we want to go through outside Earth gravity, there are some hurdles which are a little bit more than, you know, flying on an aircraft. And I would say that, first of all, you have to deal with Earth gravity that, you know, wants to take us to the center of the Earth. Thank God there is a floor, so I'm not going down, or you're not going down too. But essentially, that's a big force that is keeping us attached to Earth. And there is the atmosphere, which is very thin layer of gas. But then when you start pushing to go up, it becomes as thick as a blanket, even more than that. It becomes very viscous. And so you need a lot of energy to actually end up and flying in space. So here we go to the definition of astronaut, which is not the official definition. It's my definition is, or at least the reason why astronaut wants to go in space. And okay, one of the reasons could be satisfying the personal curiosity. You know, I want to know what it feels being in space, feeling microgravity, looking at Earth, you know, personal curiosity. But then, you know, you can go for scientific reasons. You can go for exploration. I want to go and explore Mars. Those are all things that we want to do. And now it's kind of difficult to put together all these things because, you know, let's say that professional astronauts, which are doing scientific work in space and explore, satisfy their personal curiosity, probably yes, but it's not their primary goal in space. At least when I fly in space, I'm there because I feel I'm useful to collect data that really are wanted by scientists here on Earth. So if we try to derive categories of people that fly in space, I think one of the categories could be commercial space flight participants, and a second category could be a professional astronaut. That means that, you know, if you are a commercial flight participant, you know, even today you can buy a flight, cost only $50, $60 million, but you can buy it, and you can go 10 or 12 days on space station and do whatever you want, and nobody's going to ask you to do something. You're just going there. But then, if you are a professional astronaut, the story is kind of different. And by the way, the requirement for commercial space flight participant are fairly low, meaning that as long as you can go, you should go. And in fact, the requirement from the system is that they will try to take as many people as they can, as many people as they have, you know, $50 or $60 million to pay for a flight. You don't want to tell somebody, sorry, your 50 millions are not good enough because, I don't know, something, your eyesight is not good enough. But for the professional astronaut, it's actually the opposite, is that in order to become a professional astronaut, you need to go through a very heavy-duty selection process. And in fact, only very few people are selected as astronauts. So usually there are thousands and thousands of candidates, and we select 1, 2, 3, or 4 astronauts. And then it takes quite some time to fly them in space. So one of the places where we go, even non-professional astronaut right now is, for example, the space station. Space station is 400 kilometers away from Earth, and of course we could go to the moon, about 380,000 kilometers away. About 3 days you could go. I can even say that in future people could buy, and there were already some people that bought theoretical flight to the moon just to go and feel how it feels, figure out how it feels to go to the moon and come back. Of course, sooner or later we will go to Mars. That's going to be the next step. Mars is kind of far away. It's about, you know, between 100 to 200 million kilometers. It requires a little bit more travel to go there. But strangely enough, the most interesting and complicated part to any of this trip is the beginning, is when you leave Earth to go through the atmosphere and then either go to the space station or the moon or Mars. And in order to fly on any one of these goal or places, you need to use a vehicle that is it's an interesting vehicle. This is a picture of the space shuttle. The space shuttle contains, this system contains enough energy to be equivalent more or less to the mini atomic bomb. So when you go in space, in order to beat the gravity that will pull you down to Earth and make a hole in the atmosphere and go out of the atmosphere requires a lot of energy. And it's clear that it's not something that you just go there and you go. In fact, if you want to be a crew of this vehicle, it's going to take quite some time to learn how to fly this thing. It's almost like if you want to fly to New York today, you just go to a store on the corner and you buy a ticket. But it would be complicated if the guy would say, okay, in order to fly to New York, you need to get a license to fly the 747. And this is the same situation, is that you find yourself having to negotiate with a vehicle like this. Of course, the shuttle now is retired, but we have different vehicles. We have the Russian Soyuz, which is a little bit less comfortable than the shuttle, but still does the work. It makes you beat gravity and go through the atmosphere. Or the Dragon, which is the vehicle that Matthias and Sławosz used to go in space. So, but this is still a mini atomic bomb, and in order to fly on these things, you need some kind of training. But eventually, you will end up on the space station. In this case, space station is 400 kilometers. It orbits Earth at about 28,000 kilometers per hour, which means you're spinning around Earth every hour and a half. It does this so that, in fact, gravity is pulling the space station towards the center of the Earth, but at that speed, at 28,000 kilometers per hour, it turns out that the station is falling, but it's falling over the horizon. So the station is falling, and this never-ending fall, and that's where things don't feel they don't have weight. In fact, they keep their mass, and the weight is used to actually go around the Earth. But that makes so that the space station becomes an interesting place where you can do a lot of things because it becomes a laboratory, a special laboratory where you can do things that you cannot do anywhere on Earth. Things behave differently because when you take away gravity, certain things that you cannot measure here on Earth, they become apparent. You can measure them, you can understand them, you can take this knowledge and bring it back to Earth. And so it's a laboratory, but the interesting thing is that when you have finished to work, it's not that you can go home in the evening, you have done working and I'm going to go home and go to dinner with my family or go out with the dog or something like this. This is your place, and this place where you're staying is not extremely big. I mean, the structure is fairly big. It's as big as a football field. That the truss in the middle is more than 100 meters long, but then we live in the center modules that have a volume of about 450 cubic meter. 450 cubic meter, if I would ask you how big is this room, would you be able to have an answer in a few seconds? Because we don't measure things in cubic meters, and if you do a translation between cubic meters in square meters, because we measure our houses in square meters, it turns out that the surface in there is about the apartment, a relatively small apartment, not extremely big, not extremely small, but more or less 100 square meters. 100 square meters. The problem is that you are in at least 6, 7, 8, 9, 10, 11 astronauts in 100 square meters. And, already probably people that are used to live with a partner and a dog already know that 100 square meters sometimes is too little for 2 people or 3. And think about 7 people, American, Russian, European, Japanese, Canadian, different culture, different language, different way of eating, different way of socializing, different way of exchanging information. It can get fairly complicated. So the bottom line is that in order to select people that apply as a professional astronaut, they actually look at certain parameters like the health status, the psychological status, the anthropometric measures, because if you are 2.20 meters, probably you will not fit into the spacecraft, or if you are 1.20 meters, it's also too little. So you need to be able to reach the control, you need to be able to fit into the spacecraft, you need to be able to speak English, you need to have a technical degree, because at the end you will be requested to do all sorts of activities. And what the agency train you are used to be professional competencies, technical competencies, and procedural competence. So if you know something about scientific knowledge, about the mastering system, if you are able to follow a procedure, then it's already thought this being good enough to become an astronaut. But then lately, when we started flying on long duration mission, it turns out that these things are all important, but there are some other things that are equally or even more important, because when you are 6, 7, 8, 9, 10 people inside a small environment, then you need to look at communication. Do you communicate with other people? Are you able to communicate? Are you able to give feedback without being aggressive? Are you able to listen to what the other people are telling you? You need to understand that you are a team. Everybody needs to trust each other. You need to make sure that you are making the other people trusting you. So it's a 360-degree work that happen. You need to understand the concept of leadership or followership, because we are all able to discuss about the leader, but are we able to discuss about the follower? So the people that are not leader, what do? They sit there in the corner and don't say anything? Or they say something if they see something strange. And this requires understanding the situation and being able to understand your role and follow your role. You need to understand what's going on the station. There is a fire, there is no fire, you're losing your air or something. You need to understand. You need to understand the situation, make and take decision, and you cannot delay decision forever. You're losing air or some emergency, you need to take action. And sometimes, we see our politicians that, they discuss things, and 6 months later, they're still discussing the same thing, and nothing happened. The last thing that is also equally important is that you need to be aware of the fact that, people have different gender, different culture, different religion. You need to be able to work with these people, so you need to be aware of this situation, and when you work in a team, all of this needs to be taken care of. Of course, if you are, another point which I missed is the self-care, self-management. If you're not able to take care of yourself, you're in big troubles, because the space is relatively small. You start leaving things around all over the place. You start taking more space than you're allowed to. If there is anything that you're allowed to do, probably there is a space that is yours, but it's as big as a telephone booth, and the rest of the station is common, so you need to be aware of what's going on there. Of course, for commercial astronauts, we don't, or normally they don't look too much about the technical degree. So if you want to be in space for being a tourist, do you need to have a technical degree? Do you need to have a professional competence, technical competence, and procedural competence? You probably need to have all the other stuff because you need to work in a team. But all the training that is necessary for you to become an astronaut is much less than a professional astronaut. This is a picture of the space station. I took this picture. It looks like everything is in order, right? Seems a little bit confusing, but if you ask Matthias, is it in order or see, says Matthias, because I took this picture at night when nobody was around, because during the day it's a total mess. Stuff around. But then strange things happen. For example, one of the first days that I was up there, I read the procedure, and the procedure required me to work on an experiment up there. And I remember I was looking there and thinking, okay, there's surely a stair that I could take to go up there, because otherwise, you are a terrestrial person thrown into an extraterrestrial environment, so it takes quite some time. And an American astronaut was passing by, and I said, excuse me, but how do I go up there? And he says, well, just push yourself and you will go up there. And I did not quite believe it, but then, I pushed myself, and there I am up there. And of course, now I have the idea that, I'm going to be up there, and I will fall down and hit my head there, so I'm kind of holding on. But then I let go, because something strange happened. The brain is actually working in a very interesting way in microgravity. Essentially, what happens, it turns the station around, and you don't feel anything anymore. Whatever is on top of your head becomes the ceiling, whatever is under your feet becomes the floor, and you don't feel absolutely anything. And it's kind of disconcerting at the beginning, but then you get used to have this 3D kind of movement without being allowed to do these things without thinking too much. And look what happens. Is there the audio? So I took this video just to show you that there is not that much space in there. This is could be a typical dinner, but then you see things floating around. So if somebody is not reaching up and pick up the ketchup, oh, okay. But then, see there are a lot of people around that little table, and so you see there are some more people here, and obviously you cannot reach the table, so somebody invented to go on top of the table and eat in that way, which is kind of funny, because you think it's not possible, and it's absolutely possible. Nothing is happening. You don't feel absolutely nothing, and you have to get used to this kind of stuff. So for the professional astronaut, it's clear that you are the manpower of the space station, and so the space agency want to use your work, and so they make you work as much as possible. In fact, they took 12 hours a day, and this is, we call it jokingly Houston time, meaning that they come up with something they ask you to do. And it's not simple to put together something like this, because you need to make sure that whatever resources you're using, the same resources are not needed by another astronaut. So making sure that in this case, six astronauts work together without colliding one to each other, without taking the tools or the things necessary. It's kind of interesting. And this is I showed you the station before. This is an experiment. You see how the station can become fairly complicated with cables flying all over the place, computers tape, anything, because the point here is that the astronaut itself needs to be able to be put in the condition of performing whatever it needs to perform and produce data, because at the end, our task is to produce data that we do not analyze. I don't analyze whatever I produce. I just need to make sure that I produce something that has sense, makes sense, because if I do give to scientists the wrong data, they may get to wrong results. So our task is actually to do that, and it turns out, though, that you could be whatever, and you get enough training to carry out an experiment in any technical field. For example, here it's an astronaut dealing with plants. Here is another one dealing with something chemical. Here is something with satellite. Here is an astronaut dealing with an incubator. So you can do all sorts of stuff during the day, one after the other. Once in a while, you are the experiment, because they check how your body is working, what kind of power you can generate, what kind of gas you put in your lungs, what you throw out, things like that. Or they, for example, check the composition of the blood, which just changes with the fluid shift and things like this. So they need to make sure that your body keeps working. Of course, if this life support system needs some work, you cannot call Houston and say, Houston, can you send me a plumber? Guess who's going to do the plumber? It's you who does the plumber. Or if there is some kind of electrical, you start doing you being an electrician. Some kind of mechanic, you look for screwdriver and you start fixing things. And this seems obvious, but then the space station needs to be cleaned. You cannot have your mom or dad or sister coming or brother coming and clean it yourself with your 2 PhD. You take the vacuum cleaner and go around and vacuum the station. But then, something even funkier happens sometimes. So this is an astronaut talking to a school. So maybe the planning says, okay, you do some experiments, then you talk half an hour with the school, then you talk half an hour to the President of the Republic, then you talk half an hour with the Pope, and then when you're finished doing all of this, you keep fixing the toilet that was not working. So the point is, what is the most important thing? I talked to the Pope, President of the Republic, but the toilet is working, because otherwise it's a big problem. And so here we are with the professional astronaut today can use the Soyuz or the Dragon and fly on the International Space Station. Eventually, we keep going. There are going to be some tourists that they have enough money to buy a flight today even on the International Space Station. So it's kind of funny. You had tourists, right, Matthias, coming up while you were working, and there are these guys going around. It's kind of interesting. But then, what is an astronaut? It's kind of difficult. In theory, if you are going through the atmosphere and you go up in space and then you come back, in some definition, you are an astronaut. So as Richard Branson or Katy Perry astronauts, because they flew a suborbital flight. So see, the things get a little bit complicated. But then, in the future, most likely the space station will be deorbited around 2030. There are some other commercial space stations being built. There's Orbital Reef, Axiom Space Station, VAST. So it's going to be an interesting times where the space station will not belong anymore to nations or to organizations. There will be commercial space station, and it will be funny when NASA or the European Space Agency needs to carry out an experiment or send an astronaut for 20 days or 30 days or 6 months in space, and they have to have a contract with one of these companies. But then, in the future, we will have, I'm pretty sure we will still have different space stations. I like this drawing, this rendering. It's not real, but You know, I imagine the future space station like this. I like the artistic rendering of a lunar outpost, or even Mars becomes very interesting. And this work between, you know, professional astronaut and tourists is getting more and more and more complicated. We probably needed to come up with some kind of understanding. Like I said at the beginning, we have pilots, we have stewards, but then we have passengers, so we need to come up with something like this. Because at the end, it's true, we can go to the moon, we can go to Mars, but if we look a little bit beyond that, you know, the star closest to us is Proxima Centaurus. It's about 39,000 billion kilometers away. If we take one of our spacecraft and we go there now, it's going to take 4.2 light years, more or less. But since our spacecraft cannot go at speed of light, it can go, let's say, 30,000 kilometers per hour, it's going to take more or less 151,000 years to go there. So we need to come up with something different. That's why we have a Nobel Prize guy. That's why you are here trying to figure out the future and come up with a solution to this, which seems an impossible problem. But you know, if you look at life, we had a lot of problems that were solved. And once we find we have a problem, we find a solution. So I would, where is Paola? Okay. So
I was in the dark.
So
thank you very much
I
for
don't know
this
if I
presentation.
did answer the original question.
I think you very well answered how to survive and thrive in space with your experience, and also an outlook for the future, which was very nice.
Yeah, I would say that there is in space, there is a lot of space for everybody. There is space for professional astronauts doing experiments, but I would say that, you know, today you get only engineers, you get, you know, medical doctors, physicists, things like that. But then we are missing, in my opinion, you know, poets. We are missing artists.
Well, you guys did a very good job with your books, which we presented yesterday. You did a book signing today. There are a few questions. There are too many for the time left we have. But I'm choosing the ones that are the most sort of voted. There's one, somebody has been struck by the vacuum cleaner.
The vacuum cleaner,
that
yes.
you showed, the space vacuum cleaner. So how does dust and dirt look like on the space station? Does it behave differently than on Earth? Does it look different?
It looks like a dust and Earth that you have here on Earth. It's the same. The problem is that, you know, gravity will take it on the floor here, but there it just floats around, and it's easy for you to breathe it. Goes in your lungs. Not only that, there is a ventilation system on the station, and so there are filters, and all this dust tends to accumulate there. And if there is too much dust, then the fan inside there starts having difficulties, and it can actually cause a fire. And so if you don't clean the station, you risk to go in to get a fire.
Then I choose another one, which is a bit more technical, and is the last one I take in spite of many others, but maybe you can be grabbed by the public once more and answer privately. So it seems that the space station is regularly put back on orbit. Why is that? Do you change orbits from time to time?
Well, orbit is probably the inclination with respect to the equator, and that doesn't change and is dictated by Baikonur. But what changes is the altitude, so that because even at 400 kilometers there is a little bit of stuff, with maybe molecules or something like this, and this is enough to actually break the station, and the station loses more or less 100 meters per day, more or less. So you know, the station comes down, but then if you let it go too much, it's going to go down and touch the atmosphere, it gets destroyed. So once in a while, a supply vessel is used to push the station up again, and so the station altitude is not exact, but it's around 400 kilometers, more or less.
So it's time to send you back to seat. Again, if you want to talk, there are many more questions. Thank you very much.
Thank
Big
you,
applause.
thank you.
Thank you for being so available with us. And I'm now giving the floor to my colleague, actually my boss, Arnaud Marcelier, head of CERN Communications, who is going to introduce the next astronaut. Thank you, Arnaud. This is the iPad.
Yeah, thank you. Bonsoir, bonsoir. Juste une petite seconde pour m'installer. Oui, donc on avait beaucoup d'astronautes avec nous aujourd'hui et c'était un plaisir. On a parlé beaucoup des missions, on a parlé des touristes et on va parler maintenant un petit peu plus du futur aussi. Bon, Paolo en a un petit peu parlé du futur. Là, ce dont on voudrait parler, c'est un petit peu plus de la Lune. Beaucoup de gens pensent que la Lune, on y est allé il y a quelques années maintenant. C'est vrai. Mais en fait, ça reste quelque chose d'actualité, et même beaucoup d'actualité, parce qu'il y a une sorte de course, de nouvelle course à la Lune. Et c'est un petit peu de ça dont on va parler ce soir avec Mathias. Juste pour faire la transition, avant d'accueillir Mathias, on va mettre un petit clip rapide qui va montrer un petit peu ce que c'était que la mission de Mathias. On va parler un peu de sa mission, et puis après, on ira vers la Lune.
Next up is European Space Agency astronaut Matthias Maurer.
Full forward over center.
Yes, I'd say maybe there's like just a tiny bit of offset to see, and it was that good cut out.
Roger, Matthias, we concur with that.
Eh ben, applaudissements pour Mathias qui va nous rejoindre.
Bonsoir.
Alors, comme j'ai dit, on va parler un peu plus de la Lune, mais on revient de voir quand même un peu des images. C'est difficile de résumer plusieurs mois dans l'espace en quelques minutes. J'imagine que tu as vu ces images-là des centaines de fois. Est-ce que ça fait toujours la même émotion quand tu les vois, quand tu revois tous ces moments? Est-ce qu'il y a des choses qui ressortent à chaque fois?
Oui, bon, de passer 6 mois dans l'espace, c'est toujours tellement plein des aventures, des expériences, de la joie, des moments très précieux. Et donc, chaque fois que je vois cette vidéo-là, j'ai encore des goosebumps, la poêle.
Des frissons.
Des frissons, oui.
Ok, je me rappelle, alors, il se trouve que j'ai travaillé un peu à l'ESA, on a travaillé un tout petit peu ensemble. Quand tu as volé, j'étais déjà à l'ESA. Et je me rappelle, les collègues disaient « Oh, Cosmic Kiss, c'est pas un nom très commun pour une mission spatiale. » C'est vrai qu'on était habitué à des choses un petit peu plus, je sais pas, mythologiques ou autres. Moi, j'ai trouvé ça très poétique, en fait, Cosmic Kiss. Est-ce que tu peux juste nous dire d'où ça vient, cette idée, Cosmic Kiss?
Oui. Donc, comme Paolo a déjà expliqué avant, comme astronaute, on est aussi ambassadeur. Donc, il faut aussi expliquer pourquoi on voyage dans l'espace. Et l'explication de la ESA, l'explication officielle, c'est chaque euro investi dans l'espace, ça crée 2 euros. OK. Donc, moi, j'ai pensé, OK, peut-être économiquement, c'est correct, mais ce n'est pas vraiment la raison pour laquelle moi, je suis devenu astronaute. Moi, je suis astronaute parce que j'ai des grandes questions. Des questions comme on a déjà discuté dans les discours avant. Qu'est-ce qu'il y a dehors? Qu'est-ce qu'il y a dans l'espace? Comment est-ce que l'univers a commencé? Est-ce qu'il y a de la vie dehors? Et donc, moi, je trouve la fascination de vouloir savoir, de vouloir comprendre, ça, c'est la motivation pour aller dans l'espace. Et donc, ça, je voulais mettre dans mon nom de mission. Et pour moi, je voulais exprimer une déclaration d'amour pour l'espace. Et pour cela, c'est devenu Cosmic Kiss.
Merci. Alors, il y a beaucoup de choses techniques dans l'espace. On va en parler un peu plus avec la Lune. Mais il se trouve que tu as fait, comme beaucoup d'astronautes, tu as fait une sortie extravéhiculaire. Tu peux nous dire un peu à quoi ça ressemblait? Qu'est-ce que tu es allé faire dehors? Tu as parlé d'aller dehors explorer. Qu'est-ce que tu as fait dehors, là-haut?
Tout à fait. Donc, une sortie spatiale, une sortie extravéhiculaire, c'est quelque chose de vraiment extraordinaire. Donc, pour moi, c'était la grande rêve d'astronaute, c'était une fois d'aller dans l'espace, de voyager sur une fusée. Et la deuxième grande rêve, c'était d'ouvrir la porte et de sortir dehors. Et donc, le moment où tu ouvres la porte, ton cerveau te dit « Ah non, reste dedans, parce que dedans, c'est beaucoup plus safe. Hein. » Mais quand même, tu as beaucoup préparé pour ce moment-là et la NASA t'a donné un dossier, un cahier de devoirs, une liste des activités que je devrais faire. Et la NASA m'a dit, OK Mathias, amène ton passeport parce que toi, tu vas être sur le module américain, après sur le module japonais, là, tu vas réparer quelque chose, puis tu mets un câble, après, tu vas sur le module européen, tu vas essayer de fixer quelque chose. Et aller-retour, après fixer autre chose. Et donc, j'ai fait beaucoup de trajets. La sortie était super exceptionnelle. Moi, je trouve émotionnellement, c'était exactement les mêmes émotions comme d'aller dans l'espace, encore une fois. Tu vois, c'était la journée, je crois la nuit après, c'était la seule fois que j'ai rêvé. Et je me suis réveillé 2 fois ou 3 fois parce que j'ai pensé, le câble n'est plus attaché à la station, je vole dans l'espace, je suis perdu. Et c'était vraiment émotionnel.
Ça s'est bien passé avec le câble?
Ah oui. Bon, comme tu vois, j'ai bien trouvé la rentrée.
Très bien. Ici, on est au portail de la science, on est au CERN, c'est la science qui nous fait vibrer, la technologie aussi. Est-ce que, tu as fait des dizaines d'expériences, est-ce qu'il y en a une peut-être qui était un petit peu plus spéciale ou un petit peu rigolote, je ne sais pas, une expérience que tu as envie de mentionner ce soir, parce que si on les cite toutes, on est là jusqu'à demain matin.
Oui, donc j'ai participé dans environ 150 différentes expériences. Il y a des expériences qu'on fait seulement une fois, mais il y a aussi des expériences médicales, par exemple, où il y a environ 10 astronautes qui participent pour voir un peu aussi la statistique. Et donc, cet après-midi, j'ai déjà expliqué que j'ai dû mélanger du béton sur la station, donc je ne vais pas répéter ça maintenant. Mais on a aussi fait des autres expériences. Par exemple, quand j'étais dans l'espace, c'était pendant l'époque de Covid. Et pendant l'époque de Covid, je crois la meilleure place, c'était dans l'espace, parce qu'on n'avait pas des masques, on n'avait pas de protocole, et donc on a pu travailler comme toujours. Mais on a aussi fait de la recherche qui a de l'importance par exemple, pour éviter une prochaine pandémie. Par exemple, toi, imagine, tu es malade, tu vas dans un bâtiment public, peut-être ici à CERN, tu touches le poignet d'une porte, et tu laisses des bactéries, des virus sur la poignée. Après, tu es déjà parti. Moi, j'arrive à cette porte et je ne sais pas que toi, tu étais malade, je ne sais même pas que tu étais là, et je touche la poignée là, et maintenant, moi, je peux m'infecter. Et donc, une des idées, c'était comment est-ce qu'on peut créer une poignée, un matériau qui tue toutes les bactéries, tous les virus qui sont posés là-dessus. Et donc, il y a des scientifiques vraiment intelligents, ils ont développé un traitement avec des lasers. Donc, ils ont pris des matériaux traités et maintenant, si tu touches cette surface, normalement, elle va éliminer toutes les bactéries là-dessus. Et donc, c'est vraiment quelque chose qu'on pourrait appliquer dans des cliniques ou, je sais pas, dans des bâtiments publics pour réduire le risque d'infection. Maintenant, peut-être tu veux savoir pourquoi est-ce que j'ai testé ce matériau dans l'espace.
Oui, j'ai envie de savoir, oui.
Oui, donc, dans l'espace, on a un problème, ou on a deux problèmes. Le premier problème numéro 1, c'est les astronautes. On a un système immunitaire qui est vraiment plus faible comparé à la Terre. Donc, il y a un risque plus élevé qu'on peut tomber malade. L'autre risque, c'est les virus, les bactéries dans l'espace. Ils sont plus agressifs, ils se développent plus rapidement parce qu'ils sont aussi stressés par la micropesanteur, par la radiation. Et donc, il y a plus de probabilité d'un côté et plus de probabilité de l'autre côté. Donc, le risque est élevé. Et on a essayé si les matériaux-là fonctionnent dans l'espace. Et c'est vraiment quelque chose d'intéressant. Et j'espère qu'on va trouver ça aussi bientôt dans la vie quotidienne sur Terre.
Merci. Alors on va aller un peu sur la Lune parce que c'était le contrat, c'est ça dont on a parlé. J'ai un peu dit qu'il y avait une nouvelle course à la Lune. Est-ce que tu peux nous expliquer un peu pourquoi, comment ça se passe, qui va aller sur la Lune, quand, comment, pourquoi on y retourne, juste en quelques mots avant qu'on monte le petit film sur Luna.
Ok, donc la Lune, c'est là, et tout le monde regarde la Lune et peut-être rêve comme moi. C'est mon troisième rêve que je dis, oh, j'aimerais tellement bien voyager vers la Lune et d'explorer la Lune. Et donc, les astronautes Apollo, ils ont ramené des échantillons, on a pu analyser, mais maintenant, on sait beaucoup plus que la Lune est plus intéressante que de ce qu'on pensait dans les années 70. Et donc, maintenant, on sait qu'il y a de l'eau congelée, de la glace, dans les zones polaires. Et de l'eau, c'est vraiment une ressource, c'est vraiment énormément important. De l'eau, on peut boire, donc c'est bien pour nos êtres humains. On peut le séparer en hydrogène, oxygène, donc j'ai aussi de l'air que je peux respirer. En plus, hydrogène, oxygène, c'est rocket fuel. Et donc, on peut faire un plein sur la Lune pour continuer le voyage dans l'espace. Et en plus, l'eau qu'on trouve là, peut-être, cette eau-là est arrivée sur la Lune peut-être au même moment que l'eau est arrivée sur la Terre. Et donc, avec cette eau qui venait de l'espace, venaient aussi des molécules, tu sais, le début de la vie. Ici sur Terre, si tu veux chercher comment est-ce que la vie a commencé, tu ne vas plus trouver cette trace-là. Mais sur la Lune, peut-être ils ont congelé dans cette eau. Et donc, cette eau est vraiment précieuse. Et seulement d'y aller, de retrouver l'eau et de l'analyser, ça va nous aider beaucoup à peut-être à découvrir comment est-ce que la vie est arrivée sur la Terre. C'est une des raisons.
Ok, donc on va retourner sur la Lune vers les pôles plutôt.
Oui, aussi, ici
comment
on
va
va
faire
la radiation, donc radioastronomie, c'est un grand rêve. J'ai aussi appris hier, il faut mettre 4 seismomètres sur la Lune et peut-être un petit trou noir va traverser la Lune et on peut le mesurer. Donc c'était 9 pour moi. Donc il y a plein de raisons scientifiques pour lesquelles il faut rentrer sur la Lune. Donc maintenant, si on rentre, il faut avoir des fusées beaucoup plus puissantes que la Falcon 9 avec laquelle je suis allé sur la ISS. Même pas le Space Shuttle est assez puissant pour aller vers la Lune. Donc maintenant, il y a le SLS, la fusée très puissante américaine, qui va nous permettre de rentrer vers la Lune. Après, il faut avoir une navette pour descendre un lander. Ça, ce n'est pas encore développé. SpaceX est en train d'y travailler. Il y a aussi Blue Origin qui travaille là-dessus, donc il y a un peu de compétition. Mais la plus grande compétition, je crois, ça vient de la Chine. La Chine...
Que tu connais bien, parce que tu as travaillé aussi avec les taïkonautes.
Oui. À une certaine époque, c'était prévu que nous, les Européens, volent aussi avec les Chinois. Maintenant, politiquement, ce n'est pas si facile, donc on a arrêté un peu la coopération. Bon, mais peut-être les Chinois vont allunir en 2029, parce que c'est le 80e anniversaire de la République chinoise. Et moi, ce que j'observe de loin, je crois que les Chinois sont vraiment dans peut-être la pole position d'y arriver avant les Américains.
Ok. Alors, je propose qu'on regarde un petit clip encore à nouveau. Un petit clip qui va parler d'un projet qui te tient à cœur, que tu mènes à Cologne. Un projet qui s'appelle Luna et qui permet de se préparer pour retourner sur la Lune. On va regarder ça.
Luna is for me the moon on Earth.
We're going back to the moon, and that's where it's getting real.
The next time we land on the moon, we will be part of it.
Guidance systems online. Ground control, this is Order 1. We have a green light to go, roger.
Being here in Luna feels like walking on the moon right now.
Alors, au CERN, on a beaucoup de bâtiments impressionnants, mais on n'en a pas de comme ça. Alors, est-ce que tu peux nous expliquer un peu, c'est tout nouveau, ce bâtiment?
Oui, c'est tout nouveau. Effectivement, ça a été inauguré exactement au même temps quand vous avez inauguré votre Science Gateway. Exactement. Donc, on a vu Luna maintenant, mais c'est exactement en face du centre des astronautes européens. Donc, c'est à Cologne et c'est la seule place en Europe où on entraîne des astronautes pour aller dans l'espace. Ce centre d'astronautes, ça nous prépare pour les missions, pour aller à la station spatiale. C'est dans l'orbite proche, donc à 400 km d'altitude, et pour travailler en micropesanteur. Mais une fois qu'on rentre sur la Lune, on n'a plus de micropesanteur. Donc, on a la gravité lunaire, qui est à 1/6 de la gravité d'ici, sur la Terre. Et là, on a vu, il y a plein de poussière. Il y a le Soleil qui est vraiment assez bas vers l'horizon, parce qu'on est dans la zone polaire. On a des roches lunaires, et notre travail ressemble plutôt à un travail de géologue. Donc, il faut apprendre comment travailler comme géologue. Donc, on a appris d'aller dans des zones sur la Terre qui sont volcaniques, parce que sur la Lune, il y a des zones volcaniques. Puis, on a aussi été au nord de Norvège, parce que là, il y a des différentes zones qui s'appellent anatosiques. Donc, c'est une complètement autre géologie. Et puis, il y a aussi des cratères sur la Lune. Et en Allemagne, il y a aussi un très bon cratère qui a été créé il y a 15 millions d'années. Il a un diamètre de 200 km. Et donc là, il y a la troisième géologie qu'il faut apprendre. Donc tout ça, c'est beaucoup de travail de voyager toujours et on ne peut pas s'entraîner tous les jours. Et de là est venue l'idée, ok, est-ce qu'on peut ramener de la géologie typique qu'on trouve et qu'il faut apprendre à Cologne. Et on a fait ce bâtiment avec la poussière lunaire, donc ce n'est pas la vraie poussière lunaire, mais c'est chimiquement la même propriété, ça ressemble en taille. Et on a installé la lumière comme sur la Lune, on a maintenant une installation qui réduit la pesanteur. Donc dans Luna, je pèse 1/6. Et donc je pèse comme sur la Lune. On a un scaphandre qui me limite dans mes actions de travail, qui rend tout le travail plus dur. Et tout ça. Donc on a vraiment reconstruit une petite Lune à Cologne parce que là, on veut pratiquer avec les astronautes, avec les géologues, avec les ingénieurs de comment explorer la Lune. Et au début, il y a toujours des problèmes. Il y aura des problèmes qu'il faut résoudre. Et on espère que tout ça, tous les problèmes, on va les rencontrer à Cologne. Et plus tard, sur la vraie Lune, ça va fonctionner sans problème.
Alors, comment ça se passe? Est-ce qu'il y a déjà des stages d'astronautes qui sont organisés? On va passer, je sais pas, un mois avec un programme de travail et des entraînements spécifiques à faire, comme on fait en piscine aujourd'hui déjà? Comment ça se passe?
Ça va être similaire. Donc, dans la vidéo, on a vu le bâtiment. Donc, maintenant, on voit déjà plus parce qu'à l'extérieur de ce bâtiment-là, on a une petite station lunaire. Et cette station lunaire va être connectée avec un tunnel, avec la surface lunaire. Et la prochaine mission sur la Lune, ça va durer 6 jours et demi. Donc, c'est déjà calculé de la NASA. Mais 6 jours et demi, ça ne veut pas dire qu'un astronaute reste 6 jours et demi dans un scaphandre à la surface. Non, on va rester dehors 8 heures max par jour. Et la journée après, on est trop fatigué, donc il y a une journée de pause. Donc, toutes les 48 heures, on va faire une sortie de 8 heures. Et les autres 40 heures, on reste à l'intérieur. Donc, on dort, il faut se nettoyer, il faut aussi préparer le scaphandre, il faut analyser un peu les échantillons, les outils. Et donc, tout ça doit être préparé. Et tu as raison, dans le futur, on va travailler 6 jours et demi, on va faire un petit stage pour les astronautes, et on va faire 6 jours et demi dans la station et sur la surface. Et donc, on va faire un rehearsal, une simulation identique comme sur la Lune. Mais en plus, on a aussi des scientifiques. Luna, ce n'est pas seulement pour les astronautes, c'est aussi pour les gens ici qui veulent préparer une expérience pour la Lune. Vous êtes bienvenus de venir chez nous et de travailler ensemble avec nous. Comme ça, vous expliquez mieux aux astronautes de quoi nous devions faire. Et nous, on peut aussi expliquer, OK, votre expérience fonctionne mieux si vous faites des petits changements. Et comme ça, on va tous apprendre.
Alors, je sais bien que c'est difficile de faire des prédictions, mais du coup, c'est quand est-ce qu'on y retourne sur la Lune, qu'on se pose et qu'on fait parce qu'on se prépare à s'entraîner, donc à se poser, passer 6 jours et puis pouvoir sortir, aller explorer. L'horizon, c'est dans 5 ans, dans 10 ans. Donc, ok, les Chinois, j'ai compris, mais donc nous, Européens, dans ton rêve, c'est quand?
Bon, nous, les Européens, on n'a malheureusement pas de capsule pour aller toute seule, donc ce n'est pas sous notre contrôle de préparer le voyage là. On est partenaire avec les Américains maintenant avec l'accord qu'on a avec la NASA, donc on a prévu de faire une petite station qui s'appelle Gateway, qui est prévue de voler dans les prochaines années autour de la Lune. Et les Européens, nous avions déjà 3 billets pour 3 astronautes d'aller vers cette station. Pas encore à la surface de la Lune, ça il faut encore négocier. Mais j'espère que dans les prochaines 5-10 années, on voit aussi des Européens marcher sur la Lune.
Très bien, je te le souhaite.
Merci beaucoup.
Peut-être on va prendre, je crois qu'on arrive un petit peu à la fin, on va prendre quelques questions. Il y a une question, c'est pas forcément la plus populaire, mais c'est la plus à propos. Peut-on visiter Luna à Cologne? Est-ce qu'on peut venir visiter?
Oui, on peut venir visiter Luna. Effectivement, il y a des visites organisées. C'est tout à travers de DLR. Donc, on peut visiter le centre d'astronautes et Luna, mais il y a seulement des petits groupes. Donc, ici, je crois, il y a 150 000 visiteurs par année.
Même plus.
Ah non, bon, il faut enlever 2 ou 3 ou 0.
Il faut réserver à l'avance, c'est comme pour aller sur la Lune.
Oui, c'est ça. C'est plus facile et plus rapide et efficace si on veut collaborer avec nous. Donc là, vous êtes directement bienvenus.
Il faut proposer des expériences pour Luna et là, vous gagnez un ticket pour aller passer 2 mois à Cologne et voilà. Est-ce que vous allez faire des films?
Pardon?
Des films.
Ah oui, on pourrait faire des films, effectivement. Il y a déjà des gens qui ont dit que ça a l'air extraordinaire. La NASA aussi. La NASA a développé une nouvelle caméra en coopération avec Nikon. Donc c'est une caméra Nikon, mais avec un programme spécial de la NASA. Et eux, ils sont venus à Cologne parce que eux, ils ont dit ça c'est la meilleure place sur notre planète pour faire un film, pour pratiquer de travailler avec la caméra là.
D'accord. Il y a une question qui est très très populaire et c'est sur la relation avec les Russes. Comment toi tu vois l'évolution de la collaboration avec les Russes? J'imagine dans le cadre de la Lune, mais même en général, même au niveau de la station et des activités spatiales en général.
Oui. Donc dans le vidéoclip de ma mission, au début, on a aussi vu un petit moment où on a ouvert une porte et un collègue est entré dans habillé en jaune et bleu. Et donc c'était le 18 mars 2022, c'était mon anniversaire. C'était mes camarades que j'avais invités pour mon anniversaire. C'était les astronautes qui sont arrivés. C'était des Russes qui sont arrivés 2 semaines, 3 semaines après le début de la guerre en Ukraine. Et effectivement, c'était un moment assez triste, une situation très difficile sur la station. On continue à travailler ensemble sur la station ISS, parce que c'est impossible de continuer la station seulement avec les Américains ou seulement les Russes. La machine ne fonctionne pas si on ne travaille pas ensemble. Mais malheureusement, à cause de la guerre, de la situation, on ne travaille plus ensemble dans des autres domaines. Et même une collaboration pour la Lune, le Gateway, c'est un programme avec tous les partenaires de la ISS, sauf les Russes.
Okay. Revenons juste un petit peu, ce sera la dernière question, revenons un petit peu sur l'ISS. L'ISS arrive quand même un petit peu en fin de vie. How do you feel about disorbiting the ISS?
Ah oui, ça me rend, je sais pas, ça me fait mal au cœur. Effectivement, quand on est astronaute, chaque semaine, il faut parler avec son médecin, il contrôle qu'on va bien. Et toutes les 2 semaines, c'est obligatoire d'appeler son psychologue. Et donc, on a tous un psychologue qui regarde est-ce que tu as des problèmes, est-ce que tu es bien avec tes collègues, est-ce que tu es triste, est-ce que tu es content. Et donc, mon psychologue, à la fin de ma mission, il a dit, écoute, peut-être tu ne vas plus jamais rentrer sur la ISS. Donc, peut-être c'est la dernière fois que tu étais là. Je sais qu'il y a des moments vraiment extraordinaires que tu as vécu là-bas. Et donc, je donne la bonne recommandation. Fais encore une fois le tour de la station. Regarde tous les petits coins et essaye de souvenir, de penser aux souvenirs que tu as, tout ce que tu as vécu là dans les petites zones. Et pour moi, c'était vraiment important de dire au revoir, même si j'espère peut-être une fois de rentrer, mais j'espère plutôt aussi d'aller vers la Lune, mais de voir ou de penser seulement qu'on va perdre cet instrument, cette machine extraordinaire qui a servi 25 ans déjà, il va nous servir encore 5 ans, ça me rend triste. Mais aussi, c'est le début peut-être de quelque chose de nouveau. On va avoir des nouvelles stations, des stations commerciales, plus petites, peut-être, j'espère, moins complexes, mais avec une technologie plus moderne. Oui, c'est ça. Donc la vie continue.
Merci beaucoup, Mathias. Beaucoup d'applaudissements pour Mathias.
Merci beaucoup. Merci beaucoup.
Is it on? Yes. Don't go away. Just let's stand up. Get ready for a grand finale. Before announcing what it is, I would like to call on stage all these speakers present in the room. I can see Paolo here, Patrizia Caraveo, Teresa Montarulli, Megan, Christian. Is there any Nobel around? Are they all going? They all went to bed? And yes, of course, somebody you have not seen but has been crucial to prepare this event.
Yep.
Dante.
Many people are over there. You don't see them. You've seen a lot of guys as well who have been key to prepare this event today. So a big applause also for all the people who make this happen.
And Dante Larini, who is the head of event management in the Science Gateway. I don't know, Dante, if you want to say one word before I announce what we are going to do now, all together. So you want to say something?
Ladies and gentlemen, dear guests, dear friends, it was a fantastic pleasure to have you all here at the Science Gateway. C'était un plaisir d'avoir ce festival scientifique qui mêle vraiment des conversations scientifiques avec cet esprit festif. Donc vraiment, merci beaucoup du fond du cœur d'être présent. Donc on aura une surprise organisée par Paola et nous nous quitterons en musique avec un magnifique groupe, Miss Proper, qui jouera de la musique rock à notre sortie. Merci beaucoup à tous.
Super,
merci à toute l'équipe technique et merci à l'équipe du Science Gateway.
Je vais continuer en anglais. So the surprise is that in 16 minutes exactly is going to be the 20th of July. Does this date ring a bell? What happened 56 years ago on the 20th of July? First human moon landing. So we found for you the original footage of the Apollo. And please be silent because the commentary and the exchange, the conversations between the astronauts and control are amazing. They give le frisson, like you said, goosebumps.
We're now in the approach phase, everything looking good.
Go for landing. Retro.
Go.
Fido.
Go.
Guidance.
Go.
Control.
Go.
Telcom.
Go.
GNC.
Go.
Ecom.
Go.
Surgeon.
Go.
Capcom, we're go for landing.
Roger, understand. Go for landing. 3,000 feet. 1201. 1201.
Roger, 1201 alarm.
Same type, we're go flight.
Okay, we're go.
We're go. Same type, we're go. 540 feet down at 30 and at 15. Then 400 feet down at 9.
Okay, the only call-outs from now on will be fuel.
Gate forward. 10 and 50 feet down at 4.
P66.
30 and a half down. Epic shadow up there. 50 down at 2 and a half. 19 forward.
Okay, Bob, I'll be standing by for your call-out shortly.
3 and a half down. 220 feet. 13 forward. 11 forward, coming down nicely, 200 feet. 4 and a half down. 5 and a half down. 100 feet, 3 and a half down. 9 forward. 5%. 185. Okay, 75 feet. That's looking good.
60.
Down a half.
Roger. 60 seconds.
60 seconds. Lights on. 6. Down 2 and a half. Forward. Forward. That's 40 feet down 2 and a half. Picking up some dust. 30 feet, 2 and a half down. Straight shadow.
Stand by for 30.
4 forward. 4 forward. Drift into the right a little.
30
Down
seconds.
a half. 30 seconds. Forward. Just. Good. Okay. Contact light. Okay, engine stop.
We've had shutdown.
We copy you down, Eagle. Tranquility Base here. The Eagle has landed. Roger, Tranquility. We copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again. Thanks a lot.
Break, Buzz, this is Houston. Radio check and verify TV circuit breaker in.
Roger, TV circuit breaker's in.
Okay, Neil, we can see you coming down the ladder now. At the foot of the ladder, the surface appears to be very, very fine-grained as you get close to it. It's almost like a powder. I'm going to step off the limb now. That's one small step for man, one giant leap for mankind.
There couldn't be a better ending, and I invite now everybody to leave the room and join us on the piazza. There will be the last concert of the evening, Miss Proper and the Moving Targets. Thanks, everybody. Thanks to the speakers, and thanks to you who have been with us for the whole night, and thanks to those who followed on YouTube.
And a big thank you to the technical team who have been working hard to make this event a reality. I think they also deserve a round of applause. Thank you to all the people from CERN, technical team, who were able to make this a reality. Thank you.